session, I would like to invite Dr. Sanat Tiwari from IIT Jammu. I welcome Dr. Sanat Tiwari on the stage to request to start session.
So good afternoon, everyone. Welcome to the fifth session of this plasma PSC colloquium. And so this is the second session for the day. And the session is on exotic plasmas, including dusty plasma. We have 4 speakers in this session. Professor Pintu Bandyopadhyay from Institute for Plasma Research, and 3 other speakers. 4 other speakers. Deepak Kumar from JNU, Sachin from IIT Jammu, Mona Lisa from IPR Gandhinagar, and Justin Reggie from Vellore Institute of Technology. So I will begin the session with Professor Pintu Bandyopadhyay. So before we start, I will briefly introduce our speaker. So Professor Bandyopadhyay completed his master's from University of Kalyani, and after that he joined Institute for Plasma Research for his PhD in 2000, and then he completed his PhD in 2007, if I'm not wrong. After that, he was part of Max Planck Institute of Extraterrestrial Physics, MPE, before joining Institute for Plasma Research back as a faculty in 2012. And since then, he's leading the dusty plasma physics research from his lab. I think his experience is more than 20 years now, or almost 20 years in this domain. And he's leading a laboratory which is one of the best dusty plasma laboratories around the globe. He has produced more than 60 papers in this domain, one of the best papers for dusty plasma physics. And his lab also been the first in predicting the solitons, dust acoustic solitons in this domain. So with this, I will invite Professor Bandyopadhyay for his talk. Thank you.
Thank you, Sanat, for your nice introduction. Before starting, I would like to thank the organizer, PSSI 2025, for giving me this opportunity to tell something about what we are doing here. And so I'll tell about the complex plasma, which we consider as a test bed for multidisciplinary research. So I am from IPR, and I am also enrolled in HBNI, and this is where we work at IPR. So I divide my talk in two parts. So first I will give an introduction of dusty plasma and what kind of works are going on over the globe. And then if time permits, I will talk what we are doing in our lab at IPR. So basically, complex plasma or dusty plasma is a plasma in which we have two component conventional plasma along with a small charged particle into the plasma. So what happens if you introduce the dust particle into the plasma? They get immediately charged by collecting more ions, more electrons than ions because of their high mobility, and get negatively charged. And when they enter into the plasma environment, they find a suitable place where the electrostatic force acting on them get balanced by the gravity and behaves like electrons and ions in a like how they do in a conventional plasma. So because of this heavy charged particle and the amount of charge they acquire is around 10,000 to 1,000 to 10,000 electron. So their time scale is very slow, very, very slow compared to electron and ions, but faster than the colloids. So it is very easy to study their dynamics because their time scales are very slow. So you need some kind of optical diagnostics to track them, and when you are successfully tracking them, you can study many things. So another characteristic is the behaves like a colloid. So in the colloidal system, you can study very easily the phase transition, phase coexistence. In here also, we can study. I'll talk in much more detail in the later slides. So this is another characteristics of a dusty plasma. So as I told earlier, when you put a dust particle into the plasma, they get negatively charged or they get charged depending upon the current that come into its surface. So mainly it is combined of collection of electron, collection of positive and negative ions, secondary electron emission, photoelectron emission, and thermodynamic emission. And at the equilibrium, the total current on its surface becomes equal to 0. But in the laboratory experiment, we have only the dominant current, that is the electron current and the ion current. So from our class 12 knowledge or class 10 knowledge, when you put a spherical particle, it acquires a capacity. And that capacity is equivalent to 4 pi epsilon A. That is directly proportional to its dimension. And if you apply voltage, so that total charge will be 4 pi epsilon Q is equal to C into V, so 4 pi epsilon 0 A into phi S, where the phi S is the surface potential with respect to plasma potential. And this phi S can be calculated very easily by equalizing the electron current to the ion current if you consider the other current is equal to 0 or very negligible. So for example, if you consider the electron temperature and ion temperature is equivalent to 1 eV, and if you consider the hydrogen plasma and the particle is of 1 micrometer, you can get a surface potential is of negative 2.5 volt. And the charge acquired by the particle is 2000 of electronic charge. So as these particles are charged particle, so it will of course experienced by the gravity and the electrostatic force. And I told at the equilibrium this electrostatic force gets balanced by the gravity. And because of that, and when you have many of such particles, this system behaves like collective properties like other species in the plasma does. So other than the gravitational and electrostatic force, there are many more forces that act on the dust particles. One of them is the ion drag force. The ion drag force is nothing but the momentum imparted by the ions on the dust particle is known as ion drag force. And because of ion drag force, you can study many phenomena like void formation and other ion-driven collective modes in a dusty plasma. So another important force that acts on the dust particle is the neutral drag force. It is similar to the ion drag force, but as it is neutral and the drag force is mostly dominated by the collection of neutral by the dust particle. So the other force that act is the thermophoresis force. What it is? Suppose you put one particle in between two electrodes, and if you have hot electrode in the bottom and cold electrode in the top, there will be some flow of neutrals. The hot neutrals will go from bottom to top and they transfer their momentum to the dust, and they showed that this particle experienced some force. And people found that due to this thermophoresis force, one can obtain the convective patterns and other phenomena. So I have tabulated the force, how it depends upon the size of dust particles, and mostly the predominant forces in the dusty plasma that they experience is the gravity and the electrostatic force. So the other force may come into the picture when you do something to activate those forces. So the question may come, why we need to study dusty plasma? So, I mean, you may also face this kind of questions, why we really need to study the dusty plasma. So the first point what I have tabulated here, to study the basic phenomena. So we have encountered many problems that are associated with many branches of physics, starting from classical mechanics to thermodynamics to statistical mechanics to fluid mechanics to soft condensed matter to many other fields. And this is a test bed. You need a very small device, and those particles are so heavy you can just shine a laser and you track them, their coordinates, and from there you get ample amount of information. From there you can study many basic phenomena. The understanding of astrophysical and solar phenomena, like the dust tail, the Saturn's ring, the moon clouds. Actually, when Morphill started the dusty plasma in 1980s, he was motivated by the Saturn's ring. He tried to simulate this Saturn ring into the laboratory plasma. And from there, now we are doing across the globe the dusty plasma in different labs. Dust in tokamaks. So in tokamaks, dusty plasma play both positive and negative role. So what are the positive role, you may ask? The plasma diagnostic. Suppose one dust particle is going from edge plasma to core plasma, and it radiates some emission. And if you can capture those emissions, you can predict what is the density and temperature of the plasma. You can study the dynamics, how it is interacting with the electric and magnetic field. Disruption mitigation. So sometimes we introduce the dusty plasma, dust particle into the plasma in the tokamak environment to mitigate the sudden disruption. So what are the negative role? So because of the dust particle erode from the dust surface, where plasma interact with the surface, like PFCs, limiter surface, diverter surface. So what happened there? The wall material come out from the plasma, and the wall becomes weak. So it can damage the plasma facing component or plasma walls. Tritium retention. Sometimes the particle they absorb in the tritium particle they absorb in the dust surface, and that can pollute the plasma environment. Dusty plasma is also introduced in the application of industrial plasma. The lithography, that they are producing the small electronics chips in the plasma environment, and they are facing problems to make the silicon wafer. So how we do experiment? It is a very, very simple experiment. You make a plasma. You make a plasma in between two electrodes. You put the dust particle. They get charged. They find an electric field. They levitate. You put the laser, captured by the camera. And that's all. When you capture their dynamics by a camera in a computer, so you can track their individual coordinates over the time, so you can measure many, many parameters from this particle coordinate. So this is one of the pictures that were taken in our lab. In our lab. So this is forming a very nice crystalline structure, very ordered crystalline structure. And if you see, these particles form a one-dimensional crystalline structure. This is the vertical view of the particles. Why it is so? Because you are using very monodispersive particle, and the electric field, because of these particles feel a homogeneous electric field by which they form a nice 2D crystalline structure. And from the coordinate, you can get a pair correlation function that gives you what is your interparticle distance and how periodic or how ordered structure they are maintaining. Another important factor is kinetic temperature. In all of your plasmas, you put some active or passive diagnostics to measure the plasma or electron temperature. But here what we do, we know the particle velocities from the information of space and time. From there, you can get the velocity distribution function along x and y. From there, you can easily calculate what the kinetic temperature those particles have. For this experiment, we have the particle temperature of 0.05 eV, slightly more than the room temperature. Though very early in 2000, people studied the plasma crystal in 2 dimensions, like what I have seen in my experiments, and 2D and 3D BCC, FCC crystalline structures by performing simple experiment using camera and laser. So like other materials, we can see the point defect and the point defect and line defect. If you see very carefully, you can see a line defect here. You can see many point defect here. So another important parameter is the Coulomb coupling parameter. That is basically defined by the potential energy of those particles to the thermal energy. So that is Q square divided by 4 pi epsilon 0 kT into interparticle distance. So when this factor gamma is more than 1, much more than 1, we call it as a solid. It is proven that if it goes beyond 179, then this system shows a crystalline structure. When it is less than or a little bit above 1, it is showed the liquid structure, and less than 1, it shows the gaseous structure. So similar to ice, if you have solid ice, and if you heat it, it becomes liquid like water. If you apply heat more, then you will get the steam. In a similar fashion, you can perform very controlled experiment to see the phase transition from crystalline structure to a liquid structure to a gaseous state. Like what people did in their experiments, suppose this is a solid. So we call, because of the definition of Coulomb coupling parameter, this is the gaseous state, this is the liquid state, and this is a solid state. Very relevant to the solid state physics. And one can study also the triple point of a system. Like solid BCC, FCC people have studied long ago in 2000. This medium also supports various kind of modes. The linear waves, nonlinear waves, the different structures. And interesting part is sound wave, you can always hear that. When we say sound wave, that means you can see them, you can hear them. But in this medium, you can see the sound wave by your eyes. So if you derive the fluids, taking the continuity equation, momentum equation, and the Poisson equation, and the continuity, the quasi-neutrality condition, you can end up with a dispersion relation, omega is omega square proportional to k square. And if you plot the omega versus k, you will see a linear dispersion relation for low k, high gamma, and then it shows a nonlinear dispersion relation. So there ample amount of experiments have been carried out in last 20 years to study the different wave phenomena in dusty plasma. Then in 1995, the first dust acoustic wave or sound wave that were detected by Merlino and other people. And from there, a number of experiments have been carried out to study the effect of damping, finite dust temperature, strong coupling, and other force on how this affect the propagation characteristics of sound wave. The lattice wave, similar to solid state physics, one can excite the lattice wave by applying some forces to a wire, or you can apply it by a laser force to excite this lattice wave. Another important wave is the transverse wave. In normal two-component plasma, you always need a magnetic field to have the transverse mode. But in dusty plasma long ago, in 2002, in IPS, one of my senior, he demonstrated without the magnetic field you can excite the transverse wave in a dusty plasma medium. Those transverse waves, they ride on the acoustic wave and they propagate perpendicular to the particle oscillations. And later on, we studied their dispersion relation by taking into the strong coupling and showed that this kind of wave follows the linear dispersion relation. Solitary waves, another class of nonlinear waves that is a coherent nonlinear structure that propagate a long distance without changing their identity. Even they sometimes collide with each other and retain their identity. So in 2008, we have demonstrated for the first time the existence of those kind of solitary wave in a dusty plasma medium. And later on, in IASST, they showed that those kind of nonlinear waves, they can propagate without losing their identity. Another class of nonlinear wave is the shock waves, that is defined as the sudden jump of density, potential, or velocity. And there are many experiments, people have been carried out in last 20 years, maybe these two are one of them. Mach cones, this is a special type of structures that can excite in the rusty plasma medium, like how one boat or one duck leaves these structures in a plasma, in a water medium. This is basically superposition of many linear waves and form a V-shaped structures. So these structures were excited in dusty plasma medium by putting a test charge particle through this medium and form this kind of V-shaped structures. And later on, we have also gave a model to excite similar kind of structure, how it was found in dusty plasma. The vortex structures, there are enormous amount of work have been carried out on studying the vortex structures. Manjit and the others, they have found the torus, complete torus, they rotate in a dusty plasma medium, and this is the cross-sectional view of this torus. And there are, multiple vortex structures. This is a convective patterns excited due to the temperature gradient in our lab. So you can study the vortex structure also. Dusty plasma in magnetic field. So people have, three groups in around the world. They studied the dynamics of dust particle in presence of the magnetic field. This is one that was situated in Max Planck Institute for Extraterrestrial Physics, and they have studied the dynamics, how the ion dynamics in the high magnetic field is affecting the dynamics of the dust particles. People perform the experiment in the International Space Station. They put very small device, maybe of 5 to 10 kilo of weight, and they put it in the space station. And from the ground, they give command to the astronaut to perform the experiment there. So these are some experiments where they see the length formation, the particle blob, and other experiments they did. But before putting this experimental setup, you need to test it. So how they do? They test. They put this experimental setup in the microgravity experiment. They put in a flight, and then they generate almost zero gravity or hypergravity and perform the experiment and see how the particles are acting in the microgravity experiment, where the gravity is very nominal, very insignificant. So I got a chance to fly in this parabolic flight and perform 31 into 2, 62 experiment in 2 parabolic campaign. Maybe you'll be interested to see how we do the experiment. So this is the onboard experiment where inside the flight. And this is there are many devices, from medical to the dusty plasma to other the nervous system. Many people, they do the experiment and they keep all the setup in the parabola, in the parabolic flight. And here we are doing the experiment in our own device. And for your kind information, if you have to very strong enough to get the 2G gravity. So you will see the many people, when the zero gravity attained, the people are floating like anything. And this is the 2G condition. There you cannot sustain the 2G by your own. Either you have to sleep or you have to be very strong to do the experiment. And when the 2G is over, you will come again to 0G, and the people will start floating in the 0G experiment, 0G environment. And we did many experiments like void formation, the excitation of acoustic wave, and other experiments. So I hope of time. So we are performing many experiments in IPR. Maybe you can classify it in two different sets. One is strongly coupled dusty plasma, and another is weakly coupled dusty plasma, in which, in one case, gamma is very high, more than 200 or 500, and in another case, there are gamma is very low, around 10 to 50. So there are many experiments we have already performed: the phase transition, square lattice formation, dust crystal rotation, phase coexistence, void formation, crystal cracking, Yukawa cluster in the strongly coupled regime. And another set of experiment is the convective structures that I have shown already: the sound waves, transverse waves, precursor solitons, spin solitons, the different kind of complicated structures, and the oscillatory shock structures. So as I have enough time, I'll talk about two experiments where we have done very controlled experiment on the formation of square lattice and the precursor solitons. So long ago in 1987, we showed in a very small water channel, they move one object in a supersonic velocity. That is, supersonic velocity means the velocity of that object is more than the sound velocity in that medium. They showed in the upstream direction there are very large amplitude nonlinear structures, and in the back they showed that the wake structures, that is the linear waves. They performed the experiment by simply keeping the object in rest. They moved the medium with a supersonic velocity, and they found a similar observation. Then we thought, why not to do this similar experiment in our lab? And I will tell at the end, it has a direct relevance to the space plasmas. So to perform this experiment, we have used one inverted pi-shaped device in which we have different ports for different purposes, and we produce a plasma by applying a DC voltage in between anode and cathode, and we found this is the axial and radial glow of the plasma, and when you put the particle, you can see these particles, the highly dense dust particles that are levitate near the cathode sheath. And these are the different parameters that are not reading them. So after that, we generate the flow in this medium. So what we did to generate the flow in the medium, we just generate an equilibrium dust cloud, and then we suddenly reduce the pressure. Pressure here at that point. Particles are here. So neutral comes from everywhere to drag them to its direction, and therefore a flow in the dusty plasma medium is generated. And we measure the flow by using particle velocity PIV analysis, and we found that after traveling a distance, the particle attain a constant velocity. So then we put one small object just below the medium, like how Wu et al. Did the experiment in long ago in 1987, and found that excitation of precursor soliton. What these precursor solitons are? These are the solitons that get excited in front of the supersonically moving charged object and travel faster than the object in the upstream direction. That means the cause, what creating the excitation of the nonlinear structure that propagate well ahead of the object that is also moving. So if you see this video, you will see how this precursor is getting excited. So these are the precursor soliton that is excited against the flow, and you can see very small amplitude OX structure that is exciting in the downstream direction. Then we characterize those precursor solitons by measuring their amplitude and the velocity, and we found these precursor solitons, these structures, they are really the solitons as they maintain their amplitude into each square is constant over a defined Mach number. And Wu et al. Predicted that if these are the precursor solitons, they will show some kind of behavior like this, where Ts is the time that needs to excite two precursor solitons simultaneously. And it shows the time that needs to generate the multiple solitons is inversely proportional to Nd by Nd0 whole to the power 3 by 2. And in our case, we showed that this Ts is really following this trend for alpha is equal to 3.54. The another class of nonlinear structure that we have studied by increasing the flow velocity. So that we call it as a stationary nonlinear structure that attached with the object. And we call it as a pin structure because they are like getting pinned with the object and moving with the same velocity. So theoretically, this observation have experimentally, they have predicted this kind of solitons may exist in the medium, but experimentally we don't observe it in past. So we have detected them in our dusty plasma system, and if you see those structures, they remain stationary in the near the object, and hence we are calling them as the pin structures. So these solitons, 5 minutes. These solitons are excited, and the amplitude increases with the velocities. The amplitude of soliton parabolically increases with the Mach number. However, the propagation characteristics of the wave structure, they remain as it is. So I will also tell about a recent experiment that come into physics review later, that is on the formation of the square lattice. Basically, normally we do the experiment in the RF system, where you can very easily make a nice hexagonal structure with a trigonal symmetry. But there you don't observe this kind of square lattice in RF discharge. So why we don't see the crystalline structure in the RF discharge, in a DC discharge, is that in a RF plasma, the ions who imparted their momentum to the dust particle is very nominal. So still, those dust particles can form a very nice crystalline structure. But when we consider the DC plasma, the ions which are coming into the sheath region, they impart a huge momentum to the dust particle. And hence, in a conventional parallel plate configuration, you don't see the crystalline structure. You always see a very melted, weakly coupled plasma. So we modified, from this idea, we modified the experimental setup. We use the anode very far from the dust particles, where the direct momentum transfer to the dust can be neglected. And to reduce the flux of ion to the dust particle, we use a very bigger cathode compared to the anode. And we successfully generate a crystalline structure in a DC configuration. And we found when the discharge voltage and pressure is adjusted in such a manner, we see very nice crystalline structure that we have observed earlier also. But when you play with the discharge voltage, you see that very nicely the square lattice can be found in the plasma medium, and there are many domains where you can see these black domains. These are the square lattice domain where you can see the dust particles form a very nice square lattice formation in a DC environment. And these particles, when you decrease the pressure, the few of the dust particle goes in the bottom layer and they sit on the cusp of the upper layer. And you can see the two layers. This is the top layer, and I don't see there is a particle in the bottom layer also with a less intensities. And when you decrease the voltage again, you can see that the particles, they are sitting behind one each other. That is exactly seen in the RA plasmas. So we don't see this square lattice formation in RA plasma because of this, the wake field strength in RF environment. So, to conclude, we have already demonstrated that dusty plasma can be used as a model system from soft condensed matter to fluid system to a statistical mechanics system. For you who can contribute in the recent time, so still we are very far from our goal. So a unified model of dust grain charging in plasma still remain elusive. So we need a model to be developed that work for lab, tokamak and space plasmas. This charging mechanism is still not known to us. Upcoming space mission to Jupiter, Comet, Moon, Mars, they will involve the study of charged dust grain in the solar system and need a new generation of laboratory studies to support these missions. Several groups around the world are studying the dynamics of particle in high magnetic field configuration, so required a model, theory, diagnostics tool to understand the experimental findings. Dust formation and control fusion in a major issues for plasma that I have already discussed, so we need your help to mitigate such kind of problem and resolve the challenges that we are facing in the tokamak devices. And new multi-user dusty plasma lab facility for ground and space-based research are coming up. So I request if you can get a chance, you can contribute there also. So last but not least, I am thankful to all of them who have helped me during this 20 years tenure, from Krishan, Garima, Surbi, Prashant, Ajaj, Professor Sen, Ankit, Hari, Swarnima, Saravanan, Mona Lisa, Mayank and Neha. So they have the poster and oral talk in recent times, so please try to attend them. So thank you all.
Thank you very much, Professor Bandyopadhyay, for keeping it in time and showing us how nicely dusty plasmas can be shown as the test bed of fundamental physics. So as he said that you are all invited to take this research on to the next level. So now the floor is open for the questions, please.
It was very nice talk. Sir, I want to ask few questions regarding dusty plasma because I am new with this field. Dusty particles which is hanging in the plasma, do we have seed concept around this?
Because in the plasma you don't have electric field.
Yeah.
To float them, you need to have an electric field so that it balances the gravitational force.
Okay.
So near those levitation that happens near the plasma sheath interface, where it has some electric field and the gravity that acts in the, and you have to have the sheath electric field in such a way that the resultant electric force that act in the upward direction.
Okay. Then what happens when we do these experiments in the space, in the zero
The
gravity?
space, so why I am telling that you need the electric field to balance the gravity. So if you don't have gravity, then you need not to bother about the electric field.
Okay. And one thing more, like you told that the dusty particles will behave in crystalline or the gaseous or the solid. So what governs that? Is it plasma governs that it will form these structures, or dusty particles behavior?
So basically, I told a factor that is Coulomb coupling parameter. That is the ratio of electrostatic energy to the thermal energy. The electrostatic energy mainly governed by the charge of the dust particle, and that comes from the background environment, the electron density and the electron temperature. The interparticle distance, that depends upon the confinement potential that you are applying. So you have to very precisely control these three parameters to get a either solid state or liquid state or a gaseous state.
And one more thing, that you didn't tell me about the particle dimension. What should be the dimension of
So
the
again,
dusty particles?
the particle dimension is very, closely related to the sheath electric field. You
Okay.
cannot make a very big particle so that it cannot balance the gravity.
Okay.
So, and it should not be very small so that it cannot see a electric field which is very nominal in the plasma. So what we have used in our experiment, that ranges from 1 micron to 10 micron, something like particle diameter.
Okay. Thank you.
Hello, sir.
Yeah.
Sir, I have a basic question basically. The question is like dust particles. मैं हिंदी में कर लेता हूँ तो जल्दी होगा. तो डस्ट पार्टिकल्स में जो इलेक्ट्रॉन्स उसके ऊपर बैठता है बेसिकली, तो वो तो 10,000 से लेकर 10,000 कुछ भी हो सकते हैं, राइट. लेकिन आप एक कांस्टेंट इलेक्ट्रिक फील्ड दे रहे हैं जिससे वो ग्रेविटी को बैलेंस कर रहे हैं. शायद एक डस्ट पार्टिकल के अंदर 900 चार्ज पार्टिकल्स है, एक के अंदर 10,000 है, तो दोनों का अलग अलग इलेक्ट्रिक फोर्स लगेगा. सो हाउ दे कैन बी इन ए प्लेन?
Very good question. So we are using the dust particle. Mind it, we bought the dust particle of 2 gram costing 3 lakhs. So these particles are very, equal of size. For example, if you say the particle we are using is 9 micron, 9 micron means 9 plus minus 0.05 micrometer. So these particles are very, equal size, and as the charge depends on the radius of the particle, so that is also almost equal. So, but people studied the charge fluctuation induced the waves. Because of sometimes the plasma fluctuation, the dust charge fluctuates. And that fluctuating time scale is very fast compared to what time scale we are studying. So for our experiment, we don't bother about those tiny charge fluctuations.
और सर लास्ट क्वेश्चन ये है कि जो इलेक्ट्रिक फील्ड आप दे रहे हैं नीचे से, आपका प्लाज्मा है, डस्ट भी है, राइट. तो प्लाज्मा बेसिकली इलेक्ट्रिक फील्ड को सील्ड आउट करता है. मैं मानता हूँ कि पूरा सील्ड आउट नहीं भी हो रहा है, लेकिन आप कौन सा कैलकुलेशन के बेसिस पे इलेक्ट्रिक फील्ड दे रहे हैं कि वो उस रीजन पे डस्ट को रखे ग्रेविटी के against?
Very good question, Anil. So we are not applying any electric field. We are just producing a plasma, either it is RF or DC, so that I have automatically an inherent sheath region where we have the electric field. We don't have electric field in the plasma, but we have the electric field in the sheath region, sheath plasma interface. That sheath electric field is helping me to levitate those dust particles. I am not applying any external electric field.
Okay, sir. Thank you, sir.
To him. Here.
And you have mentioned some structure like crystalline microstructure. I hope you have measured through thin film analysis tool.
No.
No? And my query is how you are studying, characterizing quantitatively how you are estimating the size of the dust in plasma. My query is laser wavelength more than 200 nanometer typically. Particle size is 4, 5, 50 nanometers, 100 nanometer. So how you are resolving the dust size? And second thing, in Wakava potential, the screen coulomb or coulomb?
This is a screen coulomb.
Okay. Okay. Thank you.
So your first question is very genuine question. So we don't characterizing the particle size. We are introducing the particle with known size and shape from the outside. But the question is, we are applying a visible laser light. That wavelength is almost in the range of the particle size. That's why the mis-scattered light, that light is getting scattered from the surface of the dust particles. And we are not bothering from this scattered light, we are not bothering about the dust dimension. We are studying their coordinate over the time, and from their coordinate, we are extracting all the information from the over the time, and that are giving me ample amount of information that is needed for our study.
A quick okay, Pintu.
Yeah.
Very nice talk. You talked about dust problem in tokamak, and there the particles are not 3 lakhs. It's much cheaper, and you want to explain through the dusty plasma that you want to solve the problem of the dust things. So how you deal with it?
And that's why I told. Suppose you have you are generating lot of X-rays during the tokamak discharge. So I am giving an example. If you put number of particles from the top of a tokamak discharge, so those particles they dilute the plasma, and they absorb the energy from the soft X-ray, so that you can minimize the soft X-rays energies and try to avoid the direct impact to the tokamak surface. So
that is not the question. I'm saying that like the dust dynamics, that like there is no kind of electric field or anything, like you are dropping a dust in and these things and they are charged up, and there is nothing to control on the things. I mean, it's basically the magnetic field and it propagates. Now you have to frame an experiment and to understand the effect of the flow of the dust without any external electric field which is given to the system, but these are the things. That is what I want, my question is.
Correct. So you have the inherent electric field in the tokamak, the radial and the
not in the tokamak, it's coming from the edge, right?
So,
from the
so
surface.
the particles are coming from the edge. Particles are not generating at the core. The particles are coming from the edge, and from the edge they are going to the core of the plasma. So if you track the coordinate of each particle, you can get the information of electric field, you can get the information of magnetic field, you can get the information of the electron temperature densities by using the simple experiment of...
So maybe there's shortage of time, we can discuss later.
Okay.
One question, sir.
Yes.
I guess we have already passed the time.
Okay, fine.
Thank you.
Upadhyay for
Thank
your
you.
wonderful talk. So now I will invite our first contributory talk speaker, Deepak Kumar from JNU, and the title of his talk is Modified Dynamics of Dust Coulomb Waves Due to Polarization Force in Gravitational Viscoelastic Fluids. So Deepak, you have 15 minutes in hand, and I will request that be in time, please. Thank you.
Hello. Yes. ठीक है. Hold. Okay. Good afternoon, everyone. I am Deepak and I am from School of Physical Sciences, JNU. And today I will present you my recent work, Modified Dynamics of Dust Coulomb Waves Due to Polarization Force in Gravitating Viscoelastic Fluid. This study is guided by Dr. Ram Prasad Prajapati, and our focus is to understanding wave dynamics in dusty plasma. So here is the outline of our presentation. I will start with a brief introduction of dusty plasma, highlighting the effect like polarization and gravitational potential, and then I will derive a model and dispersion relation. After that, we will discuss the results that we have obtained from the study, and then we will end with some remarkable conclusions. So let's start our discussion. So a dusty plasma is a complex plasma consisting of electrons, ions, neutrals, and charged dust particle. And what makes them unique is the interaction of electrostatic long-range Coulomb forces with other gravitational and other forces. And they are found naturally in comets, planetary rings, and they are also like made up in laboratory settings. The main focus of our study is dust Coulomb waves. So I will start with like what are these dust Coulomb waves. So they are the ultra low frequency electrostatic waves that arises due to the mutual interaction of dust particles among each other. They are first discovered by Rao in 1999, and they are dominant in dense dusty plasma like lunar surface sheath that we have studied in our study. So like as we all know that moon has no atmosphere and magnetic field, so and they are constantly exposed to solar radiation and UV. So due to this, the surface dust that gets charged, and that's where these dust Coulomb waves arises. That influences the charge dynamics, dust transport, and the sheath oscillation system. So the mechanism is very simple. These dust interacts with the Coulomb forces, and the wave behavior is influenced by the dust charge fluctuation, and the solar winds and UV radiation influence our wave propagation. A very like major parameter that influences these dust Coulomb waves is the fugacity parameter, and that determines the strength of dust to dust coupling, that how strongly coupled is dust. So the higher F leads to strongly coupled coupling, and that tells the transition from dispersive dust acoustic waves to the dust Coulomb waves. This is given by this parameter F. You can see like in that when F is very low, so the dust is tenuous, it behaves like gas. And when it is equivalent to 1, this is dilute, that is a viscoelastic fluid, and then it exceeds value, it becomes dense. The focuses of our study is to study the polarization force and gravitational potential. So when an external electric field distorts the Debye sheath of the dust particles, this creates a polarization force, which is a corrective force that influences the system. These can alter the amplitude and phase speed. These can stabilize or destabilize the system depending on this strength. And the other force is the gravitational force, which shows the gene's instability. It is a well-known effect. It is a classical phenomenon where internal gravity of the system overcomes the thermal pressure, and then the core collapse that creates the gene's instability. It can be modified by the polarization force, thermal effect, and viscoelasticity. So the objective of our study is to investigates the excitation of dispersion of our DCW, dust Coulomb waves, and then analyze the influence of polarization force on our system. And then we will study the viscoelastic modification to our wave dynamics, how the viscoelastic effect modifies our system. And finally, we will drive the modified Jeans instability into our system. We will begin with our study with begin our study by deriving a model. So we are using a generalized hydrodynamic model, including the known parameters like electrons and ion distribution function, dust continuity equation for dust mass conservation, and this is the momentum transfer equation which involves this viscoelastic parameter. And for the electric and gravitational potential, we are using Poisson equation. And as I said, like these dust particles are charged, so we also have to consider dust charge fluctuation. Now we have to study the dispersion relation arising from our system. So we will just do the linear perturbation analysis and Fourier transform our system to get the dispersion relation and like see how our system will behave. So after linearizing and combining equation, we get this dispersion relation, which is a very general dispersion relation which consists of dust acoustic and viscoelastic effect. Like it is very messy to understand, so we have to put some limitation to understand this. So we do study this in kinetic limit, and that gives a dispersion relation which like we can observe. So the left hand side consists of the inertial, thermal, gravitational and viscoelastic compressional effect, and the right hand side is the modified electrostatic response due to polarization and charge fluctuation. Now we will discuss these dispersion relation in an easy manner. So in the low frequency and high fugacity limit, our dispersion relation comes to this, like it is very manageable to understand. And now our conventional dust acoustic wave equation is converted to dust Coulomb wave dispersion relation. Okay, that is showing the dispersion relation for dust Coulomb waves. So we will discuss the phase speed versus wave number for varying dust fugacity, like how changing the dust fugacity will tells us about the system. So as you can see in the graph, for the low fugacity, the wave phase speed and wave number is varying. But as we increases the fugacity, the dust acoustic phase speed reduces, and as we increases the fugacity to a very high value, we can see the phase speed is got flattens. That shows the transition of dust acoustic waves to dust Coulomb waves. So this shows that at higher fugacity, strong coupling occurs, and which is the signature of like strong coupling plasma. Now the effect of polarization for parameter on DCWs. So we have fixed the value of our fugacity to 10, and then we discuss how changing polarization parameter shows us the phase speed of our DCW. So as we increases the polarization parameter, we can see the significant reduction in the phase speed of DCW, and this separation is more pronounced as higher wave number, and this shows the destabilizing nature of the polarization force, which weakens the dense plasma. Which weakens wave propagation in dense plasma. It is describing that the now wave motion is getting slower as we increases the polarization forces. And now we will discuss the other force, that is gravitational force. So due to which Jeans instability is happening. So from our previous equation, we can introduce the Jeans instability criteria, which will show our critical wave number, below which the wave is unstable and it will collapse, but above which that critical value, the wave is stable and it will like oscillate. Now we will discuss the effect of compressional speed, like how viscoelasticity change the Jeans instability. So as we increases the VC, we can see the growth rate is reducing. So this shows the at higher wave numbers, like gravitational instability is getting suppressed. So this shows that viscoelasticity plays stabilizing nature for Jeans instability. And the other effect that we have described, that if we changes the polarization parameter and then we plotted the growth rate, so when we increases the polarization parameter, we see that the growth rate is increasing, not decreasing. So this shows that the polarization has destabilizing nature to Jeans instability. And so we will like the conclusion is this. So DCWs, we have analyzed the DCWs under the strong coupling incorporating polarization forces, viscoelasticity and gravitational effect. We have described the fugacity parameter, which tells us the transition from dust acoustic waves to dust Coulomb waves. And then we like polarization lowers the phase speeds and can destabilize wave modes in dense dusty environment. And the viscoelasticity and thermal effect act as stabilizer, reducing the growth rate of Jeans instability. And our modified dispersion and instability criteria provide insight into wave behavior on the lunar surface and dusty astrophysical system. These are the reference for our study, and as you can see, the last one, this same problem has been recently published. Thank you. Thank you for your attention.
Thank you very much, Deepak. You kept it well in time. A very nice talk. So now floor is open for questions, please.
So my question is, how can you increase the coupling strength? Because for a plasma parameter, the particle size is constant, dust particle size. So how can I increase the coupling strength?
Like this coupling strength, the fugacity parameter tells like how dense the plasma system is. So the like surfaces like lunar, which has like high dust number density. So and due to dust charge fluctuation, like they get closely packed and that becomes strongly coupled.
So you interparticle distance, are you telling?
Like interparticle distance are not a concern here. We are talking about like high density plasma. So the number density of plasma is very high there at that surface.
Okay, ठीक है.
May I?
Yes.
May I? So in continuation of his question,
Okay, sir.
why do you need another parameter? We used to know that gamma is strongly coupled or weakly coupled.
Yes, sir.
So why you need another parameter for your, to define the strong coupling or weak coupling?
Okay, sir. Like there are two types of screening that we have studied so far. Like there is a Debye screening and other is the Coulomb screening. So for the like that Coulomb coupling parameter also shows about like strongly coupled plasma.
But that coupling you can include in the potential, either it is Debye or Debye-Huckel, or so
yes,
you don't need another parameter to.
Sir, that parameter like gamma is the ratio of electrostatic to the thermal energy, but the parameter that we have used is like solely depend on the dust density number. Like higher the dust density number, then it will begin to like strongly couple.
But in your gamma,
yes,
the density is also involved in terms of interparticle distance. Higher the density, lower the interparticle distance, and hence the higher the Coulomb coupling parameter.
Yes, sir.
So just pay some attention on it.
Yes,
And
sir.
second question is how the normal dust acoustic wave differs from the dust Coulomb waves?
Okay, sir. So normal dust acoustic wave, as like you have already presented here, so they are dispersive in nature, like they are like acoustic waves. But these dust Coulomb waves are densely packed dust waves, so they are very slow. They are like closely packed, and they are like very slow, and they are slowly moving waves. Like we cannot say that they are all actually
But
moving.
still
or
they are the acoustic wave. They are propagating along the direction of the oscillation.
Yes, they are produced due to the dust charge fluctuation. That's why we are calling them Coulomb waves.
One quick question. What is the physical origin of this polarization force?
Physical origin. So there are like, as I have knowledge, these are just like a theoretical study of Coulomb waves. So not so far like I know about physical. Okay, so this polarization force. So like as I said, lunar surface is exposed to solar radiation. So due to that, the external electric field, the surface dust get charged by like a non-uniform electric field, and due to which the polarization like occurs into that system, that create the polarization force.
Dusty plasma here.
Oh, yes.
Is it quasi-neutral?
Yes, it's quasi-neutral.
So in that way, like in the dust region, so you have less number of electron density.
Sorry, sir.
Less electron density.
Yes.
And so what about the Debye length? How do you calculate?
Sir, in dusty plasma, like we consider only dusty collective model. We don't study. We don't like focuses on electrons or ion.
And what about the plasma above the dust cloud?
Plasma above.
So it seems that the dust particles all settled above the gravity, there where the electric field is saturated. So don't you have that, like there is a quasi-neutral plasma on the top playing some role?
Sir, this is quasi-neutral, but like we are studying how external electric field will like change the motion of that dust system. We are not like charging, or like we are not charging the dust. We are not considering the charging, but we are like considering how external electric field will modifies the system dynamics.
Any other questions? Okay, if there are no other questions, let's thank the speaker. Thank you very much,
Okay,
Deepak.
thank you.
So our next speaker is Mr. Sachin Sharma from IIT Jammu, and he will be talking on dust shock bending around a dust void. Sorry, I changed the topic a bit on the fly because I knew that we evolved a bit.
Okay, fine. Okay, hello. I am Sachin Sharma from IIT Jammu. So today I will present my work on dust shock bending around a soft dust void. So by soft dust void, I mean the void is acting as is not acting as a rigid obstacle. Rather, it is acting as a compressible, soft compressible obstacle. So in this study, we have studied the interaction of two nonlinear structures here. So one is a shock wave and the other one is a dust void. So first I will just give a basic introduction about dusty plasmas. So we know plasma is a collection of charged particles like electrons, ions, and there are neutral atoms also. So one of the way to create dusty plasma or plasma in a system is by DC discharge. So we can have two plates, one is positively charged, the other is negatively charged, and then we provide enough discharge potential between them so that the gas gets ionized and we can create a plasma inside. So when we insert some dust particle inside this plasma, the dust particle gets negatively charged due to high mobility of electrons than ions. And now this charged particle feels sheath electric field in upward direction, and there is always gravity in downward direction. Due to balance of these forces, the dust particle starts levitating in this plasma. You can see here also. So now these dust particles levitating in plasma region, we call it as a dusty plasma medium. So this dusty plasma medium can be studied and used as experimental test bed to study various dynamics. Now, one of the important things about this dusty plasma is that dust dynamic happening, any dynamic happening in this dusty plasma happens at dust length and time scales. That is, the length of, if there is any wave propagation, then that will propagate at the scales like from few micrometers, millimeters to centimeter, and then the time scale, the frequency will be of 10 hertz to hundreds of hertz. And these particles can be easily tracked by using standard cameras, which makes it an easily accessible, and they can be further made in one-dimensional chain of dust particles, two-dimensional layer of the dusty plasma, and they can be produced in 3D dust cloud. So with all these properties, they can form in a plasma crystal state, that is a solid state. They can be created in a liquid state where we can study waves and vortices, and then they can also form in gaseous phase too. So a single plasma system, dusty plasma system, can form in all the different n-dimensional system and in different phases of matter, and that from collective bulk dynamics to individual particle level, so that we can study even the kinetic level information of dynamics. So that is why we use this medium to study the nonlinear and linear fundamental properties in our case. So for that, we performed experiment in our lab. So we used this Shivalik plasma device. So this is a cylindrical glass device. So it has two electrodes. This one is anode and this one is cathode. So anode is positively charged and cathode is grounded, and the whole chamber is actually floating. So we put dust particles in this cathode, and we see a dust cloud formation in our system. So there is one unique property of this device is the dust cloud is formed in this diffused plasma region rather than above these electrodes. In this region, which is the source electrode region, here the plasma density is 10 raised to power 14 to 15 per meter cube. But in here, where the diffuse plasma is formed, here the plasma density is 2 orders lower than in between the electrodes. So here it is 10 raised to power 13 to 10 raised to power 14 per meter cube, and here it is 2 orders higher in the center. So what happens is, in our case, there is a large void formation over this electrode, which pushes these particles and don't let them form in between the electrodes. And these particles get thrown in this glass chamber, and then they form the dust particles in this glass plasma sheath electric field. So now to study wave in our system, nonlinear interactions, so we used two configurations, two important things, then that is a high discharge voltage and a large anode than a cathode. So in our previous experiments, we have learned that if we want to excite a wave, we need a high ion streaming in our case. So for that, if we keep on increasing our discharge voltage, there is an increase in ion streaming in our experiments. And also, if we use a larger anode than a cathode, then ion streaming is significantly higher in our case. So we use this information to excite a wave in our system, which and a dust void in our case. So these are the experimental parameters. We used a DC discharge setup, and the gas used is argon. We worked in a pressure of 0.12 millibar, and we used a very high discharge voltage of around 700 volts. And the particles used are monodispersive MF particles of size 8 micrometer. And then a 3D dust cloud is getting formed, and we imagined this, visualized this cloud by putting a laser of 532 nanometer and captured it in a camera. So after that, when we reached that discharge voltage, we can see a dust wave getting propagated around a void. If you can see this video, video is 100 times slowed down for visualization. I will play it again. So you can see a planar wave is getting formed, and this gets getting bent around a dust void. So first I wanted to characterize this wave. What is the type of this acoustic wave? For that, I have done some characterization. So the dust charge come out to be 13,000 electron charge, and then dust density is around 10⁻10 per meter cube. So I calculated the sound speed, and it came to be 1.6 centimeter per second. And when I measured the speed of this wave, it came to be around 16 to 10 centimeter per second, which is way higher than the acoustic speed in this dusty plasma medium, and so that it has a high Mach number of 6 to 10. So from there, we get an information that these are actually very highly supersonic waves, that they are shock waves. To further see into it, we have done a spatio-temporal evolution of these waves. So what we have done is, we took a small rectangular region here in this direction and took the spatial profile in this direction. So we took the average in this y direction, and then looked into the spatial temporal profile after every frame. So from there we can see there is a very high amplitude wave that is traveling towards a void region, and then it is interacting with it. So these are high amplitude supersonic waves that we are observing in our systems. So then I looked into the amplitude and width of this wave. So this is the amplitude profile in spatio-temporal profile of wavefront, and from here also you can see the amplitude is almost constant after some time, and then the width is little increasing. That is also shown in this graph, that width keeps on increasing and the amplitude becomes almost constant after some time. And the amplitude into width scale, it is not constant, and that is why we know that it is not a soliton, rather a shock wave. So then we will again look into the frame by frame interaction of this wave. So from here you can see that this is a planar wave, and when it keeps on propagating and it interacts with the dust void, it compresses the dust void, and the wave is also getting bent from here inwards. So it keeps on bending from the center, while the sideways wavefronts, they will keep on propagating with the same velocity without any effect. So it keeps on bending until it reaches the central void region, where it loses its properties and it collapses actually, and then it particle trapping like thing is happening, where the energy of wave is getting transferred to the particles and then it is getting trapped. So after that, I looked into the wavefront profile in 2D plane, and from this profile I came to know that the velocity, the speed of this wave was earlier 16 centimeter per second, and when it just starts interacting with it, its speed decreases to 10 centimeter per second, but from the side fronts it is almost approximately the same. So from here I got two information, that it is the central void is bending the void is bending the central region of this wavefront, and the sideways is not getting affected, and also there is decrease in the velocity of the speed of this shock wave. So to further verify, we have performed molecular dynamics simulation in our system. So we tried to keep the parameters same. So we have took the similar dust charge of 13,000 and same dust mass and density. And then we gave a shock wave of Mach number around 5 with similar gamma and kappa values. And when we just propagated it to shock, we were able to see a bending of this wave around this void. So this is this frame by frame picturization of that structure. You can see here the planar wavefront, and then it is getting bending around the shock, around the dust void. So further, apart from it, when we further realize some things, we observe that there is a bow shock formation in our case also, in this case also, and there is dust heap and dust void formation in our dusty plasma systems. So dust heap is a high density regions where dust particles are very high, but it is a very temporary region for only for one frame or two frames. And then there is a two polar region formation also, where two polarities are occurring at the same time, like two voids formation at the similar time and two heap formation at the similar time in our case. So I will conclude here. So in our experiments, we have looked into the bending of our shock wave when it passes through soft compressible void, and then this wave later collapses and forms the transient trapping of dust particles, and there is a complex formation of these dust heap pairs and dust void pairs and bow shock formation in our experiments. So I will thank my co-authors for helping me in this work, and I will thank all of you and the organizers for hearing me. Thank you very much. Yeah.
Thank you very much, Sachin. So now the floor is open for the questions, please.
Hello. Sachin, thank you for your nice talk. I have two doubts.
Okay.
So how did you calculate the dust charge? You told it is around 2,300 or something.
13,000.
13,000.
Yeah. So the dust charge is calculated in the region where the dust void and dust shock are not. It is in the almost equilibrated region where the perturbation is not in the system. So that is the where all parameters are calculated for the dust.
How did you estimate that?
So I took the small that region and I tracked the dust particles there, and from there I looked into the velocity distribution, and from there I calculated the dust temperature. And for charge, I used the orbital motion limited method. So I have a particle size of 8 micrometer, and then measured the electron temperature, and from there I got.
Why I asked this question?
Yeah.
So this orbital motion limited is really limited.
Yeah,
so when you have so much of dust, the electron that depleted mostly on the dust surface. So the point is whether with the so much of dust density you can use this orbital motion limited theory or not.
So right now I think I am not sure about any other way to precisely calculate this dust charge rather than this.
You have to look into that. There are ways.
I will look if there is any other way better than this one. Yeah.
Did you calculate the interparticle distance for this heavily dense dust particles?
Yes, I calculated same way. I looked into the small region where
what it is?
So it is around 140 micrometer.
140 micrometer.
Yeah.
Okay, thank you.
Oh, thank you, sir.
Any other question? Okay, if there are no questions, then thank you very much, Sachin, for a nice talk.
Welcome.
So the next speaker is Monalisha Sahu from Institute for Plasma Research, and she will be talking about structural transitions in a RF-driven dusty plasma. So Monalisha, you have 15 minutes.
Good afternoon all. This is Monalisha from IPR. First of all, I would like to thank PSSI for giving me this opportunity to present this work's titled Structural Transitions in a RF-Driven Dusty Plasma in the Plasma Scholars Colloquium 2025. So, Dr. Bandyopadhyay has given a very brief introduction to dusty plasma, so we'll not go in depth, but we'll start with a very short introduction. Dusty plasmas are the plasma containing charged species like electrons, ion, along with neutrals and dust particles of size ranging from few micrometer to few nanometer submerged in it. These dust particles in typical laboratory plasmas get negatively charged by collecting more number of electrons than that of the ions, and levitates near the plasma sheath boundary, being balanced by the forces due to the gravity and the sheath electric force. The time scale of these plasmas are slower than the conventional plasma species. So these are slower than the conventional plasma species but faster than the colloids. So using a simple imaging system, one can study their dynamics. Through this animation, we can see it's not working. I have connected it. Yes.
Just allow there.
Wait, okay. Yes, it's fine. Thank you. So, through this animation, we can see the generation of plasma and the dust particle levitation near the plasma sheath boundary, being balanced by the downward gravitational force and the upward sheath electric force. Dusty plasmas, a playground for classical states of matter, mainly governed by two parameters. One is the coupling parameter gamma, and another one is the screening parameter kappa. So the coupling parameter gamma is basically the ratio of the potential energy of the dust particle to the kinetic energy of the dust particles, depending upon the dust charge, dust d by length, average interparticle separation, and the dust temperature. So by altering this gamma, one can study the phase transition in dusty plasmas. We can see in the first video shows the dusty plasma in its gaseous state, where the gamma effective value is very, very less than 1, though it's showing the dominance of the kinetic energy over the potential energy. And the second one is showing the liquid state, where the gamma value is lying between 1 to 171. And the last one is showing the solid state, where the gamma effective value is exceeding 171. So dusty plasmas are known to produce ordered structures. So it is not wrong to say that the last figure is showing the crystalline state of dusty plasmas. So therefore, dusty plasmas provide an excellent medium to study the phase transitions. Talking about the structural transitions, in past, people have studied by changing the number of particles, by changing the array power, by applying magnetic field, by changing the pressure. But there is no evidence that this structural transition is happening due to this change of this specific parameter, or there is the alteration of the background plasma parameter. So to investigate this, we have a question whether one can study the structural transition without altering the plasma parameters. To investigate this, we have performed the experiment in the capacitively coupled dusty plasma experimental device, also known as the CCDPX device. The device contains a cylindrical chamber containing 2 electrodes, and there are several circular and square ports for various diagnostic purposes. And the imaging system contains a line laser, 2 fast imaging cameras to capture the top view and side view pictures. And plasma is generated from a RF signal of 13.56 megahertz in a push-pull configuration mode. And dusty plasma is created with monodispersive melamine formaldehyde dust particles of size 7.43 micrometer with a dispersion of 0.05%. The unique feature of this device is the configuration of the lower electrode. The lower electrode is designed in such a way that there will be a channel formed between these 2 electrodes. The circularly shaped electrode is divided into 2 parts. The one D-shaped part is kept fixed and the another part is kept movable. So using a servo motor and a microcontroller, through this electrode positioning control unit, we are able to make a channel of width ranging from 0 to 7.8 mm. So here is an animation to understand the problem. In the first figure, when there is no gap or no channel formation in the lower electrode, and when we are forming the dusty plasma, we are seeing that the hexagonality structure is maintained. But can we see the structural transition by changing the channel width? Here is a channel width formed with a width of D. So we have estimated the charge and dusty wire length to ensure whether we are changing the plasma parameters in the background, because our goal was to study the structural transition without altering the plasma parameters. So to check whether the charge and dusty wire length are changing with the change in the channel width, we have performed this experiment where with increasing the number of dust particles from 2 to 12, we are seeing the compression in the dust array. So one can visualize the S0 and RM through this picture. S0 is basically the distance of separation between the dust particles at the center of the array, and RM is the total half length of the dust array. So the experimental data obtained from the are fitted to the 1D equation of state developed by Hebner et al. Given by this expression, and these are fitted to the experimental data. So one can get the charge found to be 10 to the power 4 order, and lambda is nearly 251 micrometer for a given plasma discharge condition. And this method we have taken because this is not relying upon any plasma parameter, so there is a minimum uncertainty in the values. And the next figure shows the variation of charge and lambda d with the variation of the channel width. So there is no significant change in the charge and lambda d values when we are changing the channel width. So to the question whether this geometric effect, that means when we are changing the channel width, does it alter the background plasma parameter? The answer is no. The next thing is, can we study the structural transition with this geometric effect? So these are the experimental observations These are the top views, and these are the side views, where when the channel width is at 0.5 mm, we are seeing that there is a nice circular 2D crystal is formed. And when we are gradually increasing the value of D from 0.5 to 1.38 and then 7.8 mm, we are seeing that the structural 2D circular crystal is changing to an ellipse, and then to a quasi 1D structure, and then to a nice 1D chain. And the side views are ensuring the monolayer formation of the dust particles, because the monodispersive melamine formaldehyde dust particles will be levitating in a same plane. So there are no particles up and below the crystal formation. Also, one can observe that the levitation height is gradually decreasing when we are increasing the channel width. That means the channel width is basically forming a potential trap where these dust particles are falling on this trap. And another thing is the interparticle separation is gradually decreasing. One can observe in the top view the interparticle separation in this figure, and the interparticle separation where 7.8 mm of channel width is there, the interparticle separation is gradually decreasing. So we have obtained few of the results, including the variation of interparticle separation with this channel width, variation of dust temperature, variation of coupling parameter. So in the first case, when there is minimum separation or nearly zero separation, we are seeing that the dust particles are loosely packed. So their motion is random, and they are at a maximum distance of separation than compared to the channel width formation at 7.8 mm. Indicating a tight packing of the dust particles. And in the second case, the variation of dust temperature, it is also seen that the dust temperature is gradually decreasing when we are increasing the channel width. That means when there is zero separation, the dust particles are free to move. But when there is a channel formation, these dust particles are restricted by the trapping potential, so the motion is being restricted. So from the velocity distribution profile, one can obtain the dust temperature, and it is found that it is gradually decreasing. Now, for the variation of the coupling parameter with the channel width, previously we have seen that gamma was depending upon Q, lambda D, A, and TD. So in our case, the charge and dust debye length are not very much, so we are keeping it as constant, and only depending upon A and TD, which are inversely proportional to the gamma effective. The gamma effective value is gradually increasing, showing a higher crystalline state. Then variation of levitation height, also from the experimental observation, it was seen due to the increasing in the potential trap, the levitation height was gradually decreasing. So leading to a levitation height decrease with the increase in the channel width. Next one is the variation of ellipticity. So every structure formed from the experimental data were fitted to an ellipse, and the ellipticity is found from the formula E is equal to 1 minus B by A, where B and A are the semi-minor axis and semi-major axis of an ellipse. So it is seen that at minimum separation or zero separation, this is forming a crystalline, circular crystal, and then going to a 1D crystalline structure having an ellipticity value 1. So this is evident that there is a structural transition happening from a circle to ellipse, then to a quasi 1D structure, and then to a 1D chain. Now to validate this, we have performed a molecular dynamic simulation for 12 number of dust particles by taking the trapping potential to be phi is equal to x square plus alpha y square, where alpha is the trapping potential, and from this picture one can see when alpha is equal to 1, from the trapping potential one can calculate the electric field. So the electric field will be Ex is equal to Ey at alpha is equal to 1. So this can be given by this red circular red circle showing the isotropic nature of the dust particles. Then when we are decreasing the value, let us say for the blue one, for alpha value to be 0.5, we are seeing that it is getting compressed in one direction. So for alpha is equal to 0.05, also again it is more compressing. That means when we are decreasing the value of alpha, the anisotropy in the system is increasing. And this system in the molecular dynamics simulation is taken such that there will be inward force will be coming from the potential trap, and there will be outward Coulombic force due to the dust particles. So one can study the structural transition using this system in the molecular dynamics simulation. And also one can study the bond order parameter psi 6, which is the measure of the hexagonal structure symmetry in the crystal. This is the verification of the order parameter variation with molecular dynamics simulation. The left side plot is showing the experimental observation, and the right one is showing the molecular dynamics simulation result. So in the first few observations, it is seen that there is no sign of the bond order formation. That means there is no sign of the psi 6. But when we are going from 1D to 2D structure, the psi 6 value is gradually increasing. And this is also verified with the molecular dynamics simulation result. When we are increasing the value of alpha and going from anisotropy to a isotropic medium, we are able to generate this psi 6 with increasing number. And we can see for alpha is equal to 1, we are getting a nice circular crystal, and for alpha is equal to 0.5, we are getting an ellipse. So to check whether in our system we have the same asymmetric, by changing the potential trap, we are getting the asymmetric or not, we have performed another experiment to validate this, the MEC probe experiment, to see what is really happening when we are changing the channel width. So this is an animation how we are dealing with the MEC probe profile. So we have made, sorry, yes sir. We have made the moment of this MEC probe across the channel in order to find the potential along with the electric field profiles. This is given by this plot. When D is at 0 mm, we are seeing that it is basically flat. There is no potential trap. And when we are increasing the value of the channel width, we are seeing the channel width is basically increasing. That means there is evidence that it is forming a potential well. And this green lines are showing the electric field profile. Basically, as previously we had discussed in the molecular dynamics simulation result, the anisotropy given by the electric field, we can see it is gradually increasing with the increasing in the channel width. Basically, this anisotropy is leading to the structural transition by changing the potential trap. In conclusion, the structural transition from a circular 2D crystal to an ellipse, then to 1D, quasi-1D structures, to a 1D chain is obtained. Various parameters like average interparticle separation, dust temperature, ellipticity, levitation height, effective coupling parameter are studied for a range of channel widths. The variation of order parameter are studied for different structures and compared with molecular dynamics simulation. This structural transition is due to the pure geometric effect. As there is no alteration of the charge and dy length, we are claiming that our background plasma parameter is not changing. So to validate this, potential profile measurement are done using an MEC probe. This is the end. I would like to acknowledge my guide, Dr. Pintu Bandyopadhyay, my senior, Dr. Ankit Dhaka, Dr. Dinesh Rathod, Prashant Amat, Mayank and Neha, and our team leader, Professor Abhijit Sen. Thank you for your attention. If you have any questions, you can ask.
Thank you.
Questions, please.
Mona, very good talk with captivating animation pictures. Also, I could able to get some pictures.
Thank you.
Basically, this dusty plasmos is an unexplored area for me, and I could get a lot of nice ideas in the talk. My primary question is, now you talk about levitating the particles, and then you also measure the height by varying a lot of parameters, and you also try to study the uniformity, the arrangement of particles, how they are arranged and things like that. Now, what do you achieve basically by levitating these particles, and what is achieved by arranging these particles in a certain manner? Why I'm curious to know this is, like in a normal plasma, like suppose we are using it for depositing the particles in a certain films, they call thin film deposition. Now, by adding these dusty particles, are they improving the application of a normal plasma in a certain way? What is the speciality? What is something beautiful about adding dusty particle in improving any application that has already been done by the existing plasma? That is one question. And my second question is, I'm just curious, I'm really wondering how this is happening, because you evacuate the chamber and then after a certain base pressure is reached, you pass the gas and then you reach at a certain working pressure. And at what instant you are introducing the particles inside the system? I'm really curious to know, because how they are being introduced. Are they introduced along with the gas, or it is already there in the chamber? And what is how often you introduce it? These are some primary questions. Yes.
Thank you for your question. To answer your first question, actually we are studying the fundamental physics. I think you missed the Professor Bandyopadhyay's.
No, I was there. I was there, but due to the short of time,
yes, for the how structure formation is occurring in dusty plasma, that comes with the basic plasma physics. Sorry, basic physics. And for your second question, we have a dust dispenser that is connected in the chamber. So after forming plasma, we shake the dust dispenser. From there, we add the dust particles to the plasma environment to make dusty plasma. So it is not there before.
Okay, it is inside the chamber and it keeps pumping inside the chamber regular intervals.
No. Let me clarify.
Okay.
The same process you are following for the plasma generation.
Okay.
It is all same.
Okay.
But another circular port is there where we have connected the dust dispenser containing dust.
All right.
So after generating this plasma, we are shaking the dust dispenser and adding dust particles to the plasma environment to form dusty plasma.
Okay. So there is a pumping mechanism, that is rotary pump or whatever pump through which the gas is pumped out. Along with that, the particles also pumped out.
Actually, we want these particles to stay so that we can study dusty plasma, right?
All right. Okay.
Maybe we can discuss it later.
Thank you.
Another question?
Yeah, I have a question. Nice talk. Thank you. But I'm surprised to see the results, because if you separate out the electrodes, so it will behave like two electrodes. Simple, because the plasma is there, so it will shield all the electric field in between the two electrodes. So there should not be, and the dust should fall between them. So I don't know what's happening and why you are talking about all these electric fields.
Very nice question, sir. Actually, maybe there is a mistake in my animation. Actually, these two, the electrode at the present at the lower part is connected, and to both of this D-shaped electrode, 13.56 megahertz of signal is going, and only we are opening a part of it. So the sheath is actually overlapping for when we are having a zero separation. But when we are having a separation between them, the sheath is making a potential trap for them.
Okay. Okay, thank you. We'll discuss
Thank you.
more.
Okay, if there are no questions, let's thank the speaker. Thank you very much.
Thank you.
That's a wonderful talk. Okay, so our next speaker is Justin Rezi from VIT Vellore. Yeah, and he will be talking about generalized non-ideal treatment and growth rates analysis of drift wave instabilities in a collisional dipole magnetized dusty plasma. Mona Lisa. So Justin, you will have 15 minutes. Okay, thank you.
Hello, hello. Oh. Yeah. So good afternoon, everyone. My name is Justin Reggie, and I'm coming from VIT Vellore. And my guide is Dr. Anujram Baitya. And I'm trying to study about the non-ideal treatment and growth rate for drift wave instabilities in a dipole confined magnetized dusty plasma by varying the dust grain and the dust density, like how to study the instabilities which is causing by them. So my plan of talk is that just go through the background and motivation, mathematical modeling, MATLAB implementations and the results, and concluding with the conclusions. So going to the motivation, actually studying the growth rate and the plasma instabilities with the dust grain variations and the dust density in a dipolar magnetic field configurations. So why we are using the dipole configurations? Throughout the literature, we can see that we are using the linear magnetic field everywhere to reduce the drift wave, drift curvatures in the field. So, I am curious, how we can try to study the inside the curved magnetic fields and how the dust grains and the dynamics will behave inside the plasma and how the instabilities will occur. So we can say that dipolar field is basic and simple magnetic field configurations that is existing in the universe, help for the natural confinement, and we can study many properties like confinement properties, transport instabilities, fluctuations, and everything. And a lot of fundamental research is being still have done, but for example, for density, temperature, EDF, electron density distribution function, particle diffusion, particle balance, ballooning effects, and dust charge particles has to be further studied. So our work focus on the numerical method to investigate the nature of dusty plasma by solving the governing plasma equations and dispersion function by Paradise approximations, rather than the derivative method. To understand the collective behavior and the plasma wave instabilities. So mathematical modeling, we are going to start with the cosinodal equations, perturbing the cosinodal equations, and charge dust is there. Then we are using the continuity equations and momentum equations, perturbing them, and we are getting the perturbed equations, and we are adding extra terms called in terms of collisional frequencies, nu s. And using the Poisson's equation, we are getting the and combine these every equations, we are getting the perturbed density equations and perturbed velocities, which we can further introduce into the replacement of the cosinodal equations, and adding the damping effects due to the charging of dust. We are trying to study that how the plasma will behave if we are charging per time. So how they can vary with the charging of dust. Then the collision velocities also we are considering in the momentum equations. So we are going to start with the dielectric functions, where the basic dielectric function is having 1 plus that one W term is there. That's called plasma dispersion functions. Inside the plasma dispersion function, we are having the function of thermal velocity and everything. So how to solve this plasma dispersion function? We are having some kind of higher integrals. So we are, it's like a function of phase velocities. But thing is that solving integral equations is okay, but solving them with the accuracy, when we are considering additional terms, is like somewhat difficult. So we can approximate by using the pad approximation. So what is pad approximation? Pad approximation is like a polynomial approximations. And we are, as per the literature suggesting, we can go up to the fourth order of pad approximation, or like polynomial, the ratio of polynomial equations is called pad approximations, and applying them to derive the plasma dispersion functions, where a plasma dispersion function is having a W term, we are considering the effective collision. So inside the effective collision, we have gamma collision and gamma lambda. It's like additional collision terms and the lambda damping which we are considering, try to understand. So to study, or we can expand, so right now we are getting some kind of summation terms instead of the integral term, and trying to simplify it more further by using the series expansions shown in the figure shown here. So after doing everything, like we are getting some kind of summation to some kind of final results, where we are having the plasma dispersion functions, collisional terms, lambda damping terms, and everything. So going to numerical solutions, we are having two terms called real frequency and the growth rate omega I. Like we are having functions of where omega is a function of cyclotrons, frequency, wave vectors, and dispersion functions. Same as our growth rate, we are having considering the function of effective collisions and everything. So we are getting some kind of two relations, numerical relations for real frequency and the growth rate. But even though while doing the calculations, we can say that some terms are going to be like negative terms, or like we are not getting the real value. So we have to optimize that growth rates by adding some multiplying with other factors. For the optimizing factors, we can say ky factor and rd factor, the radius factor and the vector factor, so that it may come towards our within our values. So we are trying to, so what we are trying to expect is that the lambda damping absorbs the wave energy. So what do you mean lambda damping is like say like phenomena where instead of collisional heating, the wave and particles exchange their energy with each other. So by the way of resonance. So the thing is that it absorbs the wave energy due to resonance, and second factor is that collisional damping, it may also have weakening the wave growth due to the, we have considering the frictional term and the neutral to electron collision terms. So it's like mathematical implementation, like only the main steps I just mentioned here, like we're having collisional parameter, different collisional parameters, then dipole magnetic field parameters, and omega I, E, and dust omegas, dispersion relations, and the functional of pad approximations using the Bessel functions, because we are considering the kind of spherical or cylindrical geometry, so we should be going with the Bessel functions and the expansions, and same as like collision terms and lambda damping terms, solving the we are getting the dispersion relation and substituting this everyday value into these codes, we are going to get the results. Thing is that what we are going to see in the result is that we can see that our real frequency versus the wave vector, where we are going to increase the dust radius from 2.5 micrometer to 3.5 micrometer with a step size of 0.2 micrometer. So what we are expecting is that, okay, with the increase of dust radius, the frequency is getting reduced. So we can say that real frequency actually should be increasing, but it's not linearly varying, showing some kind of non-linear variations, maybe due to some kind of additional collisions or non-ideal nature which we are considering in the mathematical modeling. And the larger grains has higher mass. Higher mass means the lower the charge to mass ratio. That means reducing the omega d or cyclotron frequency, coupling strength will be reduced. So a larger dust means like propagates with the lower frequencies. So we can say that real frequency will be reducing with the the radius of the dust. Going to the growth rate terms, we can say that, okay, there are three main things we can see that at the lower ky or wave vector, moderate ky and high ky. The lower ky, we can see that higher growth rates or like peaks at small ky, maybe due to the wave particle interactions leading to strong instabilities, and plasma waves can extract from the cyclotron motions which the dust particle is having. So dust to wave energy is happening, change is happening. Then at the moderate ky, we can see that dips to a point where we can see that till here. From peak to here, we can see that decreases and going to increase further. Like thing is that lambda damming means there is no direct collisions. So we can say that the energy from wave to particle can transfer up to a point, and it can reverse back from particle to wave can be also. So energy transfer can be both, can be a kind of oscillating way. Both ways it can travel or it can exchange. And finally, after 1 ky, at a higher wave vector, we can say that, okay, the collisional effects dominates and the growth rates are going to getting normalized, or we can say the instability is getting reduced. So thing is that by increasing the like from going to the lower ky to higher ky, peaks, moderates and going to stabilize. And comparing the radius of the dust, we can say that higher dust, lower dust radius means higher the instability, and lower dust means lower dust means the higher instability, higher the grain radius means lower the instabilities. So increasing the grain radius, the instability is getting reduced. Then comparing with the dust density, so we can say that omega r is going to increase with the increase in ky, because as per mentioned in the previous, it's going to increase. And comparing the dust density, we can say that, okay, increasing the density, more shielding is there, that means lesser will be the frequency. So increasing density, the real frequency will be getting reduced. And the growth rate, like density is varying from 10 to the power 15 meter per cube to the 10 to the power 17 meter per cube. And like growth rate, the negative growth rate means still the wave is in the stable propagation. Negative growth rate means still in the wave is in the stable propagation. So lesser the density, we are having a higher stable wave propagations. And when we are going to increase the density, number density of the dust, we can say that, okay, the instability is getting increased, or like higher damping is happening. So that means at higher densities introduces the more collisional scattering, reducing the effectiveness of lambda damming, leads to the less negative growth rate. But thing is that still the wave is more stable, but growth rate is having higher stability in the lesser density as compared to the higher densities. So conclusion is that our study tried to analyze in terms of magnetized dusty, especially the curved dipole magnetic field, by introducing the effects of collisions, charge fluctuations, lambda damming, and in terms of dust grain radius and the dust densities. And numerical solutions reveal that frequency is increasing with the wave vector. That means the typical drift wave or typical drift wave behavior is shown in the here. So growth rate, we can see that peaks, then more dips and stabilizes after a particular wave vector. That means stabilizing effect of dust. So plasma is getting stabilized by having the variation in the dusts. Yes. So I'm looking for the opportunity to implement this theoretical study into experimental by possible collaborations, if I'm open to kind of. So thank you. And
thank you very much, Justin. You kept the time very nicely. So now the floor is open for questions, please.
So what is the source of your What is the source of your drift instability? Matlab, where it is getting the free energy?
Sorry?
Where it is the getting the free energy? Matlab, either it is some density gradient or something like that.
Free energy.
Yes, matlab, to have some instability, you need to have some free energy source like the density gradient or the temperature gradient. So in your case, what is your source of free energy?
It's like dust will be having cyclotron velocities, frequencies. So the particle to wave interactions and collisions is the reason for this kind of instabilities which we are studying kind of.
Did you estimate some the profiles of the density of the plasma?
No, like we are just trying to understand how this thing is working theoretically. Till now we don't have any typical values for that. We just seeing how the radiation, like variation is happening within the plasma wave with the effect of the density gradients and the radius and the densities. So just giving the values, typical parameter values, we are trying to vary the so how we can understand the variations throughout the stabilizing effect of dust inside the plasma.
Okay. And what is the typical ratio of your rho s by ln, the inhomogeneous density scale, and you are
it's like
so the ratio of the rho s by ln.
We are considering like 1 to the power 1 e to the power minus 2.
And what is your rho s? Matlab ion Larmor radius.
Oh, like have to calculate anything.
Because the ratio has a important role for having the instability. Thank you.
Any other question? Okay, one small question from my side. So you are studying waves in normal plasma, and you are seeing the effect of dust.
Yeah.
And then how we are thinking about magnetized dusty plasma.
So like we are having plasma, right? So inside plasma we are introducing the dipole magnetized plasma we are having, and we are introducing the dust particles into the plasma. So we can say that as per DAWs, like dust acoustic waves waves are propagating or not. We are trying to understand that whether there is presence of waves or how they can be studied kind of by influence.
Okay, so you are assuming the plasma magnetized and you are putting dust into it, or you are assuming dust also magnetized. You are applying dust.
Dust is not magnetized. Like we are magnetizing the plasma.
Okay.
Magnetized plasma inducing the dust.
Okay, sorry, I missed it. Thank you. Okay, if there are no further questions, thank you very much, Justin. Thanks for your talk. Thank you. So with this talk, all the talks are covered, 1 invited and 4 contributed talks. This brings this session to the end. Thank you very much for your patience and listening. Thank you very much to all the speakers for wonderful talks. Thank you.
Thank you so much. Now I request our session chair, Dr. Sanat Tiwari, to kindly come on the stage and present a memento to our session speaker, Dr. Pintu Bandyopadhyay. Sir, please come on the stage. I request all other speakers, please be ready to come on the stage. Now I invite Dr. Nishan Sirse to present a memento to Dr. Sanat Tiwari for the chairing the session. All oral talk presentator, please come on the stage. That's Thank you, sir. Now we have a lunch break for 40 minutes. We will start our next session at 3:10. So please come back around 3:10. And lunch is the same place, IPSA Mess.
Check, check. Hello.
अच्छा, ओके. Hello, check, check. Hello, check.
Welcome back, all of you. So after post lunch, we have. Sorry for interrupting. So after post-lunch, we have first session on plasma sources and diagnostic, a fundamental part of both laboratory and industrial plasma research, chaired by Dr. Shantanu Karkari, IPR Gandhinagar. I request to come on the stage and sir begin the post lesson. Sir, you want to do? Yeah, you can. Yes, yes, yes. No problem.
Hello, check.
Okay, good afternoon to everyone. So welcome back. So we have this session. So we'll have first invited speaker and Dr. Vibhuti Bhushan Sahu is from Department of Energy Science and Engineering, IIT Delhi. He's going to talk on synthesis of functional films by control of plasma parameters with radio frequency and ultra high frequency and hybrid plasmas. Okay, so welcome sir, and please have.
So first of all, good afternoon to all, and I would like to sincerely thank the organizers and PSSI for providing this opportunity. So this is the title of today's presentation: Synthesis of Functional Films by Control of Plasma Parameters with RF to UHF and Hybrid Plasma. So this is a invite tutorial talk. So it is mostly generic, and I hope you will feel some kind of information. So before starting, I would like to briefly talk about our department. So our department is an interdisciplinary department. There are different faculties with different backgrounds, and there are various groups, and among the various groups like solar, thermal, electrical, mechanical, chemical. So this plasma group is one of the groups, and we are having 5 faculties in our department undertaking these R&D activities, including simulation and experiments on plasma science and technology. And we have a lab, common lab called Plasma Physics Laboratory, and it has 4 experimental labs with facilities, various facilities for different kind of studies. So before starting, I would like to acknowledge our student contribution as well as funding agency, industrial support, and also most of the work is done by a team of researchers. And especially most of the work were covered by me while I was working as a scientist in South Korea, then as a faculty in Nagoya University, Japan. So this is the outline of today's presentation. So most of the people in our life, most of the work, most of the events in our life is now controlled by the plasma. So since earlier 90s, we have plasma welding techniques, then etching, coating, and now recently we are in a zone of nanoscience, and where plasma science has a big role, and we have now different kind of application like sputtering, PCVD, and for flat panel display devices, then healthcare, textile, as well as medicine, agriculture, as well automobiles, then surgery, as well as defense application, apart from the environmental application. So there are plenty of applications which are being undertaken using the help of plasma. So plasma is a tool for various kind of applications. So before starting, I would like to briefly mention, recall our memory. So we have a famous equations called Saha ionization equation, which is the fundamental for all kinds of plasma generation. And according to the Saha ionization, so there is everywhere there is an ionization. And even in the ambient atmosphere, we have negligible ionization is there, and the density of charge species is negligibly small. And then he's the famous scientist. Unfortunately, he was not awarded the Nobel, but Nobel laureate. So he's Irving Langmuir. He's a chemist. He was awarded Nobel because of his series of experiments on plasma, and during early 1920s and 30s. So let us discuss briefly about cosmic ray, role of cosmic ray. We are discussing about plasma. Plasma is generated by electric field. And when you are discussing plasma generation, plasma is a highly ionized species, and plasma is created from the neutrals. And plasma is generated through these electric field. But electric field does not interact with these neutrals. Neutral has no relation with the electric field. So how plasma is then generated? This plasma is generated because of this background electron present in the cosmic radiation. So these cosmic radiations are high energy radiations. They are coming from the distant galaxies, sun, and they interact with the atmospheric molecule, and they become secondary emission. They become secondary radiations, and they are coming towards Earth, and they present everywhere as a elementary particle. And these are the background source, or we can say seed electrons for the plasma generated. So to generate a plasma, we need a device, and this device is called plasma source. And in order to develop a plasma source, we need an electrical source, you need neutral gases or mixture of gases, and we need a vacuum vessel with vacuum systems, and also there are suitable electrodes to couple the power. So these are various key components of a plasma system, plasma device called plasma source. Yesterday, in the beginning, there was a beautiful lecture by Professor Patil, and who has explained various kinds of plasma sources: DC, AC, RF, microwave, ECR, wave-heated plasma, including ICP, high-density plasma sources. So I hope you might have gone through these papers. These are beautiful papers on fundamental plasma devices. So, and in this paper, so one thing is highlighted: there are different kind of plasma devices, and which are being used actively in our day-to-day life. And yesterday we have several series of lectures on laser plasma, then plasma, basic understanding of plasma, then also today we have series of lectures on energy generation using tokamak, as well as now this session is for plasma sources and diagnostics. So the talk is mainly aiming at for discussion on various aspects of plasma sources and diagnostics, how the plasma can tailor an end application. So we have, so this talk is designed in such a manner that, so you will have some information. So for any kind of application, we need a dedicated plasma device called plasma source. So this is a plasma source, and for this source, there is an end application. The application, let us take an example of thin film synthesis, and it can be used for energy generation, it can be used for material, it can be used for synthesis of different kind of material, agriculture, and all different application. Now this device is creating plasma, and once plasma is generated, there are various kind of reactions are going on that specify the chemistry. And there are several parameters: plasma density, electron temperature, potential, electron energy distribution function. They specify the physics. So there is a simultaneous interaction between plasma physics and chemistry is going on when we are designing an applications. And the recent trend is showing we need a higher density plasma source, relatively larger area for larger area applications, and we have a uniformity issue, and we have to control radical or plasma parameters, and we need suitable diagnostics. And also, these devices are aiming for advanced application like nanoscience and new area of application, specifically for flexible application with high growth rate and larger area. So in order for an application, we have to still require advanced plasma source, and for this we need a high density plasma, as well as it should generate radicals for the applications. And in order to enhance density, some people are using magnetic field, then other high density sources like ICP and higher excitation frequency are being used for generating high plasma density. Also, we need radical and plasma diagnostics for monitoring and controlling the plasma parameter. And also, when we are dealing with an application, we should also know what is the correlation between the plasma physics and the application. For example, the material applications, so that we can give concrete information for the industry for depositing film and its growth and its various property controlled by the parameter. So this is a typical example of plasma device. This is called capacitively coupled plasma. It has two electrodes. One is power electrode and another is ground electrode. Substrate wafer is placed on the ground electrode. So it has component. We need a electrical power supply, circuitry, and also we need neutral gas, and we create a plasma and we deposit thin films. So there are various mechanisms involved: fluid dynamics, chemistry, surface chemistry, and also thin film material synthesis. Here the plasma parameter like electron, ions, and radicals, they play a crucial role for the film growth and their property. And in this plasma, when there is a plasma, and there are various reactions like electron impact dissociation, ionization, excitation, recombination, relaxation, which are carried out by the electrons. Also there are ions and there are radicals. So we have a study, recent study, which shows various activities. If there is a growing substrate, then there are several contributions from the substrate, from ion, recombination, electron, and radiation. All such effects are under impact to the substrate. So we need a diagnosis, suitable dedicated diagnostics for controlling and studying these parameters. And this slide showing how the ions species in the plasma is controlled in a plasma process. So when there is a plasma is generated, it is being used for application, then we have different kind of radicals, those are generated in the plasma. So you can see the radicals are different by a sign of hydrogen. So when the ion or species are different, their bond strength is drastically changing. So when these species are present and you are incorporating them for a application, then it is very much essential to study, control, and examine their property for understanding the overall process for end applications. And particularly plasma has a role. It can control the reaction activation energy. So in order to get a reaction, chemical reaction, we need a activation energy for a fixed Gibbs energy. And the reaction activation can be changed by plasma processes. And this is the role played by the plasma. So plasma acts as a catalyst for chemical reactions. So we need different kind of plasma source for a particular end application. And this is what industry is facing, a lot of challenges. Now, today's study, I will briefly give an example of our study on thin film deposition using a PCBD process, using radio frequency plasma. ultra high frequency plasma and mixture of radio frequency and ultra high frequency plasma called hybrid plasma. And typically we use these sources for depositing energy materials. So energy material means these are used for solar cell and other applications. So these are silicon based film used for different application. And first of all, we have to understand the plasma generation mechanism when we are using this source. So we have a silicon nitride film. We have to use source of silicon as well as a precursor called nitrogen, which is a molecular gas. And nitrogen dissociation energy is very high. And excitation, ionization process are also occurs in the plasma. So from the excitation, we see this cross section, we need an excitation energy about 11 to 12 eV for the excitation of nitrogen. And this is for the ionization, we need a high energy about 18 to 19 eV for the ionization. Why these are important? Because we have to generate a silicon nitride film. So the sources are silicon and nitrogen. So silicon is coming from silane, which is an electronegative gas, and nitrogen is producing the nitrogen species radical for making the silicon nitride film. So this is the source we have developed, and it is integrated with different diagnostics, optical, Langmuir probe, vacuum ultraviolet absorption spectroscopy, OES, and also the Langmuir probe, RF compensated Langmuir probe. And this is the schematic of the source. And there are two sources, CCP source. One is 13.56 megahertz RF. Another is ultra high frequency, 322 megahertz UHF, ultra high frequency. And this is the cross-sectional view. And there are different diagnostics. And this is the process condition. And we use several diagnostics method to understand the plasma generation mechanism. So we use RF compensated Langmuir probe, which is a multi-stage filter circuits using our dedicated structure of self properly tuned probe, as well as this is the calorimetric probe, and this is the ultraviolet absorption spectroscopy for measuring the radicals in the plasma. So first we analyze the Langmuir probe characteristics, and it shows the comparison between RF, UHF, and the hybrid. Combination of RF and UHF is the hybrid source. So we found that the hybrid source with same power is giving a density 1 order higher compared to other sources. So significantly density is increased in the hybrid plasma. We further analyze what is the mechanism. So we investigated the role of hybrid plasma for the density obtained, electron temperature, this is typically the Debye length, and this is the RP to lambda ratio, and it is very high for the hybrid plasma, and skin depth, it is 12 millimeter. And the nu by omega ratio, the excitation frequency and collision frequency, the ratio is close to 1. So this is a typical condition of resonant absorption in case of high frequency as well as the hybrid frequency. So we checked with the cross-section data of nitrogen, and this is calculated. And we see interesting result in EDF and in RF. The tail of the population, there is a small tail in the high energy population. In UHF, the tail is higher. In case of mixed hybrid, there is a generation of bi-Maxwellian distribution. And the high energy electron are required for excitation, ionization, and dissociation reaction to continue in the plasma. And we analyze further radial profile of the plasma parameter, and we can see that a 1 order higher electron density is obtained throughout the plasma radial column. And typically there is a additional warm electron with high energy, which is generated close to the electrode, UHF electrode, and it is existing in the central region of the plasma. And the plasma potential for the hybrid plasma is somewhat lower compared to RF and UHF plasma. And we investigated the situation, how the generation electrons are getting energy, and we realized the role of sheath, and we measure the sheath voltage using a high voltage probe, and we measure the voltage across the blocking capacitor, and we check the sheath voltage gradually increasing with increasing the RF voltage, RF power. So we mixed the RF and UHF power. Total power is 200. So we started from UHF full power. So sheath voltage is 0, and it is increases as we increase the RF power. And also we measure simultaneously the plasma parameter, and we calculate the ratio of stochastic to collision heating, and we see that the stochastic heating ratio is higher when we mix the higher power from the high frequency source. And this result clearly shows us the interesting phenomena. Typically for hybrid plasma, the density is higher, the bimaximum electron is generated, and typically will have a higher density. And then we checked this with the silicon nitride process. You can see there is bimaximum type distribution when there is a high power fraction of high frequency source. Then we use this for silicon nitride deposition, and we measure the nitrogen radical density, which has a similar profile with the deposition rate. This is the deposition rate, and this is the nitrogen radical density, where the gas temperature is following reverse way. And we check the flow distribution of various species using different filter like nitrogen, then hydrogen filter, using a CCD camera, and we check this flow, and there is a substrate in the bottom, and we investigated this flow is basically coming from the electron impact dissociation of the molecular species. So when the dissociation is higher, especially for the hybrid plasma, it is giving us a higher growth rate film. And then we check the film property of the hybrid plasma. So we check the chemical property of the film using FTIR, Fourier transform infrared absorption spectroscopy. And we check the bond concentration using the analysis. And we see that nitrogen to hydrogen ratio, atomic ratio in the film is higher, typically for the hybrid plasma, where the UHF power ratio is higher compared to RF. And we check the microstructure using Raman analysis. So it gives an impression of the film quality. So sometimes industry needs silicon-rich film, sometimes industry needs nitrogen-rich film. So the property, optical property changes drastically from the structural property. And we check that in the hybrid plasma, typically when the UHF power is higher and or equal to the RF power, then the film exhibits an improved microstructure and enhanced property. We check the film content using the XPS analysis, X-ray photo emission spectroscopy, and we see that nitrogen to hydrogen ratio is higher for the film prepared at RF and UHF same power. We check the functional property of the film, and so this is the functional property. This film exhibits good photoluminescence, which are useful for the device applications. So the film prepared with the higher power of UHF film has a higher range, has a higher peak of the luminescence, and it is shifted towards higher wavelength, and typically it is the film with silicon-rich film, they are toward blue, and when the nitrogen-rich film are there, they are shifting towards red color. So what is the scenario here is, when we are using a hybrid plasma, or basically when we are mixing the radio frequency and high frequency power together, then there is significant ionization, which are observed by the Langmuir probe analysis. Also, there is significant dissociation, which are observed, which are measured by the ultraviolet absorption spectroscopy. And typically, when there is RF single frequency power, the nitrogen radical density is low. When there is a single UHF power, nitrogen radical density is higher compared to RF. So the high frequency has a higher dissociation capability compared to low frequency. And accordingly, the radical density is higher for the high frequency operation. And for the mixed frequency or hybrid power generation, we have significantly higher radical density of nitrogen compared with hydrogen. So for large band gap application of silicon nitride, which is an insulator, one can tune the band gap. One can tune the property of the material by controlling the radical and controlling the plasma parameter. And so the beauty of this hybrid plasma is we are combining a low frequency power and high frequency power. So it is a mixed frequency power operation. And in the plasma, there are electron and ions. Electron response to the both low and high frequency is okay, but the ions are sluggish for the high frequency operation. So in one hand, using high frequency, electrons are making the ionization and dissociation, and with low frequency, ion bombardment, ion energy are controlled. So we are getting a improved film quality in the hybrid plasma when we are using it for PCVD applications. So this is the this is the comparison with the literature. In our case, we have deposited without heating. People use high temperature for depositing silicon nitride film. We use low temperature, room temperature deposition using hybrid plasma process. Then I will briefly talk about our activities. So in IIT Delhi, we have developed recently a new kind of CCP device, PCVD device, which is based on the hollow cathode effect. And the idea is in the RF plasma, essentially the plasma potential is higher, about few tens of volt to about several hundreds of volt. So when there is a high plasma potential, ion energy gain from the plasma potential is higher, and the degradation by the ion bombardment is severe. So to control the plasma potential and to generate a high density plasma, we developed a plasma device which can incorporate, we can bypass the generation of self DC voltage, as well as we can give us a low plasma potential device. So this is we have relatively developed. We have also recently developed a multi-target magnetron sputtering system, and the vacuum chamber and other components we are fabricated by Excel equipment. So we have given our design of magnetron. So we simulated the magnetic field, and we have used a unbalanced magnetron sputtering system with advanced facility. We're using we are now developing different kind of diagnostic tool for plasma monitoring. So in conclusion, I would like to tell, still we need to design and develop new kind of plasma sources. We have to study the mechanism of plasma generation, radical generations, and all to completely understand their role for the end application. Also, fundamental science on plasma process become more important for advanced thin film design and synthesis with molecular control of structure. So basically, we have to correlate the plasma science with material science or application when we are dealing with a plasma for a particular application. So this is the end of my presentation. Thank you.
It was a nice talk by him, and Dr. Bibu presented a general description about the plasma things, and then he talked about how the discharges are produced by radio frequency capacitively and UHF, ultra high frequency, and then he took us to some applications. Now the talk is open for discussion. Any questions from the audience?
Hi, sir. So my question is, why by increasing the RF power of the hybrid in mode, the sheath voltage is increases that you showed?
So why the sheath voltage increases at?
High RF power.
Yes.
At high RF power.
The hybrid RF power that.
Hybrid RF power. Why the power?
So basically, the measurement scenario is here. Okay. So this is the scenario. We measure the sheath voltage across the blocking capacitor. Okay. And this is connected with RF. Okay.
Yes.
So it is a high frequency. So the capacitor sheath is producing the capacitance. Okay. So it is 1 by j omega c. And when low frequency, omega is low, impedance will be higher. Okay. The contribution of the RF part contribution will be higher. And for the ultra high frequency is higher. So the sheath capacitance contribution is lower. Sheath impedance is lower compared to RF. Okay. And typically it is showing when it is 0, when the UHF power is fully operational 200, and as we increase the RF power, sheath voltage is increasing.
So here your ultra high frequency is through and some kind of antenna or what?
Yes, this is a lambda by 2 line.
Okay.
So 320 megahertz.
Oh.
It gives a wavelength about 98.
Okay.
So we use 49 centimeter copper tube.
Okay.
And these are shielded by ceramics.
Okay. So yeah, any other questions from the audience? Okay. So you mentioned about the Langmuir probe system, and you said that you have used some compensation Langmuir probe.
Yes.
So how you compensated ultra high frequency UHF frequencies?
So essentially the RF fluctuation is higher at very low frequency RF.
Okay.
And the UHF frequency we are using is close to microwave. Okay. So we assume there is fluctuation is low.
Yeah. Fine. So one more question is like, so you showed several diagnostics, and you also mentioned that the control systems to get the unique features. So which diagnostics are used for controlling the plasma?
So we are using RF.
I meant to say the online control systems.
Inline.
Inline.
So this is the RF compensated Langmuir probe for plasma monitoring.
Okay.
Then we have, this is a radical monitor diagnostics.
So this gives you the feedback control.
Yes, yes. So
okay.
There is a feedback control is there.
Okay, so yeah, so I think if there is no more questions from the audience, then we should thank the speaker again. Okay, thank you. Okay, so now there are going to be I think 1, 2, 3, 4 oral presentations, and the first speaker is Mr. Sanjeev Kumar Pandey, and he is also from India Center for Lab Grown, which was the institute? Yeah, from Chennai, right? IIT Chennai, yes. And he's going to speak on three-dimensional electromagnetic plasma simulation of a microwave plasma chemical vapor deposition reactor with spectroscopic validation. Okay, so I think you have got 15 minutes. I think 15 minutes, you know? 15 minutes and 5 minutes for discussion. So yeah, we'll give you a signal at 13 minutes is over. Okay, thank you.
Okay, hello. Yeah. So, good afternoon, everyone. Myself, Sanjeev here from Incent LGD IT Madras. I would like to thank the organizing committee for providing me an opportunity to present our team's work here. So, I'll be talking about plasma diagnostics validated simulations for microwave plasma chemical vapor deposition. So the outline of the talk will be like this. First of all, I will be briefly introducing about our center, Incent LGD. Then I'll give some introduction related to the microwave plasma chemical vapor depositions. Then I'll briefly introduce about Druid model for microwave plasma simulations. Then typical schematic and simulation tools used to model such kind of plasmas for diamond depositions, some simulation results, and experimental validation using optical emission spectrometer or optical and OES spectroscopy, and then some conclusions. So I would like to thank Professor Sau, the earlier speaker, for making my task very much easy. So this is our center, because most of the things he has already explained. This is our center at IIT Madras Research Park, which is named Incent LGD, which stands for India Center for Lab-Grown Diamond Technologies, and it is headed by chair of 5 professors, and the main PI is Professor Ramachandra Rao, and the center is established at IIT Madras Research Park in collaboration with IIT Madras and Ministry of Commerce and Industry. The center consists of 3 verticals. First vertical is MPCVD, which deals with the microwave plasma enhanced chemical vapor deposition. The second one is HPST, high pressure, high temperature process for the diamond deposition. And the third vertical is SSMG, that is solid state microwave generator center. So MPCVD, as you all have know, that it stands for microwave plasma enhanced chemical vapor deposition. So in this particular process, we generate plasma based using microwave power supply. Basically used either 2.45 gigahertz or 915 megahertz. And the plasma density that we are talking about here is approximately around 10 raised to power 16 to 10 raised to power 18 per meter cube. And the temperature ranges, since it's a non-equilibrium plasma, so temperature ranges electron temperature ranges from 1 to 2 eV, and gas temperature ranges from 3000 to 3500 Kelvin for the diamond deposition process. So in the image here on the right hand side, you will see several commercial systems that are commercially available worldwide. The figures include top launch, bottom launch. So the top and bottom launch are distinguished by the way how we are coupling the microwave into the chamber, either from the top side or from the bottom side. So major components of such kind of a system includes microwave power supply, basically of 6 kilowatts, then a waveguide assembly, then some cavity resonators, vacuum pumping and pressure control systems, and finally plasma diagnostics arrangement. So here is the portrait of what the system that we are developing at our center, named Vajratara. So this is the figure on the left. The figure on the left is the recent photo. The figure on the right is just to mention what are the several components that has been included in there. Yeah, so coming back to the modeling aspects, so we are using a tool called CST. So it implies Druid model for this microwave plasma simulations. So Druid model is a very approximated model for the plasma simulations. It is basically of 2 types, static and dynamic. Static one considers the plasma frequency to be a constant, and dynamic one considers it to be a functional form of localized electric field. And it treats plasma as a dispersive medium. So in this model, what we do is we solve Maxwell's equation, which is given in equation number 1, and the permittivity, which comes when we consider the dynamic model, then the permittivity comes out to be this, which is given in the equation number 2, and the density density is given in terms of the localized electric field, which is a very, very, very approximate way to model a plasma, because plasma is a very dynamic system and it involves very complex continuity and momentum equations to solve. But for the time being and to save some computational things and to just to design the system, these kind of models are approached usually. And in this model, there are two types of electric field that the model establishes. One is EB and one is EM. EB is the minimum field required for the breakdown, and EM is minimum field required for the maintenance of the plasma. So what are the tools that are typically available to model these things? There are various commercial tools, including COMSOL Multiphysics, CST, ANSYS, HFSS, Fluent. One more software is there, Diademo. This Diademo software is from Russian group. So this particular software is used to predict the growth rate of the diamond deposition, which is being done using this MPCVD systems. And in the figure A, you can see the typical schematic of one of the top launch MPCVD systems, which includes microwave power supply, cavity resonator, 3-step tuner, resonant cavity, and everything. And on the figure B, you will see the real system itself and every component that has been marked. So in the figure C, you will see a equivalent CST model, which was done for this particular setup. So this particular setup, so in CST, what is done here is that design has been done in such a way that the cavity where we have to grow the diamond, using microwave plasma, acts as a cavity resonator. And so what we do is we usually excite TM01 mode inside the cavity, and here in the portrait A and B, you will see this is the electric field plot, electric field variation throughout the cavity. So the antenna is on the topmost point here, and in the figure B, you will see the degree of ionization that is being there near the substrate region. So we'll have different degree of ionizations depending on how much bigger my plasma ball is. So initially, to model this, what this model uses, first we have to design the chamber in such a way to excite the TM mode and visualize the electric field without the plasma. Then we'll include this density calculations, which are discussed earlier in the slides, and then we'll evaluate what is my electric field is there in the cavity near the substrate region. So so here we are in the figure A, and figure B is there. So figure A, we are looking at the electric field after igniting the plasma inside the cavity resonator, and we can see some substantial values. We can see some substantial values near the substantial values above the substrate, which is very much is the required condition to localize the plasma above the substrate where we are putting our diamond seed to grow. The electric field ranges on the order of 10⁴ volt per meters, and the density is approximately 10⁻12 centimeter cube. So and in the figure B, to mention, in the figure B, we'll see the corresponding plasma density. So we can visualize here using simulations that the major portion of the density is grouped above the substrate, which is very much is the required condition for that diamond deposition using CVD process. Coming back to the experimental validations. So we use optical emission spectrometer to validate whatever we are observing inside the reactor. And this is the typical setup. which includes of the data acquisition setup and this reactor setup for this process. And in the figure B, you'll see various components of the OES systems like grating, slits, and everything, which are like bifurcated in the different parts. Different parts. So what we observe is since morning a lot of talk has been going on the OES spectroscopy, optical spectroscopy. So what we observe is a line radiation, which is given in the figure C, which will have intensity on Y scale and wavelength on the X scale. And what we do is try to determine the electron temperature and plasma density using this data collected from the required resolution of OES, whichever we required. So mostly we have focused on H alpha and H beta lines. So figure A, B, and C are the data collected from the OES spectrometer, and so we use Boltzmann equation, Boltzmann line intensity ratio equation to determine the electron temperature, and we use full width of half maxima of the H alpha and H beta lines to predict the density that we are electron density that we are observing, and we have collected and analyzed the data, and we have found out to be in the range of T to be in the range of 0.95 eV, and any of the order of 10^18 per meter cube. So so these are some conclusions. So although CST as a software is not very much not very precise and accurate to model that plasma, but still people, for the time efficiency and things, people use this model just to design their chambers. A more elaborate way to model these kind of plasmas would be to create 3 different modules: EM module, plasma module, and flow and thermal module, and individually couple these models to bring out the self-consistent solution, and include the growth model as well. But for the time sake, industry and people use these kind of tools, and the order of the electric field and the density is what we have observed through OES matches fairly enough with the simulations. And one of the tasks that we need to do is create a feedback loop, like whatever we are observing with the OES, back to the control systems of the CVD reactor in order to optimize the process control or the deposition control that is underway. Yeah. So in this model which I've shown, I have not we have not included methane chemistry. So there are many number of chemistries depending on the requirement. So as you introduce the nitrogen, the growth rate will be a little bit higher in such kind of depositions. But that full scalable model, we have to add that component into this. We have not still have added. So that part has been remaining. And that's all. Thank you.
Okay, so the Drude model that you have used, it assumes a density and temperature a priori, right?
Yes,
so
yes.
And then you are able to get some, microwave simulations.
Definitely.
And then you demonstrated that there is a bright plasma which is formed at the substrate.
Definitely.
So why is it that you have intense plasma near the substrate? So what is happening there?
Yeah. So if you'll see the electric field plot, this plot number A. So when you'll push the microwave electric field inside the chamber, so it acts as a resonating cavity, and
Okay.
it is a TM01 cavity. So the main mode, the cavity and the stage is designed in such a way that the maximum electric field sustain in this particular region.
Why it's so
why? Because of
how you decide the cavity lengths and all these things.
Yeah, it's based on this microwave TM transmission theory actually. electromagnetic transmission theory.
Okay, so can you elaborate on that?
Yeah, I mean, elaborate. Yeah, I mean, from the microwave power source.
So you are launching some microwave from the top.
Definitely.
And it could have been anywhere. So what's the distance from that to that place where you are putting your substrate?
From the top to substrate. So the exact numbers I am not having here, but I'll get back with the numbers actually.
Okay, so the forum is open for discussion. So questions from the audience, please. Yeah.
Which simulation you have used?
Sir, I have used a tool, CST, in which there is already a material defined as a Drude material. So,
which boundary condition you have used?
Perfect electric conductor, like to design PEC boundary condition.
I hope there is a quartz plate also there.
Yeah. Quartz plate is there. Yeah, this is the region where the quartz is situated. Yes.
Okay. So you in the dielectric you took quartz or something else, high dielectric constant?
No. There is quartz.
Okay.
What is the substrate size? I mean, does it depend on your substrate holder? The plasma change with respect to the diameter of the substrate holder?
Yeah, that's a good question. Actually, size is decided based on the how much radius of a plasma ball we are generating actually. So suppose this is a 2.45 gigahertz, so typical size ranges from 1 to 2 inch. But if we tone down to 915 megahertz reactor, so the system size will be bigger. My plasma ball size will be bigger, and substrate size can be changes accordingly. Like
no. See, but if you change the cavity size, what happens?
If I change the cavity size,
I should have the bigger plasma, right?
Bigger plasma, right? And substrate size will be decided based on the plasma size itself. Like how much area we want to treat with the. I mean, how much area we want to cover with the plasma ball uniformly.
I have one question.
Sir.
This side.
Yeah.
This one.
Yeah.
For this growth, right? You require a uniform electric field over there, right? Over the substrate.
Right.
Since you are simulating and you are basically based on this simulation, you are designing something. So in presence of plasma, if you are taking the almost constant value of plasma, then you are designing your cavities to get the uniform electric field over the substrate to have this uniform growth. How you will correlate this? Because you are having lot of assumptions in this design, right?
Yeah.
But in actual case, because for what I have heard and what I have seen,
right,
for 1 micron growth, typically it takes more than 10 hours or something like this, right?
Definitely.
Right? So for that particular period, if you have to maintain that constant electric field to have the uniform growth, so how this design basis will help you?
So this is a very good question that you asked. So this is the thing just to model the cavity. I am not saying that this is a accurate model or this is the exact model that can be. So there are variations, but it will not be in a range of that it will change some order. For the time being, just to quick the designing process, people use such kind of tools. The exact modeling of it would require a solution of Maxwell's equation with continuity and momentum equations altogether. Actually,
I think the question was like, this is the simulation you are doing is a vacuum field at that point, right? With the plasma, and then you are doing the model of the plasma actually with the Drude model.
Yes.
So the vacuum electric field is more intense, as you said, over there.
Yes, absolutely.
Correct. Okay, so that was the thing. Any further question? So one thing is like when you are doing the actual CVD.
Yes.
So you have different compositions of gas mixtures and other things actually.
Yes, sir.
So and you will have different kinds of density, electron density.
Right.
So this may not be the true thing because you have to involve the chemistry also.
Yes. This is I'm exactly saying this is basically for reactor optimization just for the time being.
Okay.
This is a very quick process. The center is also involved in developing its own in-house solver, which will require some time. So
okay, so we should stop now because of time. Okay, we will thank the speaker again. So we will go to the next one. Okay, the second speaker is Krishna Kumar Singh, and he's going to speak on cylindrical non-neutral plasma experiment. And he's also from, you're from IPR? Okay, great.
Okay. Okay. So, good evening to everyone. I am Krishna Kumar Singh from IPR. I am going to present my PhD work here. Title is non-neutral plasma, cylindrical non-neutral plasma experiment. So, the title of my experiment is actually I am doing the cylindrical non-neutral plasma as a test bed for imaging the non-neutral plasma for toroidal device. So here is the outline of my talk. The first I will go through some introduction of the device and non-neutral plasma, and the linear trap that I am working currently for the development of imaging. Then experimental setup for the electron plasma imaging in linear trap, some imaging results, and COMSOL simulation for the potential, plasma potential, how the plasma potential is vary when we change the electrode or by biasing the our electrode for the confining the electrons, and conclusion of future works. So till now everyone talking about the plasma. So this is I think no one talking in this whole colloquium the what is non-neutral plasma. So non-neutral plasma is a single component plasma which contains only electrons, protons or positrons. So why we call it is a plasma? Because it exhibits all the behavior that show a conventional plasma. That like the plasma waves, instability, device shielding. I have studied all the instabilities, collective behavior in non-linear trap device. So non-neutral plasma behaves as a non-neutral, actually it is cloud of electrons which behaves like plasma behavior. So we call it plasma. So this figure show the smart XC, small aspect ratio toroidal experimental device which is in our lab. This is schematic. This toroidal, so the plasma, it aspect ratio is 1.5 and major radius 13 centimeter, minor radius 8.5 centimeter, and we inject the electrons through in the trap by hitting the filament which is at 100 to 300 volt and confine the electron by grids. Here two. See this is a grid which we call the injector grid, and the green one is called collector grid, and the circle here is a filament. So how we form the plasma based on the injection, hold and dump technique. So where you hit the plasma, allow to go through the grid and keep the collector grid at negative potential, and when we switch off the injector grid from zero potential to negative potential, the plasma is confined within the collector grid and injector grid. So this is a way how to confine the electron in a toroidal device. So in smart XC, it is a partial with a strong toroidicity because it has aspect ratio is very small, the toroidicity is very high. But we found the confinement time of more than 100 seconds. That we call this is a world record that the whole plasma group of worldwide is surprised. How we can confine the electron plasma cloud in the toroidal device for more than 100 seconds. So the motivation of my work is we predict the confinement of electron plasma more than 100 seconds, but here is a contradiction that magnetic pumping transport theory contradict the what we have done. So magnetic pumping transport theory say that we cannot confine the plasma in toroidal device, such a small aspect ratio toroidal device, in more than 3 seconds. So we write the paper and send it for publication. So reviewer asked how we contradict the magnetic pumping transfer theory. For that, he asked for to do some diagnostics. So to investigate the transport phenomenon, how we can find 100 second of electron plasma. So we develop some diagnosis like the plasma density, temperature, plasma potential, and the collisional parameters of between the electron and electron. So the challenges was to develop this diagnosis. The first one is neutral density, electron density, because our system are in the 10 to the power minus 10 millibar. So we cannot use the Langmuir probe or directly use the spectroscopy to see the plasma cloud. So its density is very low, temperature is also very low. It lies between 1 to 10 electron volts. Also there is some geometrical constant which contradict us to develop all these diagnostics like the imaging diagnosis in the toroidal device. But we developed some diagnostic through which we claim that the confinement time of the electron plasma in the toroidal device is more than 100 seconds. For that, we develop dichoton lunge. For a dichoton lunge, m equal to 1 and m equal to 2 for finding the charge and density. Second one is the evaporative dump for temperature measurement. What we do in evaporative dump is we sweep the collector grid from some potential to 10 from suppose we sweep the collector potential from 50 volt to 80 volt. So all the electrons which have the energy between which has energy between less than the 80 volt will go on the collector grid, and we find the total charge from where we can calculate it temperature. Then charge collector, we develop a charge collector diagnosis. Langmuir probe or emissive probe are also in going, but we are not find a well result using the Langmuir probe or emissive probe, because these two probes are see directly to the plasma and it perturbs the plasma and it kills the plasma. So, but after investigating all the diagnosis, the question reviewer asked how you know the density profile of the plasma. So we have not answered how the density profile of the plasma is changing with time. So for that, we have to think about the image diagnosis to implement in toroidal trap. For that, I am investing the image diagnosis, which already people have done in other labs, but not in India. So we are trying to use linear trap as a test bed to develop the image diagnosis, and this image diagnosis, after the successfully implementation, we shift it to a SmartXC for the image diagnosis. So for that, I am choosing some phosphor to develop the image diagnosis for SmartXC. So I have used two phosphor, P43 and P42, and two of P15 and P11 are under the process. So using the two phosphor, I have obtained some images, but the images is not very well to claim that the electron is this the glow or the images that I have obtained, it is electron plasma or something. It is behave like something freezed. So I have used P43 and P22 phosphor screen, and I want to a phosphor screen which work on the lower potential, also जो vendor provide us easily. So I have used two phosphor potential in which the P43 is very best as compared to P22 for me because it works at lower potential. So for developing the image diagnosis in Smart XC, we have designed a linear trap for as a test bench for developing the image diagnosis in linear trap, toroidal trap. So these are the parameters for the linear trap. The whole trap is divided into seven parts. And this is a schematic, 3D schematic, and this is actual picture of the trap. So here is a injector grid. The E1 is a full electrode, E2, which is divided into 2 parts, and E3 is divided into 4 parts. And E4 is also divided into 2 parts, and E5 is full electrode. So we divide the trap, and after E5 there is a collector grid and the phosphor holder. So we divide the whole trap in 6 to 8 parts for different purposes, like for diagnosis, for control the plasma length, etc. So after designing the trap, we implement the phosphor screen. So the upper figure shows the whole trap which go inside the chamber, and typically the pressure of the chamber is 10 to the power minus 9 millibar, of the order of 10 to the power 9 millibar. So this is a trap, and this figure shows the aluminum coated phosphor screen, and this is schematic how I trap the electron, dump it on the phosphor, and capture the glow of phosphor using the CMOS camera. So how it works is, I have biased the electrode E1 and E5, and it trigger with the FPGA to allow the electron to go inside the trap and confine them. And after that, we dump the electron on the phosphor screen and see its glow through the camera. So before implementing the phosphor inside the chamber, I have tested the coating of uniformity of the phosphor screen by the ultraviolet light. So the wavelength of the phosphor is 440 nanometer, and also the glow ultraviolet light wavelength of ultraviolet light is actually I don't remember, like 350 nanometer. So when we incident on the phosphor, it glow, and we clarify that the vendor that provides us phosphor is uniform. Now, after implementing the phosphor inside the trap, we incident the electron beam, direct electron beam of 200 volt. Actually, the unit is wrong. 200 volt between the filament and the phosphor at 3.58 millibar pressure. So the shape of the filament is look like this because we hold the filament in C shapes. That's why it is look like the C shape. So these are some experimental result that I have obtained. So the first figure, so the dumping, when we dump the electron plasma on the phosphor screen, the glow obtained like this. So the shaded area that we see here is because of the grid, collector grid. So we remove the collector grid and further do the experiment. Before that, I have done some experiment for the verification of the glow. The glow that I have obtained is the glow of the phosphor. So for that, I have changed the phosphor bias potential. So when I decrease the phosphor bias potential, the glow intensity of the phosphor changes. That's verified that the glow that we capture in the camera is because of the phosphor glow. And further we do the experiment, and further we change the phosphor screen and do the experiment. So this is a imaging result that I obtained with P43 without aluminum coated. So this two dark figure is the figure that obtained I take this shot without plasma and take the shot with plasma and subtract both the images and do some coding to obtain the glow of the phosphorus screen. So here we see the intensity at the center is maximum compared to its edges. So this figure motivate me to do the further experiment and do the experiment with same the phosphor with different phosphor bias like 2 kilovolt, 3 kilovolt, 4 kilovolt and 4 kilovolt, 5 kilovolt phosphor bias. So what I have obtained is that when we increase the phosphor bias, the intensity at the center of the phosphor is increases. So this result is little bit worried for me why it is coming. This is still is a question for me why the electron is only come in the center. It is actually the electron is gyrating about the magnetic field, but here this electron is coming at the center of the trap. So it is little bit worried for me. So for that I have do some Compson simulation for seeing the effect of potential of phosphor that I have done on the phosphor holder. So here what I have done is this is a schematic of the trap. So this two pink electrode is at minus 70 volt and this line show the potential well that form within the total trap without biasing the phosphor. Now I have biased the phosphor. So what I have seen that what I have seen that this line, the red line is penetrate the electrode. So this can cause the electron to see electron in the trap and extract the electron direct to the phosphorus screen. Okay, sir. Now for that to resolve the problem, what I have done is I have increased the input potential from 170 volt to 190 volt, so that the effect is gone, but it is still there. So I have to work on that, why it is coming. So after doing the work, I have done the experiment, and what we see that when I increase the phosphor bias, the plasma frequency, dichotron frequency is increased. That indicate that the phosphor bias is directly affect the plasma. That's why the image that I have seen here is coming to the center. So after that I have taken the
I think
another
you have exhausted
experiment.
your time. So 1 minute, you have to go to the conclusion slide now.
So these are the challenges why the images is freeze in time and space only, where I've changed the potential, phosphor potential bias, also the time. So these two figures are work done in two different magnetic field. So conclusion of my future work is I have understand the confinement required, precise knowledge of N of R. This is my future work. Like image diagnosis, linear trap is designed, developed and characterized to use as a test bed for plasma imaging, and characterization of plasma in linear trap with different plasma diagnosis measured plasma parameters are total charge trap in the system is 299 coulomb, temperature of plasma is 5 electron volt, radius of the plasma is 3 centimeter approx, confinement type of 2 millisecond is observed. The initial result of image diagnosis are promising. Different phosphor and the applied potential affect the image of the electron plasma is being studied. And the Compson simulation also show that the phosphor biasing potential direct affect the plasma. And the future
we should stop here now. Let's ask the audience, show some questions from the audience, please. Questions?
Nice talk, Krishna.
Thank
you. My question is, what type of wave mode can either accommodate or exist in the non-neutral plasma, especially in your kind of non-neutral plasma?
In non-neutral plasma, you can excite all types of wave which we study in the conventional neutral plasma. Here people have done the TG mode in the linear trap very accurately and claim that the TG mode is excited very precisely and very accurately in the trap. And I have not studied all types of wave in the cylindrical trap because my work centralized on the image diagnosis, so I have not worked on the
Okay, so what part of the experiment that you have developed?
Sir, I am working on the image diagnosis. I have developed the linear trap for the image diagnosis, and I have used it as a test bed and implement it on the toroidal device for the imaging of the electron plasma.
Quickly answer why you call it as a plasma.
Because it has shown all the behavior data conventional plasma I have shown.
Okay, so thank you, speaker. So we'll move to the next. Please thank the speaker. Okay, so the next speaker is Akankshu Khandelwal, and from IPS Academy, Indore, and he's going to speak on non-invasive diagnosis of plasma parameters in a capacitively coupled plasma discharge. So Akankshu, it's 15 minutes, and but 12 minutes and 3 minutes, I think, for the day.
Okay. Hello. Good afternoon, everyone. My name is Akanshu Khandelwal, and I am a junior research fellow at IPS Academy, Indore. I am here to present my work titled Non-Invasive Diagnosis of Plasma Parameters in a Capacitively Coupled Plasma Discharge. This is the outline of my talk. First, there will be a brief introduction about capacitively coupled plasma discharges and invasive and non-invasive diagnostic techniques. Then, I'll be discussing about the homogeneous discharge model and the error analysis and limitations. After that, the experimental setup and the diagnostic use for the benchmarking will be described. Then the results will be discussed, including discharge impedance analysis, comparison with Langmuir probe, effect of RF frequency and voltage. After that, the talk will be concluded with summary and acknowledgement. Capacitively coupled plasma discharges are generated by applying electric field between electrodes while the electrodes are kept in contact with the plasma. The frequency of electric field is kept in ISM frequency band, which is generally found between ion plasma frequency and electron plasma frequency, typically between 2 to 100 megahertz. The CCP discharges are widely used in industrial plasma processes like etching in semiconductor processing, deposition, sterilization, ion sources due to their unique properties like enhanced power coupling due to sheath heating that provides higher plasma density and large area uniformities. Figure 1 shows some examples of CCP discharges used in industrial applications, where figure A and B shows CCP discharges used for surface treatment applications, and figure C shows CCP-based ion source. These applications for better outcome and efficiency require constant plasma parameter monitoring using some kind of plasma parameter diagnostic systems. These diagnostic systems can be classified between two different categories like invasive diagnostics and non-invasive diagnostics. Invasive diagnostics include electrical probes like Langmuir probe, MEC probe, hairpin probe, which is a microwave probe, bead-out probe, which is a magnetic probe, and mass spectroscopy. These kind of diagnostics are very accurate and they can provide localized plasma parameter measurement. But they needs to be in contact with the plasma, therefore they can perturb the plasma or they can affect the process outcome. Whereas non-invasive diagnostic techniques like optical emission spectroscopy, laser-induced fluorescence, Thomson scattering, microwave interferometry, homogeneous discharge model, they does not require to be directly in physical contact with the plasma, and they can be set up outside the plasma chamber. But on the downside, they have less accuracy and they can only provide average plasma parameter measurement. We have used homogeneous discharge model for plasma parameter estimation in our experiments. In homogeneous plasma model, plasma is considered as a series combination of sheath capacitance, bulk inductance, and bulk resistance. Figure 3 shows an equivalent circuit of homogeneous discharge model for CCP discharges. Here, plasma is shown as a series combination of capacitor, inductor, and resistor. And following equations are used to numerically solve this circuit, where the discharge power, electrode voltage, and RF current are externally measured and provided as input parameters, and the equation are solved for plasma density and electron temperature. Now, because this homogeneous discharge model is highly calculative and numerical based, if the input parameter voltage, current, power are measured inaccurately or there are some error in their measurement, then the plasma density and electron temperature measured will also be erroneous. So we have tried to measure what will be the error if there is some kind of error in voltage or current measurement. Figure 3a shows the error in plasma parameter, density and temperature if the RF voltage measurement is erroneous. For plus minus 20% RF voltage uncertainty, the error in plasma density can be up to plus minus 25%. And for plus minus 20% of RF voltage uncertainty, error in electron temperature can be up to plus minus 12%. And figure B shows error in plasma density and temperature if the RF current measurement is erroneous. For plus minus 20% RF current uncertainty, the plasma density error can be up to plus minus 40%, whereas electron temperature error can be up to plus minus 5%. There are some other limitations also, like homogeneous discharge model considers plasma as a homogeneous entity, so it can only provide average plasma parameter. It cannot generate localized plasma distributions or density or temperature distributions. The RF power, voltage or current are estimated using a commercial IV sensor. It can provide highly accurate measurements with less than 1% error, but still the power losses after the IV sensor to the electrode are still not compensated for. And radiation losses and heat losses are also not being compensated in this model. This is the experimental setup that we have used. Figure A shows the schematic diagram of discharge model. We have used parallel plate CCP discharge configuration to generate the plasma. Figure B shows the RF connection scheme where the IV sensor is connected after the matching network, so it can provide true discharge power, current and voltage measurement. Figure 5A and B shows the measurement of RF voltage and current while the RF power is being controlled from the generator. In this experiment, we have used two different excitation frequencies. Therefore, for the measurement purpose, we have kept the RF voltage constant. We have used an in-house developed Langmuir probe for the benchmarking of the experiment. Figure 7 shows the RF compensated Langmuir probe, where an auxiliary electrode is connected through a coupling capacitor to the main probe and some RF chokes are connected after it. These RF chokes provide a very high impedance on the excitation frequency. This is a necessary condition for these RF filter to work properly, that the filter impedance should be greater than this following expression. In our Langmuir probe, the impedance is measured and it has been shown in figure 8, where the impedance of 13.56 megahertz is nearly 100 kilo ohm and impedance on 27.12 megahertz is up to 80 kilo ohms. We have used orbital motion limit theory for the measurement of electron density. OML theory describes collection of charged particle around the sheath of cylindrical Langmuir probe. There are some assumptions in this theory, like the sheath should be collisionless, the sheath thickness should be greater than the radius of the probe tip, and the motion of particle is dominated by the electric field, and that causes them to orbit around the Langmuir probe tip. Expression 8 shows the ion saturation current, and it is used for the measurement of electron density. We have calculated discharge impedance parameters like sheath capacitance, inductance, resistance using the equation 4, 5 and 6. And it should be observed that plasma inductance is inversely proportional to plasma density. and plasma capacitance is proportional to plasma density. So when the RF voltage is increased, the plasma density also increases because the RF power is increasing. Therefore, the plasma inductance is decreasing. Similar result can also be observed for 27.12 megahertz. And whereas the sheath capacitance, it is increasing because the sheath capacitance is proportional to plasma density, and it can be seen for both 13.56 and 27.12 megahertz. One more thing that can be observed is that plasma inductance is greater for 13.56 megahertz and it's less in 27.12 megahertz. That is because when the excitation frequencies increase, it also enhances the coupling of RF power due to the capacitive nature of the discharge. Therefore, the plasma density increases. Because of that, inductance is decreasing. And similarly, sheath capacitance is also increasing due to the excitation frequency increasing. Similar results are also observed in plasma resistance and total reactance, that they both decrease with RF voltage and excitation frequency. For the benchmarking of the experiment, we have used a Langmuir probe and we have measured plasma density and temperature simultaneously with homogeneous discharge model and Langmuir probe. And figure A shows plasma density where the red one is measured by Langmuir probe and the black one is measured by the discharge parameters. And figure B shows electron temperature where the red one is measured by Langmuir probe and the black one is measured by discharge model. It can be observed that both density and temperature, the Langmuir probe and the discharge model shows the same trend, but it can also be observed that the discharge model is somewhere around underestimating the density and temperature values. So it can be said that because the Langmuir probe is kept at the center of the plasma, therefore where the plasma density is maximum, so it will always measure the maximum plasma density, whereas homogeneous discharge model only measures the average plasma density. Second thing is that we are using power in the model that is provided by the IV sensor. But after the IV sensor till the electrode, there are still some possibility of losses of RF power, and the radiation losses or heating losses are not being compensated. Therefore, the actual power deposited to the plasma is less than the power used in the model. That could also be a reason for this indiscrepancy. We have used homogeneous discharge model for study of effect of RF frequency and discharge voltage on the plasma parameters. Figure A shows the plasma density measured by varying RF voltage for two different frequencies. Figure B shows electron temperature and figure C shows DC cell bias. So it can be observed in figure A that plasma density increases with RF voltage because the RF power is also increasing with voltage, and it increases with excitation frequency because when the frequency is increased, it also increases power coupling due to capacitive nature of the plasma. Electron temperature increases with RF voltage because when RF voltage increases, it also enhances the electron temperature, but it decreases with excitation frequency. That is because when the excitation frequency is increased, it also increases the electron density, and that increased electron density reduces the bulk electric field that is responsible for electron heating. That is the reason why the electric field, the electron density is decreasing. The electron temperature is decreasing. The figure C shows the DC cell bias, and for 13.56, the DC cell bias is very high and it increases with the RF voltage. That is because with the RF voltage, the electron temperature is increasing, and when the electron temperature increases, the DC cell bias also increases, so it can reduce the hot electron losses. But because of frequency increases, the electron temperature is decreasing. Therefore, the DC cell bias is also decreased when the frequency is increased. Lastly, I would like to conclude with the summary. A non-invasive diagnostic technique is discussed that does not require contact with the plasma. It requires minimum experimental setup and the analysis. The error in plasma density and electron temperature due to the uncertainty in RF voltage and current has been analyzed and it has been discussed. The plasma parameter measurement is compared with the Langmuir probe. Although both shows the same trend, Both show the similar trend, and the density and temperature is underestimated by the homogeneous discharge model. It is applicable for both low pressure and atmospheric pressure plasmas, and it is a very useful technique for industrial processes where the efficiency of the process is crucial. I would like to acknowledge Anusandhan National Research Foundation for their funding. I would like to thank my guide, Dr. Nishan Sirse, for his constant guidance. I would like to thank Professor Shantanu Karkari and Professor Sarvesh Sharma for their guidance and valuable insight. And I would like to thank Dr. Narayan Sharma and Yashasvi Patil for their help during my experiments.
Okay, thank you. Let us, forum is open for questions from the audience. Yes, there is a question from...
Okay, thank you, nice talk. And maybe I have missed out something. In your previous slide where the graphs is, yeah, here we can see that with the RF voltage increase, the increase with the RF voltage, the electron temperature for the 13.56 megahertz frequency, it increases from 4.5 to up to 5.5. That is almost 1 eV increase. But for the 27.12 megahertz, the increase almost less than 0.5 eV. So almost 50% less, right? But for the case of density, the increase in the 27.12 megahertz is promising with respect to the 13.56. Why these differences?
As I discussed, when the density increases due to increasing the frequency, that density reduces the bulk electric field that is responsible for electron heating. Now that density is increasing, that reduces the electron temperature. That's why the electron temperature is increasing less compared to the 13.56.
And it's only affect just 1 eV? I mean, for the second case, its density is increasing from 1 into 10 to the power 16, right?
Yes.
16 per meter cube to 3 into 10 to the power 16 per meter cube. Almost 3 times.
Yes.
But your temperature is 50% dropped. So only that the collisions effect here or something else there? Okay, that's my question basically.
You have the answer?
The reason is in CCP discharges is RF plasma, so the electron density is very complicated. It is not linear relationship. It's non-linear electron heating is taking place. That's why you cannot correlate electron density, whatever is the increase in the electron density, the same you will see in the electron temperature as well. It's a non-linear heating process taking place in RF plasma. I think that's the answer. Yeah.
Question from the back side? Was there any question from the back? Okay, so one question from me is like you're using this homogeneous model. So, but the application that you're talking about is semiconductor processing, where you have different gas mixtures, gas chemistry.
Yes. Sir.
So the way you said that, like you have a non-invasive diagnostic.
Yes, sir.
So in the case of a complex chemistry, so is your model, are you going to have the same scaling, or will you have to work for the actual plasma?
Yes, sir, it can be worked, but the thing is we have to work with this ionization and the excitation processes properly, where we have to...
So yeah, this equation is to be modified for the chemistry that you want to talk. Yeah?
Yes, sir.
Okay, so one quick question last, this next slide number 8. So here you have seen that like sheath capacitance is saturating, and then on the left hand corner, so you see a drastic fall in the what is called the plasma inductance. Okay, maybe this is losing time now. So if there is no other question from the audience, so may I thank the speaker again, and we move to the next speaker. Thank you, Akankshu. Okay, so I think this is the last talk for this session. Prerna? Prerna? Yes. 3D simulation study of miniaturized assisted electron beam source. Okay.
Hello. Okay. Okay. Pointer is. So very good evening to all. I am Prerna from CSAR CD Pilani. First of all, I would like to thank the PSC committee for giving me this opportunity. And today I will be presenting my work on 3D simulation study of miniaturized plasma-assisted electron beam source. So moving along with the presentation. First, I will be starting with the motivation behind the study, followed by the associated challenges and the simulation models which we have developed to overcome the challenges, followed by the results which we have obtained. Finally, I will summarize my work and I will discuss about the future work which we will be carrying out. So our team at CSAR Siri is working on the development of a compact high-power terahertz source. So basically, it is a plasma-assisted source. Now, why plasma-assisted? So I will briefly talk about the backward wave oscillator. So mainly it comprises of three components. The first one is electron beam source, second is slow wave structure, and third is the spin beam collector. So as the name suggests, the electron beam source will emit a high energy electron beam. That beam will be propagating through the slow wave structure. So slow wave structure is basically also the beam wave interaction structure. So inside this structure, the electron, the beam will basically give its energy to the RF, which is present in the form of noise inside the structure. In this way, the beam will lose its energy, get collected at the spin beam collector, and the RF, which has now gained the energy, will be collected as a terahertz radiation from this window, which is present at the last. So in case of backward wave oscillator, since it is an oscillator, we are not providing any external RF input. So whatever energy is gained by the RF, that is mainly dependent on the electron beam. So that is why the electron beam source plays a crucial role in the development of a high power backward wave oscillator. So the associated challenges in terms of electron source, the first one is we need to generate an electron beam which is micron sized. It should have high current density and high energy from a miniaturized cross section. Miniaturized cross section because the slow structure dimension in case of terahertz are reduced due to the reduction in the wavelength in case of high frequency. Second one is the propagation of the electron beam in a focused manner through the sub-mm cross-sectional drift space of the slow structure, like I mentioned previously. So moving along, for the challenge one, which is the electron beam generation part. So like I mentioned that for high power terahertz generation, we need a high current density and high energy electron beam production from a miniaturized cross section. So for that, we are using pseudospark driven electron beam source. Now a pseudospark driven electron beam source is a gas discharge based electron beam source. It is plasma assisted. It is capable of producing high current density beam. From the reported literature, it can produce current density in the order of 1 kiloampere per centimeter square. And it is a pulsed electron beam source. So this is the 3D simulation model which we have developed using VISIM multiphysics for the analysis of the electron beam generation part. So this is a hollow cathode. It is a metallic cylinder which is hollow from inside, and it is filled with a neutral argon gas. And on one plane of the hollow cathode, we create an aperture for extraction of the beam. And after a certain gap distance, we have placed the anode. So the cathode is kept at ground voltage, whereas the anode is kept at a high voltage of in the order of 20 and 30 kV for our simulation study. And a trigger is placed inside the hollow cathode cavity for emission of SID electrons. So as we can see that all the dimensions of this hollow cathode are all in mm, and even the emitter diameter is 3 mm, so it is miniaturized. And these are the input parameters which we have used for our study. So this is the electrostatic simulation. So video, it is a video as well. Okay, so it is not working. So, okay. So mainly that video is basically showing that how the electrostatic field is penetrating inside and how the generation of the three species is taking place. So mainly the SID electrons are emitted from this emitter, and that electrons will propagate towards the anode, and while propagation they will neutralize, they will ionize the gas present inside. So we are getting argon ions, and along with that secondary electrons are produced. So this is basically the simulation. This results are shown at the time when the discharge is completed. So we can see that the three species are formed, and the electron beam, a miniaturized electron beam, is extracted from this aperture. So From the results, the first one, we have carried out the study for two voltages. First is 20 kV and second is 30 kV. So what we have observed is the current which we are getting at the anode, it is higher in case of 20 kV. So basically 20 kV also produces a delayed discharge. So basically this is due to the confinement effect, because at 20 kV the time required for discharge of gas is higher compared to that required for 30 kV, because 30 kV voltage is higher and it will produce a quick discharge. So that is why the current density produced is less, as well as the discharge is taking place at a faster time duration compared to that at 20 kV. And since we require higher current density, that's why we are going with 20 kV. Next is the pressure variation. So when we fill the hollow cathode with a argon neutral gas at 1 Pascal pressure, then at that time there is no discharge at all. So that means we need to increase the pressure. When we go to 10 Pascal pressure, that time we are getting a discharge and the current density generated is in this order. But when we go to 20 Pascal, that time of faster breakdown is taking place and the current density is very much high. This is obvious because the mean free path is reduced significantly in case of 20 Pascal. And also the ionization is taking faster. That's why we get a higher number of electrons which get collected at the anode. So moving along with the 20 kV and the 10 Pascal case, because we don't want a faster breakdown, although a high current density is required, which is the case for 10 Pascal. So along with this, we have carried out the further simulation. So the second challenge was electron beam propagation. So for this also, we are using plasma-assisted slow wave structure. So as I mentioned that our aim is to develop a compact high-power terahertz source. So we are, instead of using external magnetic field for focusing the beam, which is generated using pseudospark discharge electron beam source, we are using a plasma-assisted slow wave structure. So basically, it has the advantage that the ion channel-assisted self-focusing electron beam, it propagates over a long distance in the absence of any external magnetic field. So we don't need external magnetic focusing. Then the complexities which are associated with external magnetic focusing are eliminated, and it is suitable to use in combination with a PS discharge based electron beam source, and the compactness of the source we will be able to achieve using the plasma assisted focusing. Although it has these advantages, there are certain limitations associated with it. So first one is the beam energy loss takes place due to collision with the background gas molecules. Then also the beam current loss occurs due to recombination with ions, and the fill factor which we are achieving inside the drift space, it is not constant throughout the drift space. So these are the limitations associated with the plasma assisted focusing. So this is the simulation model created for beam propagation. So this is the slow wave structure. These are the veins of the slow wave structure, and this is the beam emitter. So the region inside the drift space is again filled with a neutral argon gas. So beam is emitted from the emitter. It propagates through this drift space. Via beam impact ionization, so via beam impact ionization, there is a production of argon ions and secondary electrons. So that argon ion basically assists in focusing of the beam, and the focused beam is collected at beam collector. So that is the main concept. The diameter again of the slow wave structure, they are all in millimeter. So, and the input conditions which we are applying is the accelerating voltage we are taking 20 kV from the previous case. The beam current which we are propagating is 1 ampere, and the gas pressure we are studying in the range of 1 to 20 pascals to study the effect of gas mainly. Since we are filling gas and we want to focus the beam using the plasma, that's why the pressure variation we are studying in this case. So ion channel assisted beam focusing. So what happens is when there is no magnetic field initially, at that time the electron beam propagates in a diverging manner through the drift space, and while propagating in that manner, it ionizes the neutrals which are present inside the drift space. So the ions and electrons are generated. After a certain amount of time, an ion channel is created, and these are the secondary electrons which get transversed toward the wall of the interaction structure. So the beam impact ionization results in the ion channel formation, and the ion channel neutralizes the space charge, and in this way we get the plasma assisted electron beam focusing in the absence of any external magnetic field. So these are the simulation results which we have obtained. So when we apply 1 Pascal pressure, so at 10 nanoseconds, what we see, these are the potential profiles. So these potential profiles are plotted along the transverse cross section of the beam propagation direction. So what we observe is at 1 Pascal, the potential well is highly negative. So in this case, a diverged beam will be obtained, which is shown over here. So the corresponding beam profile, this is for 1 Pascal. And for 5 Pascal too, because it is a negative potential present inside the drift space still. So that is why the diverging nature is still remaining. But when we increase the pressure to 10 Pascal, at that time a focused beam is observed. So the beam dia, what is present at the emitter, the same dia we are getting at the collector. And if we increase the pressure higher than 10 Pascal, so at 15 Pascal and 20 Pascal, a positive potential is observed inside the drift space. And we get a beam which is overly focused due to the overly dense production of ion density in that. So this is the table showing the variation in the secondary electron and the ion number density with pressure. So at 1 Pascal, we get a number density in the order of 10 raised to 15, and the ion number density in this case is in the order of 10 raised to 14. When we go to 10 Pascal, then the electron number density is in the range of, again, 10 raised to 15 only. However, the ion number density has increased by 1 order, which is 10 raised to 15. And at 20 Pascal, the variation is further increased, but not highly that amount. So basically, a saturation kind of situation is observed. So to summarize the whole work, a simulation study of pseudospark-driven electron beam source showing high current density electron beam generation through cross-section has been performed by 3D PIC simulation using VSIM multiphysics. And a simulation study for analysis of plasma-assisted electron beam focusing inside the gas-filled drift space of terahertz BW has been performed by 2D PIC method. So for future, we would like to like the study of the beam propagation using a 3D simulation using the same software VSIM multiphysics, and then analysis of the beam wave interaction inside the plasma-assisted drift space. So this will basically involve some more complex phenomenon study in that. And finally, we would like to perform the 3D modeling and simulation of the compact terahertz BW entirely. So these are the references which I have used, and thank you.
Thank you. So you did all these parts on the simulation side. You also presented some electrical signal also, I guess, that you have.
Yes, actually we have generated terahertz, but
Okay.
this is whole simulation study, and the simulation we have not performed of that part of generating the terahertz signal.
Okay.
But terahertz signal is produced experimentally.
What kind of a beam energy that you get?
So beam energy, basically we are applying the voltage which we are applying. It is in the order of 20 kV. So. Yeah, so 20 kV. So roughly we assume that the 20 keV is the energy of the beam which is propagating through the structure. That is why when I took the when I took the 20 kV voltage, so I used the accelerating voltage same as the voltage at which the gap potential was kept.
So what about that? It also interacts with the background and creates some plasma.
Yes, yes.
So in that case, do you have energies of the same order, or do you see like energies are a little different, or you have some broadness?
So right now we have not measured the energy. We have just measured the current density. So the current density, this is the. Yeah, so we were concerned in this case with the current density. So that's why we have not analyzed the energy like we have analyzed the current density. However, we can do it.
So what do you mean by then overly dense ions give them more focusing? Can you go to that part?
Yes, sir. So overly dense means when the beam propagates through the drift space, so at that time a space charge potential is created. When we take a transverse cross section, to the beam direction propagation. So this is basically y, and here in the x-axis you can see this is y. So this is a transverse cross section. So this highly negative mid part which you can see, the whatever differentiation which you can see, that is due to the beam propagation. So at 20 Pascal and 15 Pascal, what we see is instead of initially there was negative potential. So negative potential was due to main dominant part of the electrons. When ions came into picture, that time neutralization took place due to their potential, and when the number density of ions increased to that extent where the neutralization has already completed and still they are generating, so that time the over-focused part occurred, and that time such kind of beam is what we obtained.
So at Pascal you have the positive.
Yes, sir. It is
Yes. So now let us have some questions from the audience. Yes, there is one on the back.
So what is the minimum threshold you keep at the anode for keeping your desired beam current? Because at the low anode voltage, if you increase the pressure, you will get the focused over focused beam.
Yes.
So what is your minimum threshold of your anode voltage to get the desired beam current?
So from what design we have taken, so this is the design, these are the design parameters of our source. So keeping these parameters constant, if we do the study, then what we can see that for 20 kV I am getting a delayed breakdown. So this is a desirable case for high current density, and in terms of pressure I don't want a very quick breakdown. So that's why I am moving on with a 10 Pascal. And 20 kV 10 Pascal situation, when we studied for different time instances, this is the, so this is for like I mentioned, for 20 kV, and this is for different pressures at 10 nanosecond situation. So at that time we are getting for 10 Pascal a focused beam. So this all conditions, if we keep in mind that 10 Pascal is our ideal case and 20 kV is our ideal case. So it depends upon the geometry as well as the input parameters. So it is not like standard that we will get this at this pressure we will be getting the focused beam. It will depend upon the input parameters as well as the geometry of the device.
So with 10 Pascal you have a perfectly quasi-neutral plasma.
So it is giving us a situation of neutralization.
Neutralization, so it's 100% neutralized.
Yeah, almost.
So that you can predict the density corresponding to 10 Pascal. That's it, right?
Density, we can also find density.
So basically that is what he's talking about. Okay, so is there any questions further from the audience? If there is not, then we should thank the speaker again and we conclude this session. Thank you.
Thank you, Prerna. So now I request to our session chair, Dr. Shantanu Karkari, please come on the stage and present a memento to our session speaker, Dr. Vibhuti Bhushan Sahu. I also invite our convener, Dr. Nishant Sisse, to present a memento to our session chair, Dr. Shantanu Karkari. Now I invite all oral talk presenter from this session to kindly come on the stage for the group photograph. Yes, sir. Thank you, sir. Now we have a poster session 2, but just for the 30 minutes. Before that, I just want to announcement. Today we have a gala dinner at 8 p.m. at Hotel CIJ Indore. So, and transport will depart around 7:30 to 7:45. So please be here. So this poster session will be only for 30 minutes, and after that we will have our last session for today. Okay, so just for 30 minutes. So all the best for all poster presenter.
Hello, check. Hello, check.
Our final session for today is dedicated to non-thermal plasma and application, a rapidly growing field in the plasma, chaired by Dr. Vibhuti Bhushan Sahu. Sir, please start the session.
Okay, so good evening to all. This is the final session for today. To start with, the first speaker. So the first invited talk by Dr. Neeraj Kumar from CSAR Siri Pilani. So I would like to invite Dr. Neeraj Kumar to come up. I will briefly highlight the bio sketch of Dr. Kumar. Dr. Kumar is a senior principal scientist at CSAR Siri Pilani, India. He is leading a research team which is dedicated to the development of novel sheet electron driven high power terahertz sources with a focus on the development of industrial and strategic applications. He is leading national and international collaborative projects on high power terahertz technology with a combined value exceeding 100 million funds focused on advancing the field of vacuum electron devices. So I would like to invite Dr. Neeraj Kumar to start this talk of this session. So let us give a big applause to Dr. Kumar.
Yeah,
so
Thank you everyone. Good evening one and all. First of all, I would like to thank organizer, especially Dr. Nishanji, for inviting me for this particular Plasma Scholars Colloquium. So in next 25 minutes to 30 minutes, I will present whatever we are doing R&D on cold plasma based electron beam devices, where we have used plasma to focus the electron beam and to generate the electron beam, as well as for generation of high power microwave signal. At the same time, we have also extended this work for the generation of high power terahertz signal. We have used the electron beam, means we have developed a backward wave oscillator. So all these things we will cover in next 25 to 30 minutes. I will give a brief introduction about CSAR Siri. Most of you are knowing about CSIR Siri. Then specific contributions, what we have made in last, I will say 5 years, 6 years, related to work, simulation one and experimental work, although my PhD student, Ms. Prerna, has already presented the simulation part of the electron beam source. So I will mainly focus on the experimental development related to this. So CSIR Siri is particularly one of the lab of CSIR. It's in Rajasthan. And CSIR is having 37 labs, where CSIR is a society, where Prime Minister is the president of that society and Vice President is Science and Technology Minister. And under that, there are 37 labs where individual directors are leading. This is the campus of CSIR Siri, which is at Pilani, Rajasthan. So it started way back in 1953, 21st September 1953, where the scientific strength as of now it's of 80 scientists are there, permanent staff, means including technical and other admin staff. Then through ACSIR, which is the Academy of Scientific and Innovative Research, CSIR has started its own university in year 2011, where they can award MTech degree as well as PhD degree through their in-house research program. So across the 37 labs, these are the center of ACSIR, Academy of Scientific and Innovative Research. So we have a pool of 60 PhD research scholars as of now, who are means in different years, like first year, second year. And there are GRF project researcher. So this is the strength of Siri Pilani. Now coming back to the main topic of this particular talk, what we are doing, we have developed plasma assisted slow wave oscillator. And by slow wave oscillator, what I mean, it's a backward wave oscillator which utilizes ion focusing mechanism for the beam transport in absence of guiding magnetic field. Like most of the vacuum electron devices, they utilize external magnetic field to focus the electron. Either if we will name backward wave oscillator, klystron, TWT, that requires external magnetic field to focus the electron beam. And all these Cherenkov device where the electron beam need to be energetic as well as focused to transfer its energy to the RF wave. So for transferring its energy in optimum phase to the RF wave, we need to focus the electron beam, we need to generate the high current density electron beam as well as high energy electron beam. There is another method where, but as we all know, putting the electromagnet or permanent magnet over the slow structure to focus the electron beam, it's a challenging task, or I will say it's a complex scenario. So to eliminate this, what we have done, we have utilized plasma to focus the electron beam, which eliminated the requirement of external magnetic field to focus the electron beam. So instead of having external magnetic field over the slow wave structure to focus the electron beam, what we are doing, we are utilizing beam impact ionization to create the plasma, where initially there is a neutral gas, like gas, argon gas we are using. So argon gas is filled inside the electron gun as well as slow wave structure. Finally, once the electron beam is coming out, it is ionizing the gas molecule to create the ion channel. So first part, there we all know there will be diverging force due to the Coulombic force, there will be repulsion of the electron beam. So for getting focused beam, you need to converge this. So how to converge this? This is the Lorentz force equation we all are knowing. So it's electric field will give you the acceleration, magnetic field will give you the direction. This is the common case for vacuum electron devices. But if we will utilize plasma, where there will be ion generation due to the beam impact ionization, then instead of having this magnetic field, we can propagate the electron beam by creating the ion channel, which I can present in this slide. Like Prerna already, she has presented this. Electron beam will impact the neutrals and it will produce secondary electrons as well as ions. Since we are doing short pulse operation, like for typically we are generating microwave signal of 30-40 nanosecond. So we can consider during this particular time duration, ions movement will be immobile as compared to electron beam movement. That's why ultimately what you will get, a ion channel to focus the electron beam. Due to the space channel utilization effect of positive ion channel, you will get a focused electron beam and large amount of high current density, which can propagate because it will also enhance the space charge limiting current. So finally, the beam which will come out from the electron gun, that will have high current density and high energy. Although there will be beam loss, because beam current in VED, like vacuum electron devices with focusing of external magnetic field, you can get good transmission up to 99% also in TWT, magnetron or something like this. But in this case, you will have typically loss of 20 to 30% in beam current, but you are eliminating the requirement of external magnetic field, which is eliminating the another power supply to produce that magnetic field, right? Because with electromagnet, you need to have another additional power supply to create that magnetic field intensity, which is desirable, right? Or you can use permanent magnet. But again, permanent magnet have their own limitation in terms of propagating through sheet electron beam. Through permanent magnetron, permanent magnet, it will lead to dichotron instability. Like beam will have shear effect. The velocity in the x direction and y direction will have different component. While for transferring the electron beam energy to the RF wave, it requires need to be focused and the component, it should be intact. Means the beam should have the focused nature as well as the energy component should be intact so that it will transfer its energy to the RF wave. Because we are developing oscillator, there is no such external RF input. From the structure dimension, the noise is getting created and that noise is getting amplified based on the energy level of the electron beam. Means that we decide based on the structural dimension of the slow wave structure. This what initial simulation what we did. So in vacuum case, there will be natural divergence as you can see. Then 60 millitorr typically the beam gets focused. And already Prerna has presented another part of this. So this particular hollow cathode and anode schematic is there. When we apply, we will keep hollow cathode at 0 potential or minus negative, or then anode at some positive potential. So once we will apply the voltage across this, field will penetrate through this aperture. this aperture, and there are two phases of the electron beam which will come out of this this hollow cathode PC gun. There are two phases, one what we say hollow cathode phase, and second one is conductive phase. In hollow cathode phase, you can see the current is low, but the accelerating potential is high. So in that case, the beam current density is low, but the energy level is very high, while in conductive phase, there is low energy, but the current is high. As you can see, the microwave generation, means the RF generation, will occur only in hollow cathode phase, not in conductive phase. So we need to optimize this hollow cathode phase configuration so that we will get high power microwave output in this particular phase only, not in conductive phase. So you require high energy electron beam with some limitation of low current density value, it will work. But it can't be vice versa, like high current density and low means low voltage, low accelerating potential, the microwave generation will be almost negligible. So for having this Cherenkov device where you need to match the electron beam velocity with the RF phase velocity, you need to have high accelerating potential which you will apply between the cathode and anode. That is the schematic, means that is the process which is behind this kind of extraction. So based on this, we did some optimization like configuration of different single gap, single aperture. This is the case where single gap is there, means between cathode and anode, there is only one gap, one insulator gap, and then single aperture on this anode. Then single gap multi-aperture to generate multiple channels of electron beam. We have created multi-aperture on the anode surface, so that we will have high fill factor as compared to single aperture of that equivalent size. Then single gap sheet aperture, this I will discuss later on. Multi-gap single structure. Instead of this having single breakdown, as you can see, there is a single gap breakdown between cathode and anode. We need to have multiple breakdowns, successive breakdown, gas breakdown, so that we can have large duration of energetic part of the electron beam. If there will be single breakdown, single phase breakdown, there will be sudden transmission from the higher cathode voltage to the ground potential, because the cathode anode gap will get collapsed due to the formation of this conductive channel. So if you want to delay it, you can put it by placing some floating anodes as well as insulators. So this is the multi-gap configuration, like in between first cathode will be there, then insulator, then floating anode. Why we are saying it's floating anode? Because you are not applying any external potential to that anode. So there will be insulator, anode, then finally anode will be there. So in this way, you will have 3 gap structure where 3 insulators are there and 2 floating anodes are there. So with this kind of configuration, these are the experimental value which we have tested, and this what we have published in different journals. So based on this, because we initiated this particular development for X-band BWO, plasma assisted X-band 10 to 12 gigahertz backward wave oscillator what we developed. So what we did, we created this one single aperture on hollow cathode. Since for this BWO structure, the fill factor what we were requiring, that should be of 10 mm. But if we will create 10 mm of aperture on this particular hollow cathode surface, there will be large field penetration which will lead to ultimate faster breakdown, which we don't require. That's why what we did, we slowly converted this 3 mm to with this kind of tapered structure. As you can see, this is the perspex structure. This gray color part is the insulator one, while this copper part which is inserted in between, that is the floating anode terminal. So there is a tapered multi-gap structure where we are slowly converting 3 mm electron beam to the 10 mm size multi-aperture configuration. This particular anode aperture, this is the anode disk through on which we have created this multi-aperture, so that we can get high current density, high energy, as well as we should get fill factor of typically around 70% inside the slow wave structure. So that was the design parameter which we required to develop X-band BWO, X-band plasma assisted backward wave oscillator. This is the developed X-band plasma-assisted backward oscillator. As you can see, this is the hollow cathode part. This is the tapered multi-gap, multi-aperture part. This is the anode terminal. Then inside this particular, I will say, I section, this kind of periodic rippled wall slow structures are there to confine the plasma, as well as it will also have the RF generation in this part. Means we will amplify by the electron beam will transfer its energy to the RF wave. And in this particular plasma-assisted slow oscillator, we have not used any external magnetic field to focus the electron beam. So we carried out the testing also. As you can see, this is the applied gap voltage, which we have applied between cathode and anode. And there, due to this multi-gap structure and tapered structure, there was multi-hollow cathode phase formation, like low current but high energy. And finally, this conductive phase. In this particular phase, we generated this RF signal. And this, then we carried out the FFT to confirm that the generated signal in X band, what we found that typically its signal is varying between 10 to 11.7 gigahertz, and the pulse duration is of 40 nanosecond. That is the limitation of such kind of pulse source, because you will have breakdown between cathode and anode potential. So you can't have continuous emission of RF signal from such kind of source, but you can always operate on PRF based on the application. Like means the breakdown can occur in PRF mode up to 100 Hertz or something like this. Now there is a requirement of terahertz VWO, means terahertz source, high power terahertz source. So as we all know, as the frequency increases, the structure dimension will keep on reducing, right? So for 0.1 terahertz structure, typically I will tell you the slow structure size, that will be in 200 micron size. So creating that kind of structure with good surface finish, which my another PhD student will also present that development part, so I will not cover that part in this presentation. So that slow wave structure, where the dimension is of 269 micron, and the point of importance is that you need to create this surface structure with good surface roughness value, and the dimensional deviation should be as less than 10 micron. In the periodicity, means there will be multiple structure, not a single cavity, there will be multiple structure, slow wave structure, to slow down the RF wave, and that will interact with the electron wave. Again, the same concept of Cherenkov device. So we created this sheet electron beam. That time when we created, since we have not measured the profile of the sheet electron, no one was believing that through plasma cathode electron gun, how you have created this sheet electron beam. Then taking the image of this 40-50 nanosecond electron beam was difficult task. We all know we deal with such kind of measurement setup, right? So what we did, we took the concept of dielectric charging effect. We took the same image of silicon dioxide wafer before the bombardment of the electron beam, after the bombardment of the electron beam. As you can see, what we got, it was the aperture size 7 mm cross 1 mm. Without any using external magnetic field, this beam has propagated for more than 20 centimeter, and the maximum deviation along the long side direction was 22% and 19%. So this is the experimental image what we received after propagation of the sheet electron beam inside the plasma assisted drift space. So there was no such external magnetic field, because with sheet electron beam, if you will apply external magnetic field, it will lead to dichotron instability effect. Means velocity will have the kink effect. So on the corner, velocity, the electron velocity will be different for in x direction, in y direction, where the z direction is the propagation direction. So we utilize the effect of plasma to focus, and this is what I was talking about. So before the bombardment of the electron beam, this is the same image of the silicon dioxide wafer. After the bombardment of the electron beam, this is the same image of the generated sheet electron beam and propagated sheet electron beam. So we utilizes this particular concept for high power sub-terahertz source generation, where there were 3 challenges. Already one challenge Prerna has covered, and second challenge to surface roughness with 100 nanometer, which Sahil will cover, and finally this sub-terahertz source requirement to develop all the component with the alignment of less than 0.1 degree. That was the crucial. So what we did, starting with this sheet electron beam source, which we have already developed, and it has been developed in collaboration with IPR Gandhinagar with the association of Dr. Raj Singh. So we have developed the first braced version of miniaturized sheet electron beam source, plasma assisted sheet electron beam source, and this what we delivered as per the project requirement to in 2022 to IPR Gandhinagar. And this was the supported by BRNS for carrying out this research work jointly with. Then second part, beam will propagate between this. This is the upper plate, this is the upper plate, and this is the lower plate. As you can see, the wall thickness is of 269 micron, means 0.269 mm. So the beam will propagate over it, and this is the different methods through which we have created this structure. This is the final optimized one, what we have created. And the surface roughness, what we have achieved, it's 60 nanometer, which is very much acceptable for if you are propagating of frequency 0.1 terahertz. The detailed analysis Sahil will present that 0.1 terahertz, if you throw skin depth value related to this particular surface roughness, that is in order of 200 nanometer to 150 nanometer in W band. So with respect to that, if you are using copper material, because we require high conductive material, so the achieved dimension means as surface roughness is 60 nanometer, while the dimensional deviation, as we have performed the same image, you can see there is very good accuracy, and the dimensional deviation is less than 10 micron. So it is affecting the frequency response by around, I will say, 0.1 gigahertz, which is very less as compared to the generated frequency. This is the cold test, what we have carried out for this developed structure. This is the final integrated structure for the third challenge, because we have created all the components on a single plate, like beam adapter, where circular beam is getting converted into sheet electron beam. Second, this interaction structure, slow wave interaction structure. Finally, this collector, spent beam collector, and that is also acting as launching port, means coupler, which will take out the RF signal for application part. So this particular structure we have developed in-house at CSAR Siri, and there was the requirement of sub-terahertz BWO by DRDO. It was the sponsored project from DRDO. So we developed for them, we delivered this particular source, and I will be happy to tell you this, the status is that we have generated, although I have not presented the RF due to some patent issue and DRDO issue, but the status is that the peak power what we have achieved for 0.1 terahertz, it's 10 watt, more than 10 watt, pulse width 30 nanosecond, and the frequency which we have generated, we have measured, it's near about 0.1 terahertz. And this is the typical source which we have developed at CSAR Siri, and the typical dimension is 9-inch cross 6-inch. So it's a portable source apart from power supply. So this pulse source we have, and already the patent has been filed on this. So I would like to acknowledge, because without their contribution, this work was not possible. So first of all, director CSAR Siri, then PhD student, especially Prerna and Sahil, then colleagues at CSAR Siri. Since it requires interdisciplinary research, you need to deal with plasma, you need to have power supply matching and all. So there is active researcher, active senior scientist at our lab, Dr. Anand Abhishek, he is also working in this along with us. Then we are having collaboration in terahertz technology domain, especially in terahertz technology domain with Professor Sri Ganesh Prabhu sir, then Dr. Raj Singh sir, with whom we started our first project of sheet electron beam source, plasma assisted sheet electron beam source. Then from Nimish Dikshit, Dr. Nimish Dikshit ji from DRDO. Then we are also having a joint collaborative project with the Kotelnikov Institute of Radio Engineering and Electronics. Then Professor ADR Phelps, who introduced us with this kind of pseudo-spark discharge concept, and that was his major contribution. Then Dr. Fabian, he is working on terahertz technology domain for application part, so where we can utilize such kind of portable source for NDT application, non-destructive testing application. Then Professor Hermat Rosker, recently we organized on terahertz technology and application Indo-German workshop along with them last year. It was in October at CSAR Siri. So with this, I would like to, these are our future research directions. Like we would like to have this plasma assisted terahertz source. We would like to do end-to-end simulation, and Prerna is working on that. Advanced manufacturing technique where Sahil is working, and we would like to develop this sealed off. The source what you have seen here, this is not the brazed one. This is the flange based assemblies there. But for actual application, for actual, I will say, industrial application or strategic application, you need to come up with brazed version vacuum. So we are having all those facility at CSAR series where we can develop such kind of vacuum-based sub-terahertz BWO, where vacuum leakage will not be there. So for actual application, we have to come up with sealed off and compact version. And with the present capability, what I can say here that up to 0.65 terahertz we can make an attempt in development of such kind of source, and this will be the ultimate system requirement, means where we would like to work. So these are the future research directions. Thank you. I would be very happy to answer your questions.
Thank you, Dr. Kumar, for your nice overview and wonderful journey of developing such beam sources. Now it is time to have question from the audience. Okay.
Hello, yeah, it's a nice one. So the electron beam accelerated and then it passes through some wigglers or something like that. And then you have some kind of a dump also, right? It should be vacuum.
Yes.
So how you have done that?
Oh, sorry. I will explain in this part. Electron beam is coming from this portion, sir, and this it is propagating this slow wave structure part, so that the beam velocity should match. And there is a spent beam collector, which is the tapered region. So spent beam is getting collected over the side walls of this collector.
And the other side is glass?
Other side is quartz window.
Quartz window. Okay. And you mentioned that you have make some groove with some micrometer. The wigglers or something.
Yeah. That is the slow structure.
From a single piece.
Yeah, this one is the slow structure, sir. Yeah, this one.
So
this, yeah.
What was the dimension like?
Yeah, these are the dimension. Like this wall is of 269 micron. Sorry, I am not able to focus. 269 micron, and the width is of 1.786 mm. Then 658 is the vent depth.
Yeah.
Based on 0.1 terahertz frequency, we have took this design.
This was done by laser?
No, milling, micro milling.
Okay. Thank you.
To get this surface roughness.
Okay.
The detailed part Sahil will present, sir, in this particular session only.
Okay. Any more question from student or audience? Okay.
Thank you.
I have few questions. So you have told your goal is to generate slow wave structure.
Slow wave oscillator.
Oscillator.
Yeah.
So how you are ensuring slow wave features?
Okay. So like we are having periodic structure, right? If you will take a simple waveguide, the RF will propagate with the speed of light. So finally, when you are giving a longer path through creating these vein structure, the RF which will propagate through this slow wave structure, the axial velocity will get reduced. So you are basically slowing down the axial velocity of that RF wave. So finally, the phase velocity of the RF wave should be in synchronism with the beam velocity. That's why with creating such kind of periodic structure, where you are using giving longer path by putting inserting some veins inside the waveguide structure, you are slowing down the RF wave.
Okay. Another question relevant to frequency.
Yeah.
So you are generating beams.
We are generating electron beam and terahertz signal.
Okay. So how you are ensuring that frequency?
Yeah. So with this structure, you can have a dispersion diagram, right, sir? Omega beta diagram. Like omega will be the frequency and beta will be the propagation constant. So propagation constant will depend on the beam velocity. So if you want to generate 0.1 terahertz, so you need to have a specific voltage which you will apply between the cathode and anode to accelerate the electron beam with that energy. So if you want to have suppose 0.09 terahertz, then you need to defer the voltage, or you need to change the voltage, applied gap voltage. So that accelerating potential is giving energy to the electron beam, and that should be in synchronism with the phase velocity, which from dispersion relation we can calculate the phase velocity.
Okay, thank you. And how many dielectrics you are going to feed? So how you are deciding?
Three gap. Okay, dielectrics gap structure you are saying?
Yes.
Three gaps.
Okay.
Because we want to operate in the range of 20 to 30 kV. So based on the breakdown curve, we have estimated that 3 gaps are sufficient to maintain this hollow cathode nature as well as I will say energetic part of the electron beam.
Okay.
If we will increase the voltage, we have to increase the number of gaps.
Okay. Is there any question? Okay. If there is no question, let us thanks the speaker again. Now we'll move to, now there are several contributory talk. So first talk to be delivered Rohit Sharma from FCIPT, Gandhinagar. So you have 15 minutes plus 5 minutes question and answer.
Is it on?
This is forward, this is backward, and if you continue press for a second, then it will be like a lesson.
Okay, can I check once? Okay, okay. Okay. Good evening, everyone, and I would like to thank PSSI committee for giving me a chance to present my work over here. This work is done with the Dr. Mukesh Ranjan, me, along with Prashant, Poonam, and Suraj. The title of this talk is decided the production of super hydrophobic jute fabric using argon plasma and HDTMS coating. In this work, I'm giving a brief introduction about wettability and the textiles, and then follow up with the experimental sections, and I'm going to discuss some of the results related, in which I'm going to details about how the plasma affected the super hydrophobic properties of the jute. So the wettability is basically the ability of a liquid to make a contact with the solid surface and make a balance between the intermolecular forces such as adhesive and cohesive forces. So the best way to measure the wettability of a surface is a contact angle measurement. Based on these contact angle measurement, we classify the surfaces into three surfaces. Hydrophilic, hydrophobic, and super hydrophobic. If the contact angle is less than 90 degrees, the surface is supposed to be hydrophilic in nature, whereas if it is equal to 90 degree or less than 150 degree, it is supposed to be hydrophobic, and if the contact angle is greater than 150 degree, it is supposed to be a super hydrophobic in nature. The several examples has been existed in the nature, such as lotus leaf, the butterfly wings, rose petal, and the skin of an humpback whale. The two processes can be, there is two factors that majorly affect the super hydrophobic properties of the any surface, such as the surface roughness and the surface energy. So if the surface energy is minimum, the more chances are there that the surface is super hydrophobic in nature. So related to the textile, surface wettability plays a crucial role in the textile application, such as influencing it can be used for the water resistance, for durability, comfort, and the self-cleaning in nature. The natural fibers such as cotton, angora wool, hemp are hydrophilic in nature generally. They can be made hydrophobic by using surface modifications. And out of that, we have selected the jute because jute has an affinity for the moistures which resist its use for many applications. At 20 degrees of temperature and 60% of humidity, jute has a 12.5% of moisture. Whereas India is the largest producer of jute, and after Bangladesh, India, mainly jute has been grown in West Bengal, Bihar, Assam, and Odisha. And in up to 2023, India produced 1.97 million ton of the jute, and jute can be used for the various applications such as bags, niche products, sackings, and in the household goods. Whereas the jute, this diagram shows jute has a number of layers, such as cell wall, primary wall, and secondary wall. Due to that, this layer of the jute can easily be modified because the jute layers consist, the major constituents of jutes are lignin, pectin, and hemicellulose and cellulose. Because of that, it is easy to modify the texture of the jute. So for texturing of the jute, we have placed a fabric of jute, we have placed the fabric of jute in the argon plasma, and in this the system contains the SS electrode of 10 centimeter, and it is electrode is basically powered with the connected with the RF power supply, and we have treated the jute with 30 watt, 60 watt and 90 watt and exposed the jute for 5, 10 and 15 minutes. And further, we treated the jute with the chemicals such as hexadecyl trimethoxysilane. For that, we have prepared a 2% ethanol solution and stir it for 90 minutes and then dry it for 120 degrees Celsius. And then you can see over here, there's a water droplets over the jute surface which is not absorbed. And for this, the adhesion of this chemical, basically when it is mixed with ethanol, there's a two process happens, hydrolysis and the condensation. In the hydrolysis process, this HDD-TMS breaks into the methoxysilane, and this methoxysilane get attached with the jute surface. As after the plasma treatment, the jute has a more active sites, which is due to which these OH groups get attached with this phenol and forms a SiO bond over the jute surface. To confirm this, we have performed the FTIR spectroscopy. In the FTIR spectroscopy, there's a major bonds occur at such as OH bond, which is around the 3200, and then there's a CH2 bond, which is around 2900. This table signifies the number of constituents that is associated with the jute, such as cellulose, hemicellulose, lignin, wax, and the cellulose that peaks around 1060 degree. The major changes we have seen in the CH2 bond after bombarding it with the argon plasma, the CH2 bond has been disrupt, and with the increase in power plasma and the time, we can see that bare jute has a highest intensity of CH2 bond, whereas with the increase there is a loss of CH2 bond. But when we coat it with the CH2 HDTMS molecule, we can see that there is a increase in the CH2 bond. Again, it starts to recover, but it not fully recovered. It's not able to recover the initial position of that CH2 bond, whatever present in this sample. Further, we have done the FESM. We have captured the FESM micrographs in which the bare jute, the figure A, this all FESM figures are for 10 minutes of exposure time, and this the bare jute, there is a waxy layer and the debris are present on the jute surface, whereas for 30 watt at 10 minutes, we can see there is a middle lamella and the fibrillary structure of the jute can be easily visible. With the increase in power and time, we can see there is a porous network can be visible due to the removal of the material, and this removal of the material is basically generate an additional surface roughness on the jute surface. Whereas when it coated with the HDTMS solution, this there is some charging is occurred due to the insulating behavior of this HDTMS molecule. Whereas further on 90 watt 10 minute, we can see this porous structure is filled with the HDTMS molecule. So further, this superhydrophobic properties, for superhydrophobic properties, we have captured the contact angle, and we can see for bare, this contact angle has been captured within a 10 to 15 seconds of window, and the bare jute having a contact angle of 130 degree, and whereas with the HDTMS, so we are getting approximately 160 degree. We can see with the change in when we expose it with the plasma, we can see there is a contact angle has been increased with the exposure time, whereas for the HDTMS solution there is not much change has been observed, and we can see the maximum contact angle has been observed for the 90 watt 10 minutes along with the HDTMS coated sample. To study the stability of the samples, we have recorded the contact angle for a month, and we can see there is not much change in the contact angle, which suggested that the HDTMS coating and the plasma enhances the stability of the jute samples. So further, we have recorded the dewetting time. So the dewetting time basically defined as the ability or the time which a liquid droplet takes to capture liquid droplet tries to absorb on the surface, in which we have added some ink to the water, and this perfectly spherical water droplet can be seen on the jute surface, and also the stain mark has been reduced after the treating it with the plasma, treating the jute with the plasma. There's major change has been occurred when we treated it with the jute. There's 200 times enhancement in the dewetting time for the plasma treated jute has been observed, whereas there's a less, almost 15 minutes of enhancement can be observed for bare jute to the plasma treated jute along with the HDTMS coating. Now further, for self-cleaning behavior, we have studied the adhesive force analysis. In this, we have dropped a 20 microliter of droplet on the jute surface and tilted the surface, and this droplet has been starts to roll. Whereas for bare jute and up to 30 watt treated jute, this droplet doesn't roll off, and the adhesive force is, there's a clear trend of decreasing adhesive force can be observed for the plasma treated jute from 60 to 90 watt, whereas this decrement can be seen as the textures has been generated, which we have seen in the FESM images, which majorly resulted into this roll-off behavior of the jute, whereas with the HGTMS, the minimum adhesive force is observed for 60 watt 10 minutes, which is 84.3 watt. This absurd behavior is there in this HGTMS coated jute along with the plasma treatment, because this coating is not uniformly filled along this porous network. So further, with this, I would like to conclude this work. Here we have treated the jute with the argon plasma and coated with the 2% of HGTMS solution. And the same image reveal that this jute having natural wax and the debris are removed after the plasma treatment. And the texture is generated after the plasma treatment, which resulted into the increase in the superhydrophobicity of the jute. And the FTIR spectra reveals that there is a major change occur along the CH2 bond and the OH functional bonds. And this CH2 bonds recover after the HGTMS because it has a hydrocarbonic groups in this molecule. And the highest contact angle we have observed for 90 watt treated jute along with the HGTMS solution. And this result could pave a way to improve the de-wetting and self-cleaning behavior of the jute in the upcoming textile industry. So with this, I would like to acknowledge FCIPT, IPR for providing the facility for this work. And this is the research group in which I am working. And I would like to acknowledge the other members of the group which are not presented in this image. Thank you. So questions are welcome if it's there.
Thank you for your nice presentation. Hydrophobic cotton based on HDTMS.
Yes, sir.
Okay, now session is open.
Here.
So it's in vacuum system.
Yeah, what is the pressure?
Sorry, sir.
Pressure.
So base pressure is working pressure is 0.06 millibar.
And what is the comparison between plasma and HDTMS and only HDTMS?
With the only HGTMS is there is no the adhesion is not very proper. So after a certain time, this it absorbs the water molecules as the coating has been removed. So it improves the adhesion of the HGTMS molecule with the HGT surface.
So adhesion is due to the plasma cleaning effect or some other process is happening?
The cleaning effect, and also it removes the layers of the material, such as it removes the cellulose or waxy layer. So this removal of the waxy layer is basically.
Okay.
So you are putting the gas in flowing condition or in vacuum, or stable gas is there?
Stable gas is there.
So have you tried with different gas?
No, I haven't tried with the different gas, but with the oxygen or a nitrogen plasma, it basically resulted into the hydrophilic in nature. Because with the oxygen, it increased the OH group. So this hydroxyl group resulted into the hydrophilic nature. So the contact angle will be reduced as per the literature.
Okay.
Okay. Any more question? Okay.
So I'm not able to hear you.
Hello.
Yes.
Nice presentation, sir. My question is that what was the thickness of the jute that you have used?
That's a commercial jute. We haven't procured it. We have taken it from the industry, and the density of this jute is 290 grams per centimeter cube.
Okay. And
so they have provided this information.
What was the size of jute?
The sample we have treated is 5 cross 5 centimeter square.
Okay. Thank you.
Okay. One more question.
Thank you, ma'am.
Okay.
So she's asking something.
Oh, okay. Please.
This procedure you have done for jute.
Yes, ma'am.
Do you think that same procedure will work for some other fabric, say for example, say a wool fabric?
It might work, but we have to optimize the process because the texture and the functional group in the different fabrics are different. So we have to go for like for same thing. The one have been treated the cotton, but they blended it with some some other material to sustain this change. So sometimes
The reason I asked you this is you are anyway putting that
HDMS molecule over there.
So that is actually playing the role, right? The
For
etching
super
part-
hydrophobicity, it is playing a role, but plasma treatment itself enhances the hydrophobic nature because with the plasma treatment, we get a contact angle of up to 150 or 154. So it is also making it a super hydrophobic kind of thing. But it is not stable for this. Like we have dipped this sample into the water with only the plasma treated sample, it is hardly sustained for 2 or 3 hours. But with HDMS, it's sustained for more than 2 days. It is floating in the water for 2 days.
So what I have actually seen is that when you immerse the jute in water, it gets wrinkled. It wrinkles, right?
Yeah, it swells.
So in this case, you are putting the jute in this particular liquid.
In this, no, there's because the HDMS, as soon as it forms a HDMS coating, that is why we are not using water for the hydrolysis. We are using ethanol. So because if we dipped in a water, it will swell the fiber.
Okay. So your HDTMS, it's well known for
sir,
hydrophobic.
It is hydrophobic.
It is already hydrophobic nature.
Yes, sir.
But what you have shown is plasma treatment is more advantageous.
Yes, sir.
Okay. So how have you optimized your condition? You have just vary the power.
Vary the power and the time, exposure time. We play with the 2 parameters.
Okay. You have not vary the pressure and gas flow rate.
No, we don't vary the pressure. We have taken the pressure from the literature.
Again, one more thing. You have not analyzed surface analysis.
Surface analysis? We have done it with the FESM. With the XPS or something, we didn't do that.
No, surface energy analysis.
No, sir, we haven't do that.
Okay, it will give you more information.
Yes, sir.
Okay.
We have tried that, but other liquids like ethanol or non-decyl volume, they get adsorbed on the surface. The polar molecules get adsorbed on the surface. So we are not able to get it with the goniometer. So that is why we are not able to get this.
So you have not analyzed role of silection.
Role of selection of?
Silection.
Sorry, I didn't.
Silicon, oxygen, radicals.
Phenol group that is forming over there. No, sir. I haven't studied that. The reaction mechanism itself says that when it get hydrolysis, it forms a methoxysilane, and this methoxysilane get attached with the OH group present on the jute surface. So that is the reaction mechanism over which we are saying that phenol has been form a layer over this surface.
Okay. So final question.
Yes.
So are you telling it as polymerization type or some kind of plasma treatment?
Initially, it is a plasma treatment but to sustain it for a longer days, we have to have some kind of polymeric layer over there.
Okay.
But because the plasma treatment sample can up to sustain for like 60 days, not more than that. But we can't dip it in the solution. For dipping it and keeping it for 3-4 days, we need additional layer.
Okay. Okay. Thank you very much. Okay.
Sir, there's one more question.
Okay. One more last question.
Okay, nice talk. So does it produces permanent change in the properties of jute or it is temporary?
No, the texture generated over the jute is permanent because these textures are presented for more than 3 months on the sample.
Okay, so it maintained the property which are you analyzed at T is equals to 0.
Yeah.
Okay.
But the problem is the jute is subjected to the atmospheric ambient. So your properties get altered as it, put it in the ambience atmosphere.
So there is certain shelf life.
Yeah.
Okay.
So definitely.
Okay, thank you.
Okay. So let us thank the speaker again.
Thank you, sir.
Now I would like to invite next speaker, Yasik Basu Malik, IIT Delhi, to start the presentation.
Okay.
This is for forward, this is backward. Then you continue that for 2 seconds, and then you point to laser.
Okay. Okay. Thank you. This one? Okay. Good evening, everyone. I'd like to thank organizers for giving me opportunity to speak on my work, that is development and efficacy of sub-radio frequency atmospheric pressure plasma jets and its potential interaction to the liquids. So starting with, the talk will be discussed in following topics like importance of atmospheric plasmas and subsequent challenges, factors influencing plasma jet, novel sub-RF source, the development of a novel sub-RF source, plasma jet and source characterization, along with the quantification and qualitative of gas phase and liquid phase reactive species, and a word on perspective of plasma-liquid interaction in further applications. So starting with atmospheric plasmas. Atmospheric plasmas are miniaturized devices which consist of which have typical dimensions of micrometers to several centimeters, having energetic ions and electrons, which leads to reactive species, sharp electric field gradient, and UV radiation. So the device, advantage of the device is that it can be used in a localized treatment of samples, portable and handle, can be used in heat-sensitive applications because of its cold nature, cost-effective, energy-efficient, and can be used in complex samples. And due to atmospheric ambient conditions, so redundant vacuum peripheral, so cost effective in terms of that, and can be used in vacuum incompatible substrates. So traditionally, atmospheric plasmas are classified based on temperatures as thermal and non-thermal plasmas. Thermal plasmas having high heat content can be used for waste treatment, and for non-thermal plasmas, biomedical and heat-sensitive applications are utilized. So this is typically atmospheric plasmas are in surface DVD discharges and plasma jet. This plasma jet structure is commonly used because of the ambient plume, the plasma plume touching the water surface, any substrate. This is one, let's say, when talking on liquid, so it is interacting with liquid. So three phenomena, like in a gas phase, boundary layer, and liquid phase, which will be here in the case of liquid. So what makes atmospheric plasma versatile is the presence of this highly oxidative reactive species from nitrogen oxide, OH, H2O2, peroxide, and many more. So reactive species, the utilization of reactive species make it important for use in several applications. So some word on challenges. So obviously in atmospheric pressure you have, as per the Paschen law, we know, so the voltage requirement would be in some kilovolts for a gap of millimeters as well. And as we move towards atmospheric pressure, the gas temperature and electron temperatures close to thermalize. So which makes it difficult to generate a cold plasma. In atmospheric plasma, due to high collisionality, the elementary processes such as elastic collision, excitation, and dissociation occurs in the time scale of some picoseconds to microsecond with all the radical chemistry that we are intended to see. So which triggers thermal instability. So what it is, it's with a temporal variation or any slight change in electron density leads to gas temperature variation, which leads to increment in reduced electric field, increase in collisional frequency, and then again. So it becomes a vicious cycle which leads to runaway electron behavior, Joule heating, and gas heating. So there should be, so in literature, people use certain strategies such as nanosecond pulse firing, pulse modulation over base frequencies, gas flow admixture, and dielectric covering. So what it does is with nanosecond pulse firing, we are within the time scale limits, and pulse modulation to reduce the gas heating of the plasmas. With gas flow admixture is the cooling effect, and the dielectric covering is to reduce the current, sudden changes current. So for typically with based on sources, kilohertz plasmas and RF plasmas are mostly commonly used. For kilohertz plasmas, moderate electron density, low electron temperatures are obtained, but we can get a cold plasma less than 50 degrees centigrade. And for RF plasmas, they have high electron density with high temperature. So these two for high electron and high temperature and density helps to get more radical chemistries. Whereas on the downside, the RF plasmas are non-thermal. Non-thermal still means they are temperatures more than 70 degrees and so. Whereas in kilohertz plasma, we get a relatively lower than 50 degrees centigrade. Plume length for helium gas, kilohertz plasma exhibit very high plume lengths, whereas for RF plasma, this is argon plasma. For RF plasma, it is very short, typically leads to 5 to 6 mm. Poor power efficiency, whereas RF, we know it's of better power efficiency. So a novel source has been thought of to combine the properties of RF and kilohertz plasma together in a single source. So what we did is use of a sub-RF regime. Basically, in literature, people use up to 100 kilohertz as a low frequency kilohertz plasmas for low temperature application, and RF above 13.56. So this sweet spot is not being explored. So we utilize this frequency range as a base oscillation frequency of 520 kilohertz, pulsing it over 1 to 30 kilohertz. We make a modular range of voltage from 1 to 14. And with a proper LC tank circuit combination, we can control nanosecond rise time, tune this oscillation frequency as well, pulse modulation, applied voltage, and deliver targeted nanosecond pulses. And these sources become a robust and modular source. So any range can be accessed using fine tuning of this source. So next is the characterization. So as I mentioned, with precise charging of capacitor, it is being an LC tank circuit, the energy is being delivered, and the output is several kilovolts. This is a 9 kV load characteristics. So we can see, since plasma jet is a capacitive reactor, so current leads the voltage. So this waveform structure we achieve. And corresponding to the gas temperature for different voltages and frequency, we can see the maximum achieved is roughly close to 50 degrees centigrade. And the applied power for different frequencies and different voltages is being shown. So plasma jet reactor, we used a plasma jet reactor here. This is the impedance profile. So it has a capacitance nature, we can see as by phase. And this is done at ambient air. So it has open air resistance and capacitance. So from the theoretical cylindrical capacitance, we achieve the dielectric capacitance as this and gas capacitance which as this 0.95. And from actual, if it is, we do it in a series combination, we get the same as 0.582, which is measured through the impedance analyzer. These values are being utilized to simulate the circuit what we have developed and in a MATLAB simulating environment. So this is an equivalent circuit diagram. At no load condition, we able to match the voltage waveforms with the simulated one. And at load condition, these are beat or node points. Basically, this is the mismatch of the primary and the secondary waveform. So it at a constructive and destructive interface. So at constructing point it increases, and at a destructing point it goes to 0. So but at load, due to changing dynamic of impedance, these node points appear. So we are able to simulate this with the actual one. Next is the factors influencing plasma property. So these, as I mentioned, voltage, feed gas, gas flow, these are important parameters to characterize the plasma, which basically influences the electron density and reduced electric field strength, which is dependent, indirectly affects the chemistry, radical chemistry, and which are important for application for surface and volume processes. So optical emission spectroscopy is used to characterize this gas phase plasma. We can see different signatures of argon line transition and OH radical and oxygen radical. These are possible reaction for basically formation of leads to formation of argon metastables, and with respect to several electron impact excitation, we can see these transition lines. So by sweeping over different voltage and frequency, we found that for highest voltage of for highest frequency 30 kilohertz and a voltage of 9 kV, we achieve highest O radical intensity, same for OH radical. And this is for the normalized plot with respect to electron impact excitation of argon at 696.1, which is known to have the electron impact, most of electron impact excitation transition happens this. So OH radical intensity is proportional to applied voltage and frequency. O radical intensities also form the same trend. With the applied voltage, what could be the possible reason is that with applied voltage, the reduced electric field strength increases, which basically modifies the electron density and temperature. And with frequency, the average E by N, so basically with the pulse modulation frequency, the number of pulses, the time scale between two repetitive pulses reduces, and hence the average E by N increases. Norm O and OH value sharply decreases and then rises. What it means that the role of memory charges is the dielectric tube having residual ions from the previous discharges, which at as we increase the voltage, the strength helps the previous reactive species help the electric improvement in this E by N and then enhances the further ionization. With flow, we can see that from 3 LPM towards 6 LPM, we can see that the argon star value increases monotonically, but whereas the other reactive species such as OH, O, and nitrogen are almost marginally affected. Another gas used is helium, which we scan from 6 LPM to 12. Helium is a lighter gas, so we need more flow. And voltage and the breakdown voltage is lower, and so it is switched from 4 kV to 9 kV. We can see that even for helium as well, with flow the helium transitions increases, whereas the reactive species of nitrogen and H alpha are marginally affected. These are the image snapshot of over different flows. So we can see for argon, with flow the plume length decreases, and at a low flow rate, it is like a very constricted filament, as we can see. But at higher flow rate, there are multiple filaments coming through the edge of the tube. Whereas with argon, we can see with flow, we can achieve a plume length of even 5 centimeter as well with a very higher flow rate. So why this happens is because at 1.5 LPM with the voltage and frequency condition same throughout. So with the gas residence time is lower in case of 1.5 LPM compared to 12 LPM. So the energy impinging on the gas column in this particular case is very high compared to this. So the streamer formation and the merged streamer is more prominent in case of argon. This is a dominant mechanism in argon compared to that of a helium. So this is plume length variation over flow. We can see with respect to Reynolds number for the laminar flow regime, the plume length is higher, and as it's transitioning to turbulent, the plume length decreases, and the same which happens with voltage and with respect to frequencies as well. Another diagnostics used is molecular beam mass spectrometry. It is basically used to get the gas composition using the residual gas analyzer and positive and negative ion mode to quantify different reactive species generated close to the plume vicinity. So basically what it does is samples the ambient gas into the system, and with the specific stage skimmer and pressure gradient, it samples the gas directly into through ion optics Bessel box into the mass analyzer. So this is a spectra for RGA mode when it is being calibrated with respect for the maximum argon concentration. And the results are of this MBMS is quantified in terms of relative yield. So counts of targeted species with respect to the total count. So kind of a normalization. So with this approach, we see that for O plus positive ion spectra at 1.5 LPM, we see the O plus and OH plus trend is with voltage, the values increases, and with frequency as well, with highest frequency 30 kilohertz, we get the maximum yield for O plus and OH, and the similar trend is for O minus and OH minus. These graphs are for the distribution of different species generated in the positive ion, and this is the negative ion. So other dominant species are OH, NO plus, O2 plus, nitrogen, and nitrogen combinations. So basically it is the different combination of stoichiometry of H, N, and O. So we can see with voltage, different nitrogen and other ions increases with voltage. With frequency as well, for 30 kilohertz, due to interconversion of one species over complex reaction pathways, we have different interdependence, which I will be showing in the later slides. For voltage in negative ion spectra as well, we can see for a negative N minus and other combination. For voltage, though HNO and oxygen are marginally in marginal values, whereas others are in a relatively higher yield. Okay. So with argon flow as well, we can see oxygen plus OH plus also with flow it diminishes, and argon plus, so all the argon over the higher flow rate or the lower flow rate is converted to different specific ions. Similar for negative ion trends as well. So at the end we see, if we compare the relative yield of RF and sub-RF, so for RF case it is comparable, sub-RF and RF are comparable for negative and positive ion, where a kilohertz case is much smaller than the sub-RF case. So we can say the developed source is much more efficient in terms of relative yield of O and OH plus, the major oxidative species. These are the trends of different species as well. So so I'll quickly, this is done for helium spectra. So these are interdependence over of argon reaction chemistry. So we can see these reaction pathways are very closely interlinked. This is for negative ions. Plasma liquid interaction. So we can see that when plasma interacts with liquid, diverse physical mechanism happens, such as evaporation, penetration, sputtering, free convection, and with these leads to different chemical reaction pathways. So the stable long-lived species are H2O2, nitrate, and nitrites. Emission spectra with gas, with free in a gas phase, we can see only OH is there, but when it interacts with liquid, a very high-tense spectra of nitrogen, OH, and other H alpha is also seen. So from this H alpha stark broadening, we arrived at 10 to the power 21 per meter cube. So titanium oxysulfate method is used to characterize H2O2 in the plasma-treated liquids. I'll skip. Terephthalic acid is used for OH radical quantification in liquid, using fluorescence spectra when excited with 310 nanometer and 425 emission at 425. Physical properties are measured through pH, pH meters, multifunctional pH meters, and UV spectrometry to analyze the dye degradation. So basically calibration is performed and we get a linear calibration for both the cases. Methylene blue dye degradation, so a model dye, cationic dye methylene blue is taken at varied from 6 to 9 volt, and for this 15 to 30 kilohertz for this time scale and this volume, we can see that with time at a time of 10 minutes, roughly 600 seconds, the decoloration is saturated, whereas for the lower time it is relatively increasing. Same for voltages as well, but whereas if we see around different time scale, the degradation increases very fast with respect to different applied voltage. So this is basically that over time the surface of the liquid gets saturated with the reactive species and no more further dissolution can happen. With initial concentration, the effect of initial concentration is seen that with higher concentration, more time it takes to degrade. With highest concentration with voltage, we can see, with the maximum voltage, we get the maximum decoloration. And this is the UV visual spectra. So we see the absorbance is measured. This is at 150 second, and as we go more time, the absorbance, specific absorbance at 664 nanometer due to N nitrogen double bond C reduces, which is the characteristic how we measure the degradation of methylene blue. Degradation pathway is quantified the subsequent OH attack on the parent molecule in this way that first the methyl bonds and decreases. So basically it's based on the bond energy. So OH will abstract electron from the bond, and similarly it reduced to the elemental form of nitrate, sulfate, carbon dioxide, and H2O. And for reactive species dissolution, we see that for OH radical, which is short-lived, 1 microsecond lifetime, with time we can see that the fluorescence intensity, which is used to quantify OH, for 9 kV it gets highest and it saturates at a specific time. And same is, so at 30 kilohertz we get the maximum dissolution on the surface and then it saturates. So basically it is due to, first of all, the respective dissolution liquid saturates over time, and second, the terephthalic acid, which is used to quantify itself, is an organic compound which degrades over time. So this might be the reason. H2O2 is quantified in titanium oxysulfate, and we see with time the H2O2 concentration increases for both conditions. 30 seconds, sir. And with pH, we can see with increasing nitrate concentration, the long-lived species HNO3 decreases the pH. Solution conductivity shows the resolution of ions, which improves over time. And compared with the sinusoidal one, we see the H2O2 has much more concentration in sub-RF compared to sinusoidal and OH as well. And with volume variation, we also see that with low volume, we achieved roughly around 400 micromolar and H2O2 at roughly around 4 millimolar. So typically, potential application of this source could be in the areas of biomedical, where basically liquids are part of the substrate of the reaction. So biomedical application, wound healing, antimicrobial, sterilization, destruction of harmful organic compounds such as PFA, which are carbon-fluorine bonds, and pharmaceutical and personal care products as well, nanoparticle synthesis, in seed germination, growth and its quality, and food shelf life as well. So, in conclusion, sub-RF source is developed, which we can tune with nanosecond rise time or pulse modulation frequency. With developed, we can optimize the RNS yield. At 9 kV 30 kilohertz and this lower flow rate, we achieve the maximum concentration. Physical properties of the water is studied over different times, and methylene blue degradation is analyzed. I'm thankful to my supervisors, my mentor, Veda Prakash sir, for conceptualizing the work, and RF, CRF. Special thanks to seniors, all members of PPL and APRL, and to my friends. This is our good APRL, and thank you.
Okay. Now, due to time limitation, one question can be taken. Okay, please.
Backstage.
Can you go back to slide number 15, please?
15.
15 specifically, okay.
The jet-like structure,
this one?
This slide. So do you measure density
Not
of the...
audible.
So how do you measure the density of the plasma?
Density of plasma?
The jet.
Actually, we have measured indirectly using this OES spectrometry. When plasma was interacting with the liquid. There we go.
Okay.
So using Stark broadening H-alpha method, we basically first measure the FWHM, then deconvolute the Lorentzian and Gaussian profile, and from there, subtracting the van der Waals collisional method, from there we get the the FWHM of the Stark one, and so the empirical formula we achieve that level. So it was only possible because when the plasma was interacting with liquid, so as I mentioned, there are various dynamic processes, so which improves the H dissociation, and then when the H-alpha transition at 656 was observed, and we applied that empirical formulas to get it. It is widely been used in the literature for quantification of electron densities using OES.
So you didn't use any Langmuir probe?
No, actually in atmospheric pressure we can't use any, because as soon as if you interact anything, the whole scenario changes, because in atmospheric pressure 1 micrometer is the mean field path. So we can't use directly. Only spectrometry methods are widely used. We can use TALIF, LIF and many others.
Thank you.
Yeah.
Okay, let's stop it here.
Yeah.
Okay, thanks the speaker again.
Thank you, sir.
So the next presentation will be from Sahil Jain, CSAR Sri Pilani. So 15 minutes plus 5 minutes Q&A, okay?
This is for forward.
Okay.
This is backward.
Okay.
Continue press for 3 seconds for pointer.
Okay. Thank you.
Good evening, everyone. Myself, Sahil Jain, working as a PhD student at CSAR Siri Pilani. The topic for my today's presentation is Development Strategies for Plasma-Assisted Terahertz Beamwave Interaction Structures. So this is a brief outline of my presentation. Firstly, I will be discussing about the motivation behind carrying research in this particular domain, then the major challenges, followed by the design, development, and characterization of the beamwave interaction structure, then followed by the cold test measurements and the references. So the motivation behind carrying out research work in the terahertz domain is particularly the properties of the terahertz radiation, that it can penetrate through human body tissues like X-ray, but unlike them, it is non-ionizing, so it is safer for humans to use. Also, it can penetrate a wide variety of non-conductive materials like wood, paper, plastic, etc. So it can be used for non-destructive testing application. So all these properties can be utilized in the different application areas ranging from non-destructive testing application to find hidden metallic objects in the different materials, and the quality inspection in manufacturing, and also for terahertz imaging and security screening applications at the airports and strategic sectors. So all these applications require compact high power terahertz sources in the terahertz region with the and plasma assisted backward wave oscillator. It is a potential candidate that can deliver high power in a compact form. So also research at CSAR series is going on the various plasma assisted backward wave oscillator that can generate high power terahertz radiation in a very compact form. So plasma assisted backward wave oscillator generally consists of three major components. First one is the electron beam source, second one is the beam wave interaction structure, and third one is the spent beam collector. So the major focus in this study will be the development of this beam wave interaction structure. And for the plasma assisted terahertz backward wave oscillator, the plasma assists in the electron beam focusing inside the slow wave structure via ion beam focusing mechanism that helps us to eliminate the requirement of external magnetic field to focus the electron beam. Also, plasma assists in increasing the beam wave interaction efficiency by shifting the slow space charge waves near to the walls of the structure. And plasma helps in RF signal generation by efficient interaction of the electron beam and the electromagnetic wave present inside the structure. And to fully exploit the properties of the plasma in high power terahertz radiation, especially for enhancing the beam wave interaction, the precise dimension control over the fabrication of the interaction structure is very much crucial, and also the surface quality of the designed interaction structure should be very good in order to propagate the electron beam and the electromagnetic radiation in a longer duration. So the major challenges arises during this research studies were there is a requirement of a very reliable and advanced manufacturing technique that can help us to develop these structures with good surface quality and very less dimension tolerances. Also, there is a requirement of providing consistency and repeatability in creating these small sub-mm kind of interaction structures. And also the tight dimension tolerances between the different components of the electron beam source is very much crucial in order to develop the high power terahertz source. So beginning with our designing work, we designed the beamwave 3D model of a unit cell of the beamwave interaction structure in the COMSOL multiphysics software and perform eigenfrequency simulations to determine the operating band of this particular interaction structure. This interaction structure should be operational in terahertz and the sub-terahertz region to cover the wide bandwidth. Also, the RF module of the COMSOL multiphysics was utilized, and the dispersion plot of this particular unit cell was plotted, and it is operating in the range of 82 gigahertz to 110 gigahertz, which is a W band frequency range. And after the designing part, when we got the operating bandwidth for the particular interaction structure, we tried to develop this planar interaction structure with the help of different microfabrication techniques which are available at our institute. Initially, we employed wire electrical discharge machining process, which is a non-contact type based machining process, and in which deionized water act as a dielectric medium between the tool electrode and the workpiece, and the brass wire of 0.2 mm was initially used to create these sub-mm millimeter wave structures. And the wire electrical discharge machine uses a brass wire of continuous spooling, which help us to create these sub-mm structures in a very uniform mannered through the entire length of the interaction structure, and better uniformity was achieved, and wire EDM process have very lesser machining time as compared to the other machining processes. Only limitation of this process was the surface quality of that particular developed interaction structure was not very good. So with learning from this particular machining process, we move forward to the another machining process which was micromilling. Unlike wire electrical discharge milling process, it is a contact-based machining process in which the tool electrode comes in contact with the workpiece and etch out the material from the workpiece. Initially, the workpiece and the tool electrode was immersed inside the cooling liquid to etch out the debris and reduce the heat effective zones. So this helped us to create the interaction structure with better surface quality, and the dimension control was very well achieved with the micromilling process, as it is a contact-based machining method. Also, the formation of built-up edges with the chips was also reduced, which helped us to improve the surface quality of the developed interaction structure. These are the characterization results of both the interaction structure that have been fabricated through the different microfabrication techniques. Figure A shows the same image of the wire EDM structure that has been fabricated, and for the figure B, it shows the micromilling image of the structure that has been fabricated. And these table 1 shows the dimension deviations that have been achieved for both the interaction structure using different fabrication processes. And overall, a dimension deviation of plus minus 20 micron was achieved for both the structures. And for the table 2, we can see the surface finish of the desired interaction structure. For the wire EDM, it was coming around 960 nanometers, and for the similar for the micromilling, it was around 150 nanometer, which is much acceptable in the range of terahertz frequency range for the 100 gigahertz, as it is less than the skin depth of that particular frequency at that frequency range. And with the achieved dimension deviations of the fabricated structure, we tried to perform the cold test simulation using the RF module and the frequency domain analysis. We developed the interaction structure with the W-band matching waveguide, because for the cold test experiments, we have to match the waveguide section with the VNA ports also. So we provide a matching network for this particular interaction structure and perform simulations for the exact dimensions that we have developed, and compared for both the wire EDM and micromilling developed interaction structure, and there is a good correlation, and it fits well within the W-band frequency limits that we have obtained earlier from the dispersion curve. And after this cold test simulations, we move forward for the cold test measure experimental analysis, and we performed the cold test experimental analysis using a W-band casing that we have developed at our institute, and integrated those upper and lower plate in a staggered vein kind of a manner, and inserted it inside the casing and connected it with the VNA ports of the frequency extender that we have used. And these are the experimental comparison results for the simulated ones and the cold test experimental results, and there is a good correlation between both the results. Deviation of 4 gigahertz for the experimental and simulation results was obtained. This is mainly due to the impedance mismatch between the VNA ports and the casing that we have used for performing the cold test measurements. And these are the references that we have used for carrying out this research work. And further, for the future work, we can extend the fabrication process for the higher frequency backward wave beam wave interaction structures to work on the higher frequency backward wave oscillators that we have planned to develop. So thank you for the time.
Okay.
Yes, sir.
Thank you for your presentation. Nice presentation. So now it is time to take few questions. 2 questions. Oh, okay.
What is the tool size for the micromilling?
Sorry, sir?
Tool size for the micromilling?
Sir, 0.3 mm.
0.3 mm.
Because the smallest dimension was 0.269 mm. which was the wall depth, wall thickness, and the etch out region that we have to fabricate was 0.797 mm cross 1.786 mm. So we initially use 0.3 mm micro machining tool for
this EDM thing you had done yourself, or you gave it to someone else to do it?
Sir, I have myself tried that wire EDM and the micro milling process on the machine.
You may be knowing if you do the wire EDM very slow, you get very, very smooth surface.
Sir, for the wire EDM, we can have it smooth surface by passing that particular wire through in multiple etching depths. Initially, for this particular results, we have etch out the material in a single pass only. But if we etch out the material in multiple passes of that particular structure, we can obtain much better surface finish for wire EDM also.
Okay.
Okay. So I have a question. So in your comparison of low power text signal DNA,
yes, sir.
So you have some there is some mismatch between simulation and experiment.
Yes, sir.
So how did you develop the mesh here?
Develop
mesh design.
Mesh design.
Huh?
For the simulation part.
Huh?
Sir, it was a physics domain meshing that we have optimized for this, like only.
So you have done that simulation?
Yes, sir. RF module we have used for COMSOL multiphysics and in the frequency domain analysis only.
Okay. So in this case, the output is open.
Sir, no, we have measured the S11, which is the reflection coefficient. For the one port, we have inserted through the VNA frequency extender, and other port we have shorted because we are developing a backward wave oscillator, so we want to transmit in one direction only.
Okay, okay. So you have made short circuit.
Yeah, we have shorted it from the other end, and we have measured only S11, which is the reflection coefficient.
Okay. You can check S21 parameter also.
Yes, we can also check the S12 parameters also. Yeah.
So it will give more information.
Yeah, it will provide a better information about the transmission characteristics of that particular interaction structure.
Okay. Okay, if there is no question, so let us thank the speaker again.
Thank you, sir.
The final talk of this session, Sumana Hajra from Saurashtra University, Rajkot. So please start the presentation. So you have 15 minutes plus 5 minutes Q&A.
Good evening, everyone. My name is Sumana Hajra from the Department of Nanoscience and Advanced Materials, Saurashtra University, Gujarat. So I am doing under the guidance of Dr. Ashish Ravalia, and my co-guide is Dr. Mukesh Ranjan sir from the FCIPT Gandhinagar. And so This is the outlook of my today's presentation, where introduction, synthesis, characterization, result and discussion, and some references. So I am working in the material science. So I am working in a multiferroic material. So what is the multiferroic material? The multiferroic material is that which has more than one ferroic primary order, which has a ferroelectricity, ferromagnetic, and ferroelasticity in that material, which has many applications like sensors, data storage, and resistive switching. All this kind of applications it is used. So I am choosing in a multiferroic, which is a BiFeO3, where the pure BiFeO3 having a room at the room temperature, which has a high transition temperature. So in this material we get the ferroelectricity and ferromagnetic properties of that material. So I have chosen here the calcium doped BiFeO3. So the dopant in the pure BiFeO3, what is happening? There is some leaky current for the application for the device. So we have dropped the calcium so to balance out the leakage current. So we have chosen that BiFeO3 for the application orientation. It has uses for the photoelectronics like logic gate devices, and then memory storage devices, sensors, and all this device application purpose. So introduction to plasma. So everyone is talk about the theory, right? So I'm going to working on the thin film. So I'm experimented on my thin film doing the plasma treatment. So here this is the plasma. It is the ionized gas consisting of like electrons, ions, and neutron molecules, atoms, right? So when the plasma is exposed to some material, so what is happening? What are the mechanisms can occurs here? So these mechanisms like plasma, physically they are the sputtering or etching on that material, or maybe they chemically react with the surface atom, and third one which is can be break the bond at the surface of these atoms, right? So this is when the ions interact with the samples, the many thing is happening here. So here that the incident ion is falling, and then the sputter, this atom from the surface is some will be the implanted, some will be created some vacancy defects on that samples. So yeah, this is the synthesis route. What I have to make first the material for this thin film. So we have chosen that CSAR method, which is a solid state reaction method. So we have taken some materials and we grind it, and some we heating at the muffle furnace, and we make some palletizations, right, for the to making the thin film. So to fabrication for the thin films, what we have used that is the pulse laser deposition. So here the pulse laser deposition is that when the incident laser is falling on this that target, so there will be the creating of plasma plume on this surface. So it will be deposited on the substrate. So this is the plasma which is created plasma plume. So I think. Yeah, the plasma plume is created here. So it deposited the thin film. So we get this thin film. So after then what we are doing here, we have doing the capacitively coupled discharge RF sputtering we have done. So yes, the Patil sir has explained about that the CCD about the experimental purpose. So what we are doing here, so in this setup we have, this is the electrode power, the positive electrode power. So we put here the thin film. So we have a plasma treated for the different time variation for the 1 minute, 4 minute, and 7 minute, and 10 minute for the 100 power watt. So what is happening? So what we have first done, that this is the pulse laser we have done, we have made the thin film, and after that we have make this the experiment done, the CCD, which we sputtered from the surfaces. So yeah, this is some characterization. This is the AFM images. You can see here, this is my pristine image, which is without plasma treatment. So here this plasma treatment, in these particles are more agglomerated each other. So after the plasma is treated, here the particles are etched out from the surfaces for the 1 minute plasma of exposure. So after then here in a 4 minute we can see here the particles are more agglomerated, maybe redistributions of the particles during the plasma treatment. In the 7 minute you can see the particle size are like more smaller and more making a more sputter from the surfaces. So in a 7 minute and 10 minutes, as well as also the roughness is also increases with that, and also somewhere it decreases after some treatment. So this is the say height distribution for this. Here we can see the Gaussian-like distribution. After the 1 minute, it is it is like became more narrower, right? So in we can see here in this. In the second images, which is the particle separation, we can see here. As in the pristine, we can see that the particle separations are very near. But as the plasma is treated, the particle separation between the two, it is increases with the exposure of time of plasma. So here we get here that the grain size of this particle for the pristine is in 250, right? And after the 1 minute and 4 minute and 7 minute, here we are getting that the plasma grain sizes are reduces with the exposure of the time. So here this is the graph with the separations of these particles and grain size. So this is the CFM we have taken, the conducting atomic force microscopy. So I am studying only the surface. After the plasma treatment, what is happening to the thin film, right? So with the different time exposure. So in this CFM, so in the pristine, we can see here, this is the 2D of images, and this is the current mapping images, which we can get on the surface, the conductivity on the sample, right? This is in the pristine, we are getting the which is the darker and brighter color, which explains that the lighter color is which gives the high current, and the darker color, which is the low current indication of the sample. So this is the line profile, and this is the 3D images. So here in the pristine, we get the conductivity only on the particle grain boundaries only. So after in the 1 minute, we treat it. So here where it is near about the little that conductivity is observed, but after the 4 minute and the 7 minute, we observed here that the conductivity is increases, as well as in not only the grain boundary, but as well as also in the grain interior region also we get the conductivity. So in the 4 minute and the 7 minute, we observed here. So in the 10 minute, it is also the grain boundary and also the interior, as well as we also get in the 10 minute. So this is the CFM IV. What we have done in a random region, we have the tip is scanning of the surfaces, right? So we get the conductivity, and this is the taking from the 0 volt to 10 volt and 10 volt to minus 0 volt with the cyclic behavior we have taken for the IV. So here we get in the pristine, we not get that much the hysteresis loop, right? But as the plasma is treated on the surfaces, we got some the hysteresis loop for in the sample. So yeah, this is the MFM. The MFM is the magnetic force microscopy. So in my BIFO3, there is a because of the plasma treatment, there is a vacancy that created, the defect is generated on the surfaces, right? So due to here in the pristine, we can see the this is the normal, the 2D images, and this is the amplitude of these images, and this is the shows the phase diagram, right? In the BIFO3, we are getting this magnetic because of the Fe ion is the present in the bismuth material. So here the domains are like brighter and darker color, which shows the BIFO3 is oriented towards the 71 domain wall and the 109 domain wall. From the literature survey, we got that, and here we are getting, as in the pristine, we have seen the little, the domains are oriented toward the 71 degree domains, right? But as in the 1 minute, 4 minute, we can see the domains in the 1 minute it increases, but again in the 4 minute it decreases because of that the redistributions of atoms. So due to the vacancy defects are generated in that of this material. Then in the 7 minute and the 10 minute, where we can see in the 10 minute that the gain boundaries are like more oriented or elongated towards the one direction due to the plasma treatment. So we are getting this direction, and more the domain walls we are getting here. So this is the line profile we have taken that. So phase diagram, the domain width is in the pristine is more, but in the 1 minute it reduces, but towards the oriented toward the 71 degree domain wall. But in 4 minute we can see here there is a more width because of the agglomerations of we have seen in an AFM. So in the 7 minute it is again the lower domain width in this material. And so 10 minute, it's again that the lower, the gain domain is oriented toward the 71 degree domain. So yeah, this is the polarization versus electric field. We have taken the PE loop of this sample. So what it gives the idea, when we apply some electric field to that material, how it's polarized, right? In BiO3 there is a Bi, which is a 6s2 lone pair. So due to this, we are getting some ferroelectricity in that material. So when we are applying for application orientation or for the devices, we can know how much the material can retain a certain time or certain electric field when we apply. So at the fixed voltage, at the fixed frequency, the 10 kilohertz, and the varying the different voltages, we observed here that we are getting some loop. But in the pristine, it is the low leakage current we observe. But in the 1 minute, we are observing the more leaky current we observed here. But after the 4 minute and the 7 minute, it reduces the leakage current, which can be applicable for the device applications, right? So in the PE loop, we found it that the different the polarizations we are more towards the direction, yeah, to investigate the response of this material. Yeah. Conclusion is that, so I have synthesized this material by using the SSR methods, and then we have the fabricate the pulse laser deposition, and then we experiment carried out, that is the capacitively per couple discharge RF sputtering, and then we have characterized, because we want to study the more focus on the surface morphology after the plasma treatment, what is happening. So we have taken the AFM, then CFM, MFM characterization technique, and then we observed that in a nanostructure there is a changes, right? In a local conductivity of the sample surfaces also changes, and the magnetic domain wall and the ferroelectricity in this material is also changes, right? So it will be, if the plasma treatment for the device application, it can be beneficial for the devices, so for the future device applications. So these are my references, and thank you.
Okay, thank you for your nice presentation showing the effect of plasma and plasma treatment in your ferroelectric material.
Yes, ferroelectric material.
Okay, so now question is, okay, first, please.
Hi, ma'am. So you fabricated these thin films using pulse laser deposition, right?
Yes.
So you simply place the substrate at like 90 degrees or something, or you kept it at an
On
angle?
parallel.
On
Like,
parallel?
yes,
So
parallel.
you didn't consider glancing angle deposition or any
No,
other
no,
trick?
no. We have not.
So
used
is
that.
there any particular requirement for your, like if you need a porous structure or a crystalline or an amorphous structure, is there any particular requirement for your project, or is it just...
No, it's not that
It's not?
required, but normally what we are using, why we are using the PLD, because it is epitaxial single growth we can find out, na? PLD.
Right.
So that's why we have chosen that PLD.
Okay. And
So
any
single
sort
growth
of,
we can find it.
Right, correct.
Yes.
So I actually worked on a project on glancing angle deposition.
Okay.
That's why I asked. And any sort of assist gases that you use, or
No,
just
only the partial oxygen we have used that.
oxygen?
Yes,
Since
yes.
it's an
Because it's the
oxide,
oxide material, so that's
okay,
why I have to use the oxygen.
Okay, next.
Okay, so I have one question. Like this PLD method, was
Yes.
your thin film was uniform single phase, or did you take XRD?
No, I have not taken XRD.
Okay.
Because I am only focusing on this surface morphology to understand how the plasma is exposed and what the change on the nanostructure.
Okay, and the thickness of the deposition, how much it was?
It's near about 250. Yeah.
50 micron.
No, nanometer.
Nanometer.
Because we are working on the nanometer.
And the plasma gas?
Plasma gas is, we have inside this chamber we have used that oxygen.
Only oxygen.
Yes.
Okay, next.
So what was your conclusion? Which time duration gave you the best performance for magnetic properties?
So, ma'am, is that as the plasma is exploding, so we want to take the IV measurement, right? So we can conclude from that also that how the device performance is giving.
No. In
Yes.
your experiments,
Yes.
you did for say 1 minute,
Sorry?
then till 10 minutes, right? Some
Yes,
4
yes.
minute and 10. Now which one is best?
So, ma'am,
So if you have to
it's
tell
7 to
somebody-
10 minutes. अच्छा हाँ. Yeah.
Why not argon for etching? Why oxygen?
Why oxygen? Because my material is itself oxide. So if we generate
For etching, you used for
yes,
etching,
yes.
right?
For etching only the oxygen we have used. So there are many. We can do the different gases also, but we try with the oxygen because our material is oxide itself. That material. So because of maybe some defects it's creating during the PLD deposition. Yes, ma'am. No, ma'am. It's because in the BFO na, there is some defects, oxygen defects are generating. So due to enhance, because to fill that defect, so we use that oxygen. That's why.
Oxygen also used for cleaning.
Playing a very important role to this material. So.
Okay.
Sorry, I have one more question actually.
Okay.
You said that your grain structure is decreasing with the plasma treatment. So how do you like to explain this actually? Why it is happening?
Because when the ions is exposed to the sample, na, so what happens? Some will be the sputtered. Some atoms will be sputtered, and due to that sputter, you can get that the particle size or grain size will be reduces. I feel that.
Okay.
Hello.
Okay, please.
See, PLD is a process which has a very high cross section for oxidation. Do you know this?
Yes, yes, sir.
PLD is a process where you have the highest cross section for oxidation.
Yes.
So there is no way you can have an oxygen deficient film if you are doing a PLD film in oxygen.
Yes, sir.
So when you say that you are trying to remove some deficiency,
Yeah.
which is little bit dicey, it cannot be.
Okay.
Okay, second question is you are keeping on telling sputtering, but I don't see you are doing sputtering. You are doing plasma annealing, looks like.
Yes, sir.
Are you doing plasma annealing or just sputtering are you doing?
Sputtering, sir.
They're doing etching essentially.
Okay, sorry, etching. We are
No. Are you using a sputter source on which instead of the target you have put the substrate itself and removing the material?
You are using, can you go to that slide showing your targets? And
No, the sputtering part.
Yes.
Go back.
Yeah, what is this? Where is your electrode?
Sir, itself the chamber, it's ground.
Chamber is grounded. Which is the electrode?
This is, sir.
And the sample is kept on the electrode, right?
Yes, yes.
So you are basically, is there magnet underneath?
No, sir.
So you are just doing a plasma cleaning,
Yes,
basically.
yes. Sir.
Have you by any chance measured the thickness? Because the question I am asking is, do you know how much material has been removed?
Sir, actually we have done before the plasma, we have only checked that the thickness by FESM. So after the plasma, we have not observed the thickness.
Because you are doing AFM, right?
Yeah.
All you had to do was create a step while doing PLD. You could have measured the thickness every time.
Yes, sir.
You know what I mean, right?
Yes, sir.
Just partially mask that substrate with a silicon piece, deposit, you already have a step.
Yes, yes.
And anytime you do AFM, you will keep on measuring thickness also.
Yes, sir. Yes, I understand.
Okay, thank you.
Okay, so you should cross-check
Yes, sir.
cross-sectional measurement.
Yes, sir.
And one question from your cyclic voltammetry.
Yes.
So can you show that slide?
Which one?
Cyclic voltammetry.
Okay. Yes, yes.
You have shown pristine sample. Go back here. So which is giving you the optimized result?
Sir, it's a 10 minute.
10 minute?
Yes.
Okay. So what is the structural or any morphological change that drives this property?
Sorry, sir, that I
So-
didn't understand the question.
So my question is, what is the physical change, material property, change in the material property
Yes.
that drives this kind of behavior?
Okay, sir. Due to the sputter of this atom from the surfaces, so there will be creating of some other kind of defect or removal of that surface from the atoms. So maybe due to this reason, we can get this kind of an cyclic IV. Yes, sir. No, sir. No. Okay, sir.
What exactly is happening, right?
Okay, sir.
All you have to do is put it in a furnace and heat it at 900 degrees, right?
Yes, sir. We can put it. Thank you, sir.
Okay, so let us, time is now very less. So I can allow one more before closing the session. Okay. There is no question. Let us thank the speaker again for her wonderful talk. Okay, so now this session is closed. I would like to thank all the participants for their efforts and maintaining time for this session.
So before the end of the session, I now request our session chair, Dr. Vibhuti Bhushan Sahu, to come on the stage and present a memento to our smited speaker, Dr. Neeraj Kumar. Sir, please come on the stage. I also invite our convener, Dr. Nishan Sese, to present a memento to our session chair, Dr. Vibhuti Bhushan Sahu. Two students. Now we have to depart for the gala dinner. Before we have an announcement. So today we have noticed that many of the students came late for the morning session. So we request you to all to please come before the time tomorrow. And tomorrow's session is very important. We have industrial and technological session followed by the panel discussion with experts. So this is a great chance to you to learn and interact with the professional. So we request to please make sure to reach venue before 15 minutes at least. Okay? Thank you so much.